everyone, welcome to this video on machine learning using Python course. Let me ask you something interesting. You type a question into ChatGPT and within seconds it gives you a detailed answer. You upload a photo to an AI tool and suddenly it recognizes object, face, or even generates a completely new image. You open Spotify and somehow it already knows exactly what song you want to hear next. So what's really happening behind the scenes? Now, these systems are not just running simple programs. They are learning patterns from massive amounts of data. This ability for computers to learn from data and improve over time is what we call machine learning. And today, one of the most powerful tools used to build these intelligent systems is Python. Python has become the backbone of modern AI development, powering everything from recommendation system, chatbots, fraud detection, self-driving technology. And companies like Google, Netflix, Amazon, OpenAI, they rely heavily on machine learning models built using Python to process huge data sets and make intelligent predictions. But here's where things get really interesting. Machine learning is not just for big tech companies anymore. Today, anyone with the right knowledge can build models that can predict house prices, detect email spams, recognizes images, analyze customer behavior, or even build their own AI-powered applications. And that's exactly what this course is going to help you understand. So before we begin, let's quickly look at what we'll be covering. First, we'll understand what machine learning actually is and how machines learn patterns from data. Second, we'll explore why Python has become the most popular programming languages for machine learning. Next, we'll learn about different types of machine learning techniques and algorithms used to solve real-world problems. Next, we'll understand how data is prepared and processed before training a machine learning model. And finally, we will see how machine learning models are built, trained, and evaluated using Python. Also, if you are interested in mastering the future of technology, then the professional certificate course in generative AI and machine learning is the perfect opportunity for you. This is offered in collaboration with ENICET Academy IIT Kanpur, and it's an 11-month live online interactive program which provides you hands-on expertise on cutting-edge areas like Gen AI, machine learning, tools like ChatGPT, DALL-E to Hugging Face. You will be gaining practical experience through 15+ projects, integrated labs, live masterclasses delivered by esteemed IIT Kanpur faculty, alongside earning a prestigious certificate from IIT Kanpur. You will receive official Microsoft badges for Azure AI courses and career support through Simplilearn's Job Assist program. So what are you waiting for? Hurry up and enroll now. The course link is mentioned below. Now before we get started, here's a quick quiz question for you. Which programming language powers many of today's most popular AI tools and machine learning applications? Your options are Python, MS Word, Photoshop, or Excel. Let me know your answers in the comment section below. So without any further ado, let's get started.
I'll be your mentor or trainer for this course of machine learning, and I hope we have this wonderful, interactive, exciting journey. All right, so let's begin with this journey and try to understand what is machine learning and why is there so much buzz around it. Let me go through what all we would be covering in this particular course, and then we begin the discussion. So if we talk about a learning path, the first, topic that we will be covering today is Introduction to Machine Learning, which focuses on the basics of machine learning. Second is Supervised Learning, Regression and Application, which focuses on supervised learning with an emphasis on understanding and implementing different types of regression models. Third is Supervised Learning, Classification, Applications, like basically we're trying to cover that what are the different learning techniques available in the machine learning. So first technique that we would be covering up is supervised learning. Under supervised learning, we would be covering up regression as well as classification. Then we would be moving on to the ensemble learning method, which focuses on advanced ensemble methods to enhance the performance and robustness of the models. Then we would be moving on to unsupervised learning and finally recommender system along with the application. What is machine learning and why is there so much of buzz? Why are you here to learn machine learning? Let me put this in another way. So basically, we want the machine to get trained with our data. We want the machine to learn from the data so that it can predict data. What kind of data that we want to predict? Why do we want these predictions? right? Because now are we living in the digital technology where data is all around us? Even this, session is data, right? When all the material that has been sent to you is data, anything on the news which is coming is data, anything doing for entertainment is data, e-commerce is data, your work profile is data, because we are living in huge amount of data is all around us. Do you think is there any escape from data now? No, not now. When I used to take sessions 5 years now, and 7 years before, the scenario was a little different, trying to adapt. But I don't think so. There is now any survival without data. Can you survive without this data? Not moving on social media. And one day, as it says, if the internet stops, do you think your life also stops? Your mobile phone is lost, everything is lost. Isn't it? The data has become a lifeline, and now we see several applications which are working, or the concepts that are being based on data. Now it automatic translation. Translation has not become difficult. If you want to convert something from English to German, German to Spanish, any language, translation is right there. We speak to the machine and we get the translation. Virtual personal assistants are there. Image recognition, email spam filtering. That's actually comes under the domain of machine learning. That it, based on the algorithm or the pattern or the text or the words which are there, it is able to filter out whether the mail is a spam or not. So, what do you think would be the criteria? Generally, the mails with spam are saying that you have a lottery system, other system, or there is a bonus. So, that becomes your email spam filtering. Then we have the text and the speech recognition, medical diagnosis, online fraud detection, is there, where we want to detect how is the online fraud happening, web search and recommendation engines, and of course what is going to be the traffic prediction. Not only the traffic prediction on the roads, but it also related to the traffic going on to a particular website, whether that website is going to get crashed or not. Data becoming now difficult to handle because it's digital data. Understanding data, everything numerically is difficult. Earlier the data was this much, it could be handled. Now it's becomes like this much and this much and this much, and it's increasing. So we need certain algorithm, we need technologies which can help to analyze so that we can improve our performance. But if we look at on the overall scenario, still there is a lot of confusion about the AI, the machine learning, and the deep learning. Yeah, what is the subset or the issues, like what is artificial intelligence, machine learning, and deep learning? Are you able to distinguish between the three? So this is one of the initial chess, developed by the computers. IBM Deep Blue chess program developed in 1997. When was it developed? It was developed in 1997 by IBM. And this particular program was strong enough to defeat the world chess champion at that particular point. His name is Gary Kasparov. Okay, he was capable of defeating the world chess champion. Getting my point? Right? And then we have this IBM Watson under machine learning. So AI is the bigger branch. All right. Artificial intelligence is the bigger branch, right? Under which we have the machine learning subset, right? Which we are going to study. In machine learning, basically, it works on statistical algorithm. That is why we say that before learning machine learning, it is important to have a good concepts and knowledge of statistics that helps to understand. So based on statistical foundation, statistical algorithm, the machine is capable of doing Google search algorithm, Amazon recommendation, and email spam filtering. How, like we just saw, that it is capable of filtering the email. And then finally, we have the deep learning, which is also under machine learning, in which we have the AlphaGo, the natural speech recognition, and the level 4 automated driving system. The scenario has changed and we are into the AI revolution. So the bigger branch is still AI. We are seeing, we are the, witnessing this revolution in front of us. Under AI, we have the machine learning. Under machine learning, we have the deep learning. And under deep Gen AI task, right? So when we talk about the Gen AI task generation fine tuning, we have the agents, automation, and the virtual assistants. And this Gen AI is now capable of even doing a lot of text generation that we see. We ask a lot of things to the chat GPT, other models like Gemini, Copilot also. We want to generate images, video generation. All these things are being possible. AI that we are talking at the moment is only and only related to the software. Through software, we are able to or give intelligent answers. But what is basically the difference between a traditional programming and a machine learning programming? So let me explain you with this particular example. So in traditional programming, again, we have this data, right? That this is my data, which is 1, 2, 3, and 4, right? And over here, we have machine learning algorithm where we have 1, 2, 3, and 4. Okay, the data has not changed. I'm giving you a very simple, example. Now, if we talk about the program, initially the program, when we talk about C, Pascal, Fortran, even C++ and Java, and even Python, they are capable of giving logic. Now, if I want to distinguish that, what are the numbers, what is the logic behind that these numbers are even or odd? So simply we understand the logic that if I talk about Python, I percentage 2 is equal to 0. That means if the remainder divided by 2 is 0, then the number is, it is odd, right? Else it is odd. Getting my point? Yes or no? This point is getting clear. So now, even if a number 10, it would automatically give me that this is going to be an even number. And if I give the number 57, it is going to be odd. But now, machine learning, how things happen, I give the output along with it. I say that 1 is odd, 2 is even, 3 is odd, and 4 is even. Got it? Now the computer, based on certain statistical concepts, algorithm will try to detect that when I feed the number 10 over here, that it is going to be even. Can it predict me as odd also? Yes, the prediction can be wrong also. Clear? But if the algorithm has to be good enough that it is predicting that 10 is even and 57 is odd. So coming on to the concept, the first kind of learning is known as supervised learning. What is it known as? Supervised learning. That if this is my known data, this is already now images, that this is my input, and I also feed the output. When I feed the input as well as output to the machine, it becomes my labeled data, right? That means this is an image of an apple. I feed it into the machine, and when I feed this apple, it says, predicts that is this apple or not, and it predicts it's an apple. But it can predict wrong also. So might have seen sometimes the chat GPT also gives wrong answer. The image development, Ghibli and all give wrong answers. the biggest fear, that these, if a wrong or a incapable data is set to them, then it can give false and nonsensical and fabricated information also. So this is the fear that we are now moving ahead, right, Ajay, Charan, Hardik? But if we talk about earlier system, if we talk about the traditional systems, expert systems were working that we have a user, we are trying to give the query and then try to get the output out of it, right? If this is my query and this is how I get the output out of it, and then I try to infer what is it. But inference is not coming from the data, but this data, it's coming from data, but this data is created from an expert. Now, what do I mean by that? Let me explain this to you. Expert can be a cardiologist, a lawyer in different domains, right? A cardiologist, a lawyer, somebody from in the finance domain, maybe for 30 years, 30 plus years of experience. And we created if else knowledge, inference knowledge, that whether you are capable of getting a loan or not. And if I have a cardiologist, some information has been fed that maybe your BP rating is this much, or your terms. If that is matching to the inference engine, that's how it will give the output. So what happens? For example, if you are a user and you enter to the user interface, maybe all your blood reports, your BPs and your test reports, all things are given as the user interface, right? And then we do the inference engine, and based on this knowledge base, we get the output, right? So what has been replaced now? Rather than knowledge base, it is completely based on the original data, and things have become complicated on images, on, non-structured data. So do we understand supervised learning now? Can I say more the data, more my system becomes intelligent? It is only capable of recognizing hexagon, triangle, and square. And if I add a shape of a circle, maybe a parallelogram, maybe a rectangle, it's capable of analyzing that. So that is where, the systems are getting modeled, because the data is becoming huge day by day, right? So this is supervised learning. So under supervised learning, we have the label data. What is label data? We have the input as well as the output, where we try to train the model. After the model has been trained, based on the test data, we try to do the prediction, whether it is a square or a triangle. Clear? We will initially start with supervised learning, that we have the input, the output. We will try a model. So where will we do the model? That means now the data, the 70% of the data will be used for training, and 20 to 30 percent will be used for testing. Then it will predict the output. Okay. And as I've been telling you, there is a very strong relationship between machine learning as well as statistics part of it, right? So statistics is a field of mathematics, but when it is combined with computer science, the machine learning, it becomes statistics and machine learning. The idea of statistics is that it helps us to draw inferences, relationship between variables, whereas machine learning gives optimization, prediction, accuracy, etc. Right? And then we have prior assumptions about the data, some knowledge about the population usually required. This is none. Dimensionality of the data usually applied to the low dimensional data. And knowledge overlap, there's no ML knowledge required when we study statistics. But in machine learning, some statistics knowledge is usually needed, as it becomes the foundation for few algorithms. So if you do not know much about statistics, there is nothing to worry. It's not very difficult. Definitely concepts of probability would be required. So I would just request you, the learners, to Get familiar with the concepts of probability, conditional probability, Bayesian theorem, and probability distribution. So this is what I expect from you all. Got it? Right? And to make the picture a little more clear, the boundaries are not very crisp now because there is data everywhere. But to make the picture a little more clear that, when we start with initially Python course, we are doing visualization, exploratory data analysis, maths and statistics. And when we try to do overlap between AI, machine learning, deep learning, we get this data science. So data science becomes the foundation for AI, ML, and deep learning. If I technically ask you what is learning, and now you might have been hearing this word agent, it could be a human agent, it could be a robotic agent, it could be an AI agent. So if we talk about a little more technical definition of learning, basically we are trying to improve the behavior based on the experience. When we say you are a very learned thing, you experience, that means different types years of knowledge. The range of behaviors is expanded. The agent can do more, right? The range of behavior is expanded and agent can do more. The accuracy on the task is improved. The agent can do things better. And the speed is improved. The agent can do things faster. So what is the idea of learning? If you see this, means that DS, okay. So if we talk about learning from the machine as well as from the human point of view, this definition is valid. That it is the ability to improve our behavior based on our experience, right? It's not always about acquiring new skills. That's one of the things, that range of behavior that you are, driving, swimming, stitching, cooking. Of course, the range is increased, but also accuracy. By doing the thing again and again, doing learning increases my accuracy as well as speed. And if we now see technically in machine learning, the different types of learning techniques are supervised learning, unsupervised learning, semi-supervised learning, and reinforcement learning. So all these kinds of actually learning come from the fact that how we as humans also learn. So do you also agree? Only agree through training and testing? Training and testing happens when we are going to school, we are trained and then we are tested in universities, colleges, or even this session. Is there any other way we learn also? Do we learn through observations? Do we learn through our mistakes? Do we learn? There are different kinds of learning also possible. And exactly the same thing we also try to replicate in our machines also. So one of the learning method is observation. So one basic difference between supervised learning and unsupervised learning. What do we mean by supervised and unsupervised learning? Supervised learning says that this is my data, right? Are my apples, right? And I tell them that this is my image, these are apples. I data 70% of my data is used for training and 30% of the data is used for testing. Label data is given in absolutely correct, Mega. Label data means supervised learning. And then the model predicts me that it is an apple. And what is unsupervised learning? Do I have a label data? No, I have not told that this is an apple or this is a banana or this is a peach. But the model or the algorithm, sorry guys, is capable enough to distinguish between the three of them, that this is my apple, this is my peach, and this is my banana, right? So initially we will, build concepts on this supervised as well as unsupervised learning. The machine is given huge sets of data that are not labeled as inputs to analyze. The machine needs to figure out the output on its own, where it identifies the patterns. And the two types of algorithm which come under unsupervised learning are association and clustering. And K means for clustering problems and a priori algorithm for association rule learning problems. Right? And then we have supervised learning. The input is in the form of raw data that is labeled. The machine is already fed with the required feature set to classify inputs, divided into two types of problems, regression and classification. And then we will try to understand different regression algorithms. This is the first stage that we are going to work on. Clear? So now let's understand what is self-supervised learning, Here we have the input data. Is it labeled? No, this is not labeled data, but we have partial labeled data, that this is an orange and this is a banana and its quantity is less. And here both the types of data are mixed machine learning model, and this is my unlabeled data to predict the output. So it's an apple. So this is my input data, right? This is my partial data. And when I combine them together, prepare the model, I get the output. Clear? And reinforcement learning, the most effective way of learning from which we as humans learn a lot. That means from our mistakes, from our feedbacks, from our punishments, from our rewards, right? So if this is the input given to the machine and the machine predicts that it is a mango and I give a feedback, wrong, it's an apple, it notes it down. And now when I feed the apple again to the machine, it says that it is an apple. So making the overall picture a quick recap that basically, if we talk about machines, there are three types of learnings. We have the supervised learning where we have the input and output. And this supervised learning is capable of calculating error, that is output minus the input. And what is because why are we capable of calculating error in supervised learning? Because we have the actual output over here, right? And based on the actual output, is my machine predicting the correct result? That if it is an apple, is it actually telling me an apple or not? Or is it telling me this is a cherry? So I can calculate my error. So the biggest advantage or the simplest way to learn is supervised learning, where we are capable of calculating the errors, right? Here we have unsupervised learning where we do not know the output. It's just trying to do the clustering and association between the objects. And the other type is reinforcement learning, that is not going to be part of this journey. That's generally taken into deep learning concepts, that where the machine learns from its, punishments and rewards, right? And of course that we are capable of calculating error. Again, I'm telling you, in this particular course, we are going to try to cover supervised and unsupervised learning, concepts, algorithms in detail. Now, moving ahead to supervised learning. There are two types of supervised learning. We have regression and then we have classification. We have regression as well as classification. Now, what is the difference between the two? Please try to understand. Under supervised learning, if the output, it's all about output. If the output is numerical, then this is known as regression. And if the output is categorical, then it is known as classification. Getting my point, learners? What we are trying to achieve, that what is going to be the temperature tomorrow. So if it gives me that tomorrow it is going to be 84 degrees Fahrenheit or any other value, then this kind of algorithm is regression. But if I want to predict whether the temperature is going to be cold or hot, this is known as categorical data. Clear? So the regression works on numeric and classification works on variable and categorical. Two types of numerical data. One is discrete, another one is continuous. Do we understand that? And if we talk about categorical data, do we understand nominal and ordinal data? This is what is covered in data science class. So basically, data types are divided as qualitative and quantitative. Very, very important when you divide the data as qualitative, it's categorical. Ordered data is something, like rating, ranking, they come under order. Feedbacks of movies. Nominal is that there is no order as such, the color of the eyes or nationality. And quantitative is numerical values. Continuous, which can be divided, such as distance, salary, price. And something which cannot be divided is example, cats, etc. So now I hope the concept of regression and classification is clear to everybody, right? So making your concept more clear, that regression is something when the task of predicting a continuous, quantity, that I want to predict the price of the house. That price of the house in 2014 was this much. Then in 2024, it is this much, right? And then what will happen? What will be the price in 2034? Clear? So since price is a numerical quantity, it comes under regression. And classification, as I told you, that if I want to separate whether the mail is a spam or not, that comes under a classification problem. Clear? So now we will begin our journey in this machine learning through supervised learning. First, we will try to complete algorithms which are like simple linear regression, multiple linear regression, polynomial, support vector, decision tree, random forest. We are not covering neural network. All the others will be covered. Similarly, in classification, we will cover logistic, K nearest neighbor, support vector machine, naive Bayes, decision tree, random forest. Again, neural networks are not covered. Yeah, so with this, we come to the end of the introduction. And if you will now look at your slide, the ebooks, that is lesson number 2. Now we can begin with lesson number 2. So just have prepared the foundation for that. So let me show you the lesson number 2. All right, so we are now starting with this. I hope now you would be able to locate this particular file in your LMS, in your material. Please look at that. So analyze the distinctions and applications of machine learning, deep learning, artificial intelligence through the real world examples of various technical applications. Differentiate among various machine learning models and explore each model learns from data to predict outcomes. Explore Python libraries for effective data manipulation, visualization, implementation, and machine learning algorithm. So the business scenario says that ABC is an e-commerce company which is struggling with a surge in fraudulent transactions on its website. The manual review process for transaction has caused delays in order processing and led to negative customer experience. To address this, ABC will use machine learning algorithms to detect real-time fraudulent transactions. So machine learning algorithms are capable for detecting the fraud transaction. And these algorithms will be integrated into the company's transaction processing systems to flag suspicious transactions and prevent fraud. Additionally, the company will use these algorithms to predict the customer behavior on the past purchase history, thereby improving the recommendation engine's performance. Now everybody is using mixture. Everybody wants the best. The more you learn, the best output you get. And when I say best output, you want the prediction to be highly accurate. So when your report goes to a machine learning or an AI machine, it has to give accurate result that whether you are, that predicting that, it should be accurate enough to predict that, yes, you are, you have a tendency to have cancer or not, so no, so not only one technique will be used, it will try to use mixture of techniques to get the best results. Got it now? So now are we clear what is machine learning? So machine learning is a subset of AI that assists systems to learn and improve automatically from the experience without being explicitly programmed. Arthur Samuel coined the term machine learning in 1959. It enables programs to learn automatically, making computers more intelligent without human intervention. But human feedback is extremely, extremely important because, see, ultimately, machines are not genius. We have to tell them that this is, an acceptable result or not. So, who is known as the father of machine learning? It's Arthur Samuel, and he coined the term machine learning in 1959. Father of AI, that's John McCarthy in 1956. Yes, John McCarthy in 1956. Are we now more clear what is the difference between the traditional approach where we had the data and where we were programming explicitly the output, right? And the machine learning approach based on the algorithm, based on the data, the patterns it understands, it predicts the output. That is why statistical techniques, algorithms are the foundation for machine learning. It automatically learns the features and reduces the need of manual featuring. Clear? It handles complex and unstructured data such as images, text, audio without requiring extensive preprocessing. Performance improves with more data and learning iterations, enhancing accuracy and generalization. Right? And now do we understand this Venn diagram also? That machine learning, deep learning, AI are often used interchangeably. So AI encompasses simulation of human intelligence in machines. So self-driving cars are, AI. All the robotics come under the category of AI. But machine learning, Amazon Alexa, where we are giving it specific instructions and it gives us output. And when I talk about deep learning involves neural network, which is going to be your next stage after machine learning to understand how neural network work, how are they capable of understanding complex pattern recognition such as recognizing patterns in images, speech, text, etc. So, what are the examples of machine learning? In a chess game between a computer and a person. So why do you think that why is this chess game always coming into the picture? Why do you think is the chess game always coming into the picture? Well, when we talk about human beings, a person who plays chess well is said to be intelligent. It's an intelligent game. Agreed? Is said to be intelligent, and even if the results go wrong, there's no harm. There are no catastrophic results, Even if the person is winning and says the machine is winning, it is not that harmful. Yeah. So that is why, was one of the way where AI exploded in, intelligent gaming systems, theorem solving. That is why chess, AlphaGo, these are the games which you will, read or see when we talk about a little history of AI. So in a chess game, between a computer and a person, the computer uses AI to analyze the game, predict moves, decide its decision. AI uses machine learning to figure out the opponent is a beginner, intermediate, and an advanced level. How the AI uses machine learning to identify whether you are a beginner, intermediate, or an advanced player by predicting our moves, based on our moves, it will immediately judge, that you are a beginner or intermediate or an advanced level, right? And you might be playing a lot of games where there is AI and other, graphics games over there, especially the young generation, right? Well, I don't, but you can, how smartly, they are capable of hiding things and they become smarter. The level changes, as you are also becoming smart, the level of the game becomes smarter, right? We all observe that. So AI decides its next move against the opponent using a complex neural network that learns various features, patterns from the data, right? Then, of course, many applications are there. We see machine learning all around us in spam filtering. Spam filtering actually use knife-based classifier, social media analysis, customer service, chatbots, now a lot of available online recommendation. We all see that. Sentiment analysis. How does the sentiment analysis happen? Anybody who has an idea based on the words and especially the emojis? Is it a smiley? Is it a angry face? Is it a sad face, crying face? All these things are taken into account. So these processes allow computers to learn patterns from the data, make predictions, predict outcomes, classify target, feature, and improve performance. So that's what we want machine learning, that they help to predict the outcome, what is going to be the price of the house or any other thing after 10 years down the line, classify target features based on the similarities and improve the overall performance of the system. And we have seen, is there a very, very strong relationship between the data and the output? Yes. The amount of data, if it is more, of course, the output or the quality or the prediction also increases. Where the red line is the quantity, and if it is high quality data, we get better results, better insights, and better predictions of the output. So, of course, maintaining the quality, authenticity, and removing the errors. All these points have to be taken into account when we are talking about the data and the machine learning algorithms. Clear? Right? So when we talk about types of machine learning, ML can be divided into 4 main categories, each characterized by its capacity to predict the conditions or identify the patterns to produce outcomes, such as what is supervised learning, unsupervised learning, semi-supervised learning, and reinforcement learning. Now, I think the distinction is clear. Supervised learning, we've done this. What are the 3 main points under supervised learning? First is the label data. What do we mean by label data? It will have the input as well as the output. Second point is splitting of the data into training and testing, right? Generally, training happens on most of the data and testing on the rest of the data. And third is calculation of the error. Because in supervised learning, we know the actual output also and whether it is predicting it right or wrong. Clear? And some commonly known, supervised learning algorithms are linear regression, decision trees, logistic regression, support vector machines, etc. So some examples of supervised learning are predicting temperature rise based on the yearly temperature trends. Predicting, why supervised learning? Again, predicting temperature rise. It comes under regression because it's a numerical problem, right? Numerical output. Predicting crop yield based on the seasonal crop, quality changes, again regression. Sorting waste based on the known waste items corresponding to the waste type. This type comes under classification or filtering. So under supervised learning, calculation of error is also going to be an important aspect of machine learning, because we have to be very clear that the output of machine learning will always not be 100% correct. Clear? Now these examples making the picture more clear? And if we talk about unsupervised learning, very much used to, identify different parts of the object, image segmentation for object detection, identification of user groups based on commonalities, identification of anomalies over geographical landscapes based on the data patterns. The unlabeled data set is provided to an unsupervised learning algorithm to discover hidden patterns and to recognize their relationship. So it's not that unsupervised learning is not important. It is equally important to analyze different features, different relationships in the data, right? Rather, this is the algorithm which helps us to discover the hidden patterns and discover the relationships. Clear? And now coming on to the unsupervised learning example, it automatically groups the images based on the similarity that this is unlabeled data. Based on that, it is capable of distinguishing the middle-aged people, old-age people, the young, the infants, the teenage, etc. Got it? And what is semi-supervised learning? As I've already told you, it uses a combination of small amount of labeled data. Sometimes, the data is, that's one of the constraints that we see in data is not completely labeled. A large amount of unlabeled data is used for training. Like supervised learning, it aims to learn from a function that can accurately predict the output variable from the input variable. It uses the unlabeled input to assist the learning process by collecting more information, improving model generalization. So it falls between supervised and unsupervised learning. So suppose this is my raw data and I have partial that this is adults and these are kids. Then the machine automatically distinguishes between babies, teens, and tweens, and also distinguishes between the senior citizens, youth, and adults. Got it? So it automatically learns the correct, groupings of the kids or the different people into teens, tweens, and babies, and the adult ones into these category. Clear? And another example of semi-supervised learning, which we see it practically, that was your question, Megha, that Google Photos is popular example of semi-supervised learning, that when a picture is taken, it gets stored in the Google Cloud platform. And from slowly, the Google tracks, whose picture it is, at what place it was taken. So in various instances, uploaders label images. Despite Google's lack of knowledge regarding image names, its algorithm can identifying by analyzing visual features and shapes and colors, and it does that. It does a lot for me. It's able to identify my friends, my family, in which location I was and where. And reinforcement learning is a type of machine learning where algorithms learn from the environment by performing actions and receiving either rewards or penalties as feedback. If the program finds correct solution, the interpreter rewards the algorithm. If the outcome is incorrect, the algorithm is penalized for incorrect predictions. It must reiterate until it finds a better result, right? So ultimately, reinforcement learning involves an agent. It interacts with an environment, learning from the rewards and states to choose from, and then based on the output, it gives the best action. And if it is an error, it learns it again. All right. So this is my input raw data based on the environment, reward, state, and action. It's capable of detecting them separately. Okay. So the example is this type of learning is seen in YouTube recommendation where the user searches for a particular song. The program shows the list of available songs. So when a user selects a specific song, the system trains itself to remember and deliver similar results for future searches based on the user's interaction, like views, shares, etc. So this is the concept on which recommendation systems work. So other examples of reinforcement learning are game where players can play with bots, autocorrect tools, search recommendation engines, self-driving cars. And then the Python packages that we would be doing in for machine learning. We are aware about NumPy. It's a very powerful tool for numerical Python computing. Matplotlib for drawing data visualization. Pandas. So I hope you all are aware about NumPy, Matplotlib, Pandas. But we will be working more on the Scikit-learn, file, which consists of different algorithms. But the pre-processing the other part is also being taken care before we feed into the algorithm. So a quick recap. So machine learning refers to the machine's ability to learn from the data and replicate human behavior. AI includes machine learning, deep learning, each with unique capabilities for simulating intelligence. There are four main types of machine learning: supervised, unsupervised, semi-supervised, and reinforcement learning. Python packages are folders with modules that organize code for easy reuse and maintenance, improving the development efficiency. Now, clear? So now let's go in for a knowledge check. Question number 1. Yes, learners, are you there? Which of the following best describes the machine learning? A, B, C, and D. Question number 2. Which example illustrates the use of machine learning to enhance customer experience in an e-commerce company? What distinguishes between deep learning, machine learning, and AI? Yes, it is a subset of ML that uses multiple layers for complex pattern recognition, such as recognizing patterns in images, speech, and text. Right. So with this, we come to the end of the very introduction and basics of machine learning. Yeah. So what I'm looking forward is, this is the overall picture of statistics that we have. The learners who have already done data science are aware about it. The ones who are not aware about it, the different types of statistics that we have is descriptive. Under descriptive, we have measures of central tendency and measures of variability. Under measures of central tendency, we have the mean, mode, and median. Under measure of variability, we have the range, variance, and dispersion. And here we have the inferential statistics, how we infer the results. So this is the important part that we are looking at, that includes confidence interval, hypothesis testing. So you can do a lot of search on inferential statistics. And this is what I am saying, that statistical inference, constructing confidence and intervals on population, hypothesis testing, that is what I'm looking. And what is the advantages of these particular program? Because ultimately, probability in data science and AI play a very, very major role in understanding uncertainty, predicting outcomes, how probable the correct the output is. Even the LLM models, the chat GPT is predicting on the probability. Okay, this is the next word. So if it is 70% above, then let's predict the output. How do we model complex system? Enhancing AI. And it is the statistics and the probability together which help in exploratory data analysis and give meaningful insights and features. So as we are going through this flow, we understand we are going to start with supervised learning. What is supervised learning? Before supervised learning, I would like you to cover, cover the basic concepts of machine learning, which I've prepared through my PPT, and then we will move on to what they have shared. Okay. So the first thing is regression, What are the two main algorithms which come under supervised learning? Yeah, regression and classification. What is the difference between regression and classification? Basically, regression happens when the output is numerical, and classification happens when the output is categorical. All right, so I start with my PPT again so that it helps and it gives you strong foundation, clear concepts so that we can move along with that. So if we talk about the first knowledge check, what is machine learning? Correct answer, it is C, that it is an autonomous acquisition of knowledge through the use of computer programs. Second question, what is the key difference between supervised and unsupervised learning? A and B are both correct. What's the key benefit of using deep learning for tasks like regression? How do I, okay, you've written yes, okay. What's the key benefit of using deep learning for tasks like recognizing images? Yeah, they can learn from complex details from data on their own. That's the idea of deep learning. That's the use of neural network. Absolutely correct. All right. So now we start with the concepts of machine learning under supervised learning, which are valid for regression and classification algorithms. Whenever you will say, machine learning, these are the basic questions that will be asked, right? So if I talk about machine learning or supervised learning, what are we trying to, do in supervised learning? What is the main aim? What is our main objective of supervised learning? But prediction of the data. Okay. We would call it prediction of the data, future based on given data, right? We want to predict. And is this prediction always correct or it can be wrong? Can be wrong. They can be errors, right? Right. And so they should be a limit of accepting the errors or rejecting the result, right? There should be some way of accepting and rejecting the results. We all understand this very in a conceptual, subjective matter. Now let's try to understand it on the basis of mathematical functions, right? So here we have the plus over here and here we have the minus over here, right? This is my data set. This is my x-axis and this is my y-axis. These are given as my data, right? And what are we trying to do over here? We are trying to predict the output. So what are we trying to predict? The data, that what is the value of this question mark? What is the value of this question mark? All right. And what is the value of this question mark? Right? Is this question mark a plus sign or a minus sign? Can you tell me? What is this question mark, a plus or a minus sign? What about this? What about this? So this is my first question mark, second question mark, third question mark, and fourth. So based on your observation, can you tell me what is this first? Do you think it is a plus or a minus sign? What does this particular data point represent? Is it a plus or a minus? Because this particular data point is more close to the plus. So if there are chances that this is going to be plus sign, more chances. Yes, it can be negative also, but we can say 70 to 75% or 90 to 95% chances are that this is going to be plus. What about the fourth one? This is negative. Now, what about the second and the third one? What about the second? What about the second and the third? This is going to be a little difficult to say that this can be plus, this can be minus, based on the way the neighbors I am selecting, what will be my output. Agreed? But if technically now, if I use a straight line function, mathematically, how do we use a straight line function? That y is equal to mx plus c. So in all the points which lie on the left side of this line, they all are known as plus. They all will come under the category of plus. And the data points, now all the points which are lying on the right side of the line, they will be all negative because most of the points are minus or the red points. Can I say that all the points which are lying on the left side are plus and all the points which are lying on the right side are negative? There are very few. There is only one plus sign, and if you see, all the points belong to the red negative class. One way I have to do something. But again, the question is, why this straight line? That how do I decide the straight line? So one point to understand is that when data points are given, that is known as a hypothesis space represented by capital H, and the line is represented by small h. Right? And it is going to be this red line which is going to divide the data points into two different classes. So there can be more than one solutions to a problem or infinite solutions. I can draw infinite straight lines. But which one to accept? The line which will be accepted is going to be one with gives me the minimum error. Right? The error word will be different for different algorithms, but I will accept that straight line which will give me the minimum error, or I can say the maximum accuracy. Clear? We will calculate, as I told you, in supervised learning, we keep the track how we can have maximum accuracy and minimum error. So what is the capital H over here? Hypothesis space is the set of all possible legal hypotheses. This is the set from which the machine learning algorithm would determine the best possible only one, which would best describe the target function. And small h is a hypothesis function that best describes the target in supervised learning algorithm. So now, technically, what does supervised learning mean? That the hypothesis or the small h, they can be several small h that an algorithm would come up, depends upon the data, also depends upon the restrictions bias that we have imposed on the data. So next thing is we need to find out mathematical functions which give relationships between the data points, right? So basically now the idea is that we want to find a mathematical function where, we want the error to be minimum or the result to have maximum accuracy. Again, I am repeating, we want to find a simple mathematical function which gives me minimum error or maximum accuracy. Clear? Thank you, Atul. Thank you for your understanding. Thank you, learners. So now, what are the different stages that we are looking at? Now, suppose data points can be of any kind. So if this is my data points over here, and if I want to solve it with a simple linear function, see, straight line function is a simple mathematical form, calculation that y is equal to mx plus c. Okay. So when y is equal to mx plus c, right? And if these are my data points, now how do I calculate my error? This is going to be actual minus the predicted. It will have very high error. And this particular concept is known as underfitting. Do you think that this straight line is consistent covering all the data points? No. Right? So the simple straight line equation or function is not capable of covering all the data points. That is known as underfitting. Other way is that if I draw a function which passes through all the data points, so it makes it a very, very highly complicated mathematical function with high degree, right? So it makes a complicated function with high degree mathematical function. That also we don't want. Why we don't want? Because if the data point is out of all the data points, then this is going to give me my maximum error. So we want a mathematical function which is simple and which covers all my data points. So something like this exponential, right? And this gives me a good fit or a good balance. Now clear? So Ajay says no. So the model even fails to predict labels, what it learned, right? It will predict the labels, but with very low accuracy. The error will be high. So we will not accept models with high errors or low accuracy. So overfitting is a situation. How do I know the error is high? Overfitting. So one way is that error is equal to, if I talk in technical terms, so how do we know that if it is underfitting, overfitting? So that's what I'm telling you. Generally, the formula for error is Bayes square plus variance. What is it equal to? It is bias square plus variance. But the equation is in good balance, not linear. Yeah, it's not necessary that it has to be a linear equation. No. We want an equation which is simple and nice. So how do we know? So now if I say that error is equal to bias square plus variance over here, right? And this is, so how do I know whether it's overfitting or underfitting? It's not about the straight line, but when I have variance, if the variance of the data goes very high, then I know that it is an overfitting model. If the bias of my data goes very high, I know it's an underfitting model. And to keep my error low, I want the bias as well as variance to be low. Getting my point? Right? Now, what do we mean by bias and variance? A very, very typical example. A bias means how far are we away from the original data points. So bias means we are close to the center. Variance, what does variance mean? The spread of the data is also low. So this is the ideal situation we always want the data points to be in. This is where we will say, okay, a good fit has been achieved, where we have the low bias and low variance. Okay. And when we have the low bias and when we have the high variance, low bias means that the data points are near to my actual target points but spread out. So what is the case? Happens over here. This is known as the overfitting case. And what is high bias and low variance? That over here, these are my data points. And this is high bias. So this is underfitting situation. So in whole of machine learning, we don't want underfitting. We don't want overfitting. Of course, this is a worst case where the bias is more, variance is both. The idea is to have low bias as well as low variance. Clear? Okay. Now, I'll explain the previous example with this explanation after this, Puneet. I think so this will make things more clear. So these are my data points over here. A linear model is not a good fit, underfit. That means over here, what is more? My bias is more. What is bias? That my data points are very far away from the actual points. Bias means we are far away from the actual points, right? This is high bias. And what is variance? Variance is when the spread of the data is more, right? And when spread of the data is more or my mathematical function is too complex, then it is overfitting. When my mathematical function is too simple, it is underfitting. And when it is a balance, it gives me the right data. So now when I talk about complexity, now, when I say overfitting means more complexity, that generally linear models give me underfitting, right? We start with simple models, but generally they do underfitting. Then we will move on to non-linear models, support vector machines, tree-based models, deep learning models. Why are we doing this? Because they give me more results, better results, more accurate result, less of error. But what is the cost? That my model has become complicated. I'm losing the interpretability of the model. What do I mean by interpretability? That if this is my input, right, how do I know that this is going to be my output? That's possible in linear model because I know y is equal to mx plus c, that if this is my input, I will get this output, otherwise I will not. Clear? And to make it more clear, the overall picture that I was talking about, please look at this slide. So ultimately, where is the trade-off? Where are we fighting in the whole of machine learning models? If life was so easier, wouldn't have the problems be solved by now? But no, there is still a trade-off which is going. So how will I know it is underfitting, though it is showing in diagram? Is there any? Yes, yes, they are mathematical way. But first, let's get the grasp of the thing, okay? That ultimately the idea is to get highest accuracy, right? And interpretability is also important. Why? Because we want to see why am I getting this output. So we always start with linear regression or logistic regression problems. That is what we do. That is what we are going to do in our whole of this journey. And why linear regression? Because they are linear and smooth, well-defined relationship, easier to compute. And as we move along this journey, decision trees provide good accuracy with high interpretability. KNN clustering. Clustering and KNN algorithm are mid-range. Interpretability is okay and accuracy is also okay. But if I want really good accurate results, that is why new algorithms, complex algorithms were built with kernel-based approach for support vector machines, ensemble methods, and of course, neural networks. Now clear? Is this slide getting clear to everybody? That is why complicated neural networks are capable of solving non-linear relationships, non-smooth relationships, and long computation time. Clear? Okay. If I want interpretability of the models, then I might go in for decision trees, but I will have to compromise on my accuracy. But if I am not interested in interpretability, that we are not, we always want best result. That is why neural networks, deep learning have taken the market. It is we as users who will decide. What is the difference between accuracy and interpretability? Interpretability is how am I going to find out the relationship of output given a particular input? So if I know a mathematical equation, okay, this is related with beta naught x1, beta 2 x1, I know why am I getting the result. But if it is some integratable model like neural networks working in layers, in different layers, in some layer differentiation, integration, addition, subtraction is happening, I will not be able to interpret the result, but it is giving me highest result, then of course I will use it. If I have a very mathematical complicated system. See, now try to understand the whole story again. Let me just repeat the story because this is very important in the whole of machine learning, and these concepts are valid for deep learning also, okay? The story says that we want to predict the output or the data. We are clear? The first point says we want to predict the output of the data with minimum error or maximum accuracy. First 2 points are clear? The threshold, Simon, is maximum accuracy and minimum error. That point is clear, right? And which is the simplest mathematical function that we have? We always talk about a straight line. If that straight line is giving me minimum error, is it that only we will always apply one algorithm, or is it a different algorithms or a different hit and trial methods that we have to apply? It is different hit and trial methods algorithm that we will try to get the output. It's not just, oh God, regression and decision tree is working. Okay, this is the end of it. No, you might go in for advanced algorithms, and that's where the research is going. Why do you think that the problems are not solved? Because every time, every algorithm will have its own pros and cons, and the research is going at each and every level. And it's still going, we are just trying to improve on the algorithms every time. Why? Because we still see the LLMs, the chat GPT giving us wrong answers, wrong predictions. So there is still a lot of scope of improvement, where we have to work. Clear? So life was, if the thing was so easy, I think so by now, everything would have been solved by AI and machine learning algorithm. No. Why is it not simple? First, data is variable, uncertain. It keeps on changing. Secondly, every algorithm has its pros and cons. So the errors, the accuracy, my requirements upon the product, on the data or the algorithm keeps on changing. And that is why this change happens. Right? So they are plethora of algorithms which have been built. As in machine learning, we will always start with linear regression algorithms because of the simple mathematical function and high interpretability, but they have minimum accuracy. But as we move along with the journey of decision trees, clustering, kernel-based, we want maximum accuracy, but the trade-off is that we decrease on the interpretability of the model, right? So as I have been telling you, splitting the data for machine learning in supervised learning, we always and always want to select the data randomly. So there is a function train underscore test underscore split that we would be using to split the data. Train underscore test underscore split, which is part of the Scikit-learn library. This is my data. And we will be randomly selecting it and dividing into training and testing data. Now clear? And most of you see this is around 70 to 80% of the data. And this is around 30 to 20% of the data. Puneet is just wondering if interpretability is more important as we go to complex problems. Not really. Not really, ultimately, Puneet, not really, because we are always interested in the final result. It's something like, as I give my example, suppose, you have a magician and, the magician turns a pigeon into a flower. Are we interested how does it does, or are we interested in the output as a flower? Okay. So we are always interested in the output. Got it now? Better? Yeah. So if logistic regression is having minimum accuracy, then it is a no, Nanda. No. The accuracy is less over here. It doesn't mean that it's a wrong prediction. Logistic regression might not give you the best results for the prediction, and maybe using a neural network would give you, it's something like using logistic regression is giving you 70% of accuracy and neural network is giving you 97%. So that's the difference. But of course, neural networks are better. That means, right? Got it? So yeah, there are a lot of terms which you have to be associated. You have to understand it in the correct sense. I understand I'm giving you time for doing that. Yeah, now coming on to the part that you all are interested that, ma'am, what is the mathematical equation? How do we know the mathematical term which is used to see the output? Now, first of all, we are going to calculate error, right? In regression, the error is known as mean square error. Now, let's start understanding this. So we have this mean square error, okay? The error name is that I'll explain you technically when we move on to regression. Now, in supervised learning, whether it's classification or regression, we know the data is divided into training and testing. Now, tell me which error is more important. Now, let me put it in this way, that you go to a class, and you are pursuing some course, you do errors, you are learning, and you do errors while training, right? And still you don't perform well in the test. And there is somebody who doesn't attend even one single class and performs well in the test. So which error is more important? It is the training error which is important, or the testing error? Among the two. Of course, both are important, but among the two, which one is important? So what is more important, to have the training error less or the testing error less? The training error is less, but the testing error is very high. Is it a good thing? It's an even big failure. So again, I'm asking you this question. Is the training error important or the testing error important? Of course, the final test, if you're not performing well on the final day of the test, then the whole training is useless. Agreed? So when my training MSC is high, of course, I can reduce my training by giving in more data, and my testing MSC is less. What is this case? This is the case of underfitting. Of course, the training error should not be higher than the testing MSC. The model is too simple for it to solve, and then I will say the model is underfitting. Now clear? That was the question, I think so. So now clear mathematically. So this is how I will judge based on my training and testing that my model is underfitting. So I will now not use a straight line to solve my data points. I will not use. Okay. Other is my training MSC is 0. Excellent. But my testing MSC is so high. Absolutely not acceptable case. So this is the case of overfitting, which is high variance. And what do you think the data or the model goes through? Is it more of underfitting problem or an overfitting problem? What do you think? Most of the models in machine learning face which kind of problem? Reducing the training error is easy, but failing on the testing is a total failure, and that is what we will look at most of the algorithms, that how to prevent overfitting in the models. That is why I was telling you these concepts are very, very common to machine learning, deep learning models. So are you getting a grasp of it? And I don't straight away start with regression. Come on, let's start doing it, other things. You have to have good foundation of machine learning concepts so that you understand other materials, the in-depth knowledge, how we accept and reject the particular model. Training and testing, that we will decide, because when the data is there, we will split the data into training and testing, and then we will calculate the training error separately and the testing error separately. Okay, we will have suppose I said 1000 rows, 700 rows will be used for training. Then we will have 300 rows used for testing. Then calculate the errors for training and testing separately, and then decide whether it's underfitting or overfitting. So what will be the best case? Where my training error is also low, testing error is also low or almost equal to each other. So again, looking at the concept x-axis, we have the model complexity, and then we have the predictive error. So over here on the x-axis, this is my underfitting over here. And what is overfitting? That when I start with my model, simple model, my errors are high, both the bias and both the test and as well as the training. As my training increases, the training error or the model complexity increases, the training error decreases, but the test error will dip and then increase because of high variance. So we want to find out a model. How do I decide which model is best for my data? Where the training and the testing error are minimum or close to each other. So this is what I'm trying to explain you. Please try to understand that as the model complexity is less, here we have the bias more. As the complexity increases, the bias decreases. When the interpretability is high, the variance is low, and as the complexity increases, the variance increases. But we are looking at a point where these two intersect to find the optimal model complexity. The variance is the spread of the data. Variance is a statistical term which means the spread of the data. So as my model complexity is going to increase, the complexity, as the complexity of the model increases, the variance or the spread of the data also increases. Got it? That's the relationship. Again, I am telling you, we are trying to create a graph between error or accuracy is going to be opposite of this. And this is my model complexity. We always start with minimum complex model. This is the case of underfitting. Agreed? When my model is simple, but my bias is high, as the complexity of the model increases, my bias decreases, but my variance increases. So I don't want the overfitting situation or the underfitting situation. I am looking at a situation where my error is minimum. So the test error is U-shaped in curve, and where the value is minimum, that becomes my optimal model complexity. Now clear to everyone? Okay. Now, now since the topic has been taken, now let's do one thing. If you have downloaded the ebooks material, I want everybody to make a folder in the desktop and move under lesson number 3. Something like this. See, what I would see is, let me share my screen. In work and data break, how do I understand that? So once you are into, now we're starting with lesson number 3. So do you see this 3.1 and 3.2 learners? So how do you go about opening it? Open the Jupyter notebook environments, install and open the file along with me. So chapter number 3, we have to start with lesson 3. Lesson 3 is supervised learning, regression and its application. Yeah, are we all able to open this? Let me guide them that how do we go about it. See, the prerequisite for the course I've been telling it is Python. So we always, like there are a lot of tools like PyCharm, VS Code, you can do it through other tools. But generally we use Anaconda Navigator download. Please go ahead and go to the Anaconda, fill in your like the details, the email ID, and I want everybody to download the Anaconda, right? And based on your system, whether it's Mac, Linux, or Windows, and go in for a full distribution. Don't go for mini Conda. Google Colab. If you're aware about Google Colab, that's also one of the online tools available, which helps you to run the code in the Jupyter kind of environment. Let me show it to you. Anaconda distribution, go and download it, install it. Or the other one is go to Google Colab over here. Just log in through your Google account. That's the another way to go about it. And from here, I will upload the file. Which file? The file which I have already downloaded on my ebooks. That's there on my desktop. Machine learning. Third chapter, 3.1. And I open it. Yeah. So there are 2, 3 methods, whichever one you are comfortable with, that's not an issue. If you're clear, you're comfortable, Anush, on VS Code, that's not an issue. Got it now? Everybody is there with me now? So this is one of the very safest tool. You don't need to, download the Anaconda on your desktop through the Google Colab, through your good internet connection, you will be able to run the code. Yeah, so this particular file is, basically if I talk about 3.1, again, I'm repeating, go on to your learning management system on the reference material. Please download the ebooks, the Jupyter notebooks, and then try to open. So if we talk about, if we are back to 3.1, let's quickly go through the file. That file is completely theoretical. Okay, nothing great in that file. It talks about what supervised learning is and what are the 2 types of algorithms in supervised learning. It's regression and classification. What is the difference between regression and classification in supervised learning? In regression, the output is always numeric. And classification output is always categorical. So when the target variable is categorical, we do classification. So this example, we are very clear. So when it's predicting numerical value, right, that is regression. When we are predicting a categorical outcome, determining the whether tomorrow it is going to be hot or cold, visualization, the same thermometer scale divided into two colored regions, cold and red for hot, with a threshold separating is classification. And if you look at the applications of supervised learning, do you think HR people use machine learning to identify the different job profiles, shortlisting of the resumes? HR is also using machine learning now. Yeah. In finance, what is the use of machine learning in predicting of fraudulent data? Are you ready for that loan approval or not, right? And this is similar to how a credit card company determines your credit worthiness before issuing a card. Then emails, this is about spam filtering, whether it's a spam or not. Manufacturing, anybody in manufacturing? So in manufacturing, supervised learning is also used to inspect the quality, classify the products into different grades. For example, a factory might use a machine learning model to check for defects in products and ensure they meet quality standards, much like the quality control inspector. Maritime industry, it helps in forecasting the historical events, weather condition. So precautionary accident, it's capable of predicting any kind of, weather. It might get wrong also, which we have seen. And supervised learning techniques like regression model can be used to predict tidal currents, forecast demand and supply, reducing inventory losses. Think of it as how weather forecast predicts rain based on past weather patterns. Fraud predictions, we use this in agriculture field too. I'm into automating parking. So under supervised algorithm, there are a lot of algorithms that we will begin tomorrow. Tomorrow, again, as you understand my style, we'll start with regression, then linear regression, logistic, naive Bayes, KNN, under classification. They all come under classification. So under linear regression, we would be working on multiple linear regression. And before we move on to classification, there are a lot of concepts that we will study, such as, excuse me, excuse me, cross-validation, regularization, hyperparameter tuning, sklearn pipelines. So there is a lot more to be explored tomorrow. We will be concentrating on linear regression and its concepts tomorrow, right? And linear regression is now very clear where the output is numerical, then like predicting housing pricing, we will use regression. After doing supervised regression in supervised learning, then we will move on to classification algorithm. Under classification, plethora of algorithms that need to be done. Initially, we'll start with logistic regression, naive Bayes, KNN, decision trees, random forest, and support vector machines. So it's a long journey. Tomorrow we'll do linear regression. Next weekend we will be doing classification. And then we will move on to the next stages of ensemble learning. Then it is unsupervised learning, right? So I think so you all are excited about this journey. So it's a long journey. I don't want to burden you today with all the concepts. So let's go slow and steady. That's my rule. Slow and steady wins the race. But I hope you got the crux of today's class, right? So this is 3.1, right? And we'll be beginning with 3.2. We started with the very first session of machine learning, where we understood what machine learning is, what are the different types of learning techniques, what are the different types of machine learning techniques, supervised learning, unsupervised learning, and reinforcement learning. What is supervised learning? Supervised learning means it consists of label data, which consists of input and output. We split calculate the errors. The two main algorithms under supervised learning are regression and classification. Then we understood unsupervised learning. Unsupervised learning consists of unlabeled data, where based on the similarity of the data, the groups and clusters are formed. So two main algorithms are clustering and association. And last but not the least is reinforcement learning, that based on the feedback, positive and negative, the machine learns. Are we good to go? Everybody is clear with these concepts of machine learning, the basic concepts? And then we started with the concepts of overfitting, underfitting, and a good fit. Yes, learners. Now you will tell me what do we mean by underfitting, fitting in machine learning. Very, very important question. It will definitely be asked if you say that you know the concept of underfitting and overfitting. Yes, learners. Can you tell me what do we mean by underfitting and overfitting? Underfitting is the case where the error is high. What error is high? Bias is high. We are very far from the actual data point, but we talk about simple mathematical function. What is the advantage of simple mathematical function? That it gives us more interpretability of the model. What do we mean by more interpretability? That it gives the relationship between the output. And if we talk about overfitting, again, the error becomes high because the variance goes very high, right? And definitely it makes more and more complex. So we don't want a algorithm to be or model to be underfitted or overfitted. We want a good balance fit. That is, how do we judge that? That the training error and the testing error should be similar, right? So today we will start with the first, learning technique, that is supervised learning technique and the regression model. Are we good to go? So as now you are getting more familiar with my style, first we will try to cover the concepts and then move on to the practical aspect. Because unless and until you clarity of what is happening, how are we going to interpret the model, there is no point moving on to the code. But definitely we'll move on to the code. But let's start with the concept of regression. So here we go with the regression. So what is regression? Now, if I ask you, what is regression? Tell me. So when we're talking about regression, learners, please be clear with this concept that always the target variable or the dependent variable are all numeric values or continuous value. Don't say the term data, right? See, everything is data, but if you're not very specific, technically you go very wrong, right? So you have to understand now data. We are talking about structured data which in tabular form. It consists of input as well as output values, right? Whatever are the input or the output value, X over here is referring to your independent variables, right? But whenever we are choosing any model or algorithm, we always and always take into consideration the dependent variable. So it is very important that the dependent variable has to be numerical or continuous, right? So we are trying to find out. So basically, what are we trying to find out? We are trying to find out the relationship between the independent variable based on the output. Clear? So let's try to break the term linear and regression. Linear, we understand from simple mathematics that anything of degree 1, any function which has value 1 is said to be linear. So this means that progressing from one stage to another in a single series of steps, sequential extending along a straight line or nearly a straight line. So we all understand the term linear, right? And as very rightly said by Nanda, regression is a statistical terminology which is used to find out the relationship between one dependent variable. We always have one output. If the output is categorical, we will go in for classification algorithm. And if the outputs are continuous or numerical, we will go in for linear, not linear, but regression algorithms. So moving ahead. Thus, a linear regression means a linear approach from. So, when I combine the two terms, linear regression, it means that the linear approach for modeling the relationship between the dependent and independent quantitative variables. It will plot a straight line because that's the simplest linear approach as a best fit along the data points to predict the target value, right? So, what are the different types of linear regression available to us? So, a simple linear regression is with one depend. Obviously, the dependent variable is always one. That's the target or the output. But if the independent variable is one, it is simple linear regression, and it is always represented by a straight line. So, beta naught is the intercept, and this refers to the slope. So this refers to beta naught plus beta 1 x1. Getting my point? And then we have multiple linear regression. That is over here when an independent variable, then this straight line turns into a hyperplane. So line in higher dimension, 2 dimension becomes a plane, and in higher dimension, it becomes a hyperplane. Getting my point? Are you all getting the concept, mathematical equation along with the graphical view? And of course, with the code. I'm trying to explain you from all aspects. All right. And when I say polynomial, sure, Hardik, I can do that. Right. Over here, we are talking about linear regression. Linear means something of degree 1. So do you see all the variables have, all the coefficients have the degree 1? Do you see this? Right? These are known as the regression. So the term linear regression means we are trying to find out relationship between the independent variables with the dependent variable. So a simple linear regression is beta naught plus beta 1 x1. Clear? That is when we have one input variable and one output variable. Mathematically, it is represented by a straight line where beta naught represents the intercept of the line and the beta naught represents the intercept and beta 1 represents the slope of the line. Clear? Have multiple linear regression, graphically, a straight line now becomes a hyperplane. That is a multiple linear regression. Of course, generally, practically, we will have more than one independent variables with output variables. And then we have polynomial linear regression. That is y is equal to beta naught, beta 1 x1, beta 1 x squared, and q. Clear now? So now let's try to understand it from now. The same thing from the machine learning point of view. So in simple terms, it is a method of finding a best straight line fitting the given data set. So in simple terms, find a simple straight line which tries to find the relationship between the independent and the dependent variable. And best linear relationship, how do I decide the term best? Something with minimum error or maximum accuracy, right? Something with minimum error or maximum accuracy is taken in terms of simple terms. And if I talk about technical terms, it is a supervised machine learning algorithm that finds the best fit relationship on the given data set between independent and dependent variable, almost the same thing. But the basic concept or the algorithm it works on it is OLS, the ordinary least square method, also known as the sum of the square residuals. Clear? So to explain these terms graphically, mathematically, I want everybody to concentrate here on the graph or the slide shared. So this is an equation of a straight line. What is beta naught? Beta naught is the intercept. What do I mean by intercept? what is the value of y when x is equal to 0? Are you all getting this point? What does the term intercept mean? That what is the value of y when x is equal to 0? Clear? Is this point getting clear to everyone? And if I talk about beta 1 refers to the slope of line. Is this term getting clear to everybody? Since I have only one input variable or independent variable, it represents a straight line. Clear? Now, once we have understood the equation of the straight line, what do these blue dots represent? The actual data points available, right? That the first data point has value 1, y is equal to 3. This is value 4 and value is equal to 6. All right. Now, this is where how we are going to calculate the error. What is the error? The actual value. This you can consider this yi as my actual value, and the red dot on the straight line is the predicted value if I want to fit a straight line on these data points. Right? So this is my actual output and this is my predicted output. Clear? The error is clear. How are we calculating the error? Now, what algorithm are we technically using over here? Ordinary least square method or the residual. Residual means the error, sum of square error. So what does this mean? It is equal to the sum of the square of error, which is actual minus predicted value. Getting my point? So, and why are we taking the square of the error? There is a story behind that also. Why? Because suppose is plus 2, for example, and this error is minus 2. So the total error is 0. So what I'm trying to say is if the error is plus over here and minus, and if I add them, it will show me 0 error. It is not 0 error. So I will try to take the square of the value. It will become 4 plus 4, that is the error is equal to 8. So always the errors are taken as square of errors and we are looking at minimum square of errors. That is why it is known as the ordinary least square method. We want the sum of the square error to be the least. This is known as the RSS. Getting my point, learners? So this is the total RSS. Why the total? For this particular data point, this is going to be my first error. For this data point, my second error. For the third one, fourth one, fifth one. And if they are infinite points, then infinite data points are calculated. Clear to everybody? So why? Okay. Now, because this is my actual y1 and what is my predicted y1? This is my predicted value, right? Base, because we are using Nanda, this particular function, this is my predicted value and predicted values are represented as y cap. So for the first one, it will become beta naught minus beta 1 x1, then y2 beta naught beta 1 x2 for each data points. Now clear? This is how, based on this mathematical function, I am going to predict my output for each data points. Clear? So the formal statement of simple linear regression. I'm talking about simple linear regression with one input and one output. Y1 is the value of the response variable. Again, predict, target, predicted, dependent. They all mean the same thing. Do not get confused with the terminologies. In the ith trial, beta naught and beta 1 are the parameters. Xi is the value of the predictor variable in the ith trial. And epsilon I is the random error with mean E. Epsilon I is equal to 0 and variance is equal to square. Clear? Okay. Now this random error, this is very, very important to understand that a random error, we are talking about Are we talking about the whole data set or a part of data set or a sample of data set over here? This is my population, and if I take a part of it for training and as well as testing, do I always consider the whole data set or a part of data set? It's always sample. And is my sample, and we want the sample to be the true representative of the population. But since it is a part of the data, there will be some error also associated with it, which is irreducible, that is represented by epsilon, right? So epsilon I is the random error with mean. This is the random error which is always going to be introduced. It's not reducible like bias and variance or overfitting, but it's part of the whole linear regression where the mean of that error is equal to 0 and the variance is equal to epsilon square. Now clear? So the idea of whole linear regression or significance model is that it is highly interpretable. What is the idea behind this? That it is why the error is 0. We always want the error to be 0. In this case, we are considering that, the average of the error, not the square. The sum of the square or the average of the error is equal to 0, not the square. Okay. So now the significance of linear regression lies in the fact that we can easily interpret and understand the marginal changes with input to the output. So linear regression is an highly interpretable model. How is it interpretable? That if we increase the value of x1 by 1 unit, keeping the other variables constant, then the total increase in the value of y will be beta 1, and the intercept term beta naught is the response when all the predictor terms are set to 0 and are not considered. Right? So how much is my y value change will depend on how much is my beta 1, is it positive or negative, beta 2 and beta n. So now, what are we trying to find out in linear regression? The values of beta naught, beta 1 and beta n, right? Where the error is minimum. Clear? Right? I understand, there are a lot of concepts, a lot of mathematical terms coming. So just hold on till we start moving on to the practical part and, you will see them practically. Just try to grasp as much concepts as you can. So the different assumptions which we follow in linear regression is linearity. That is the relationship between the features and the target. Homoscedasticity, the error term has, this is where, the linear regression has its assumption or constraint, and the term is known as homoscedasticity, that the error term is constant variance. Throughout the whole data, the error term will be constant. Multicollinearity, there is no multicollinearity between the features. And if we talk about independence, observations are independent of each other. Getting my point? Normality, this is where the point I was saying that the error residuals follow normal standard distribution where mean is equal to 0 and the standard deviation is equal to 1. Okay, so multicollinearity means that we can have more than one input. Are they related with each other? No. Every first input should be independent with the second one should be independent with the third. The input should not be dependent on each other. They should all be directly dependent on the output. First, let's try to understand the concept. So how do we go about in the supervised learning process? That we have this full data set, right? And we will, after doing all the pre-processing. So today I told you to revise all your EDA, that we will load the data set using read underscore CSV command, do head and tail, try to find out null values, work on them, do encoding if required, and then split the data into training and testing. First step is getting clear. And of course, training can be, it's generally 7 to 80. If you want to keep it 50-50 also, nobody is stopping you. Or 60-40, that's completely up to you. Okay. And the function which is used in Python in the Scikit-learn preprocessing library is train underscore test underscore split. X is the first parameter which represents the features of the input data. So this is how we will create a list or an array which will contain all the input. Y refers to the target or the label vector of the input data. Size of the test data, test underscore size. And finally, we have random underscore state. What is this random underscore state? It is the seed that initializes the pseudo random number generator. What does that mean? That I will give any fixed number. It could be 42, it could be 3, it could be 0, it could be 500, right? I want to keep this number constant so that the shuffling or the randomization of the data happens in the same way so that I can check the accuracy and do the comparisons. Clear? Right? So again, remember this point. Whenever data is given to you, you have to identify it in terms or split it in terms first, in terms in number of inputs and the output. Always separate the outputs from the input, and then we will use this function and then we will get 4 outputs. Train underscore test underscore split gives 4 output, that is x underscore train, y underscore train, x underscore test, and y underscore test. Clear? Training underscore test underscore split is used to split the data, right? We are preparing the data which will be used for training and testing separately. So the parameters of this function are input, output, how much we want to give for testing. It could be 3/4, half, completely up to you, no rules for that. And random underscore state gives me the seed that initializes or does the shuffling of the data in the same manner. And the output of this function is 4 output. I get input training and output training data and input training and output testing data. Clear? And now if I talk about multiple linear regression, right? In 3-dimensional setting with 2 predictors, 1 response, the least square regression line becomes a plane. So this is a multiple linear regression model. Epsilon is the normalized error, okay, which is irreducible. Nothing can be done much about it. And now we will practically deal with data which has 3 inputs: the budget of TV, budget of radio, budget of newspaper, and which one of them affects the sales most. So this is the first, algorithm that we are going to study. Okay. So this is simple. This is polynomial and these are the errors. So let's start with the practical work and then get back to the different errors and analysis. Got it? Have you got an idea what linear regression is all about? So I request you all learners to, from the LMS, to open 3.2 supervised learning regression, linear regression file. Okay. So now do you understand the term independent variables, straight line when we have? In 2-dimensional, when we have 1 input, 1 output, it's a straight line. Blue dots are my data points, and this is a straight line or the line of regression, which I want to fit on the data points. This graph is now very clear to everybody. I'm starting with the file now. The first 3.2 regression, this graph is clear. And where do you think regression is used? It has a huge application in oil and gas industry. Various types of data are collected in oil and gas industry from surface, subsurface to understand production, sale processes, how much gas is required, how much liquid, how much is the pressure that needs to be created. So linear, non-linear regression model forecast global oil production. Oh my God, the whole world is fighting on oil, and well, we can use our regression models to forecast the global oil production, right? So the whole world is on a big fight on oil only, right? Marketing, linear regression helps to analyze the effectiveness of advertising campaigns, predict sales based on marketing spend, segment customer based on demographic data, right? Then we have retail. Then we have linear regression is utilized in retail for demand forecasting, inventory management, pricing optimization, and customer analytics. Healthcare, linear regression is applied in healthcare for predicting the patient outcomes, analyzing relationship between the different medical variables and their diseases. Getting my point? And finally, we have the real estate, that in the real estate industry, linear regression predicts the property prices based on the factors such as location, size, amenities, and economic indicators. Clear? So now what are the different types of regression? Regression can be classified into two categories, linear and nonlinear. Linear regression finds a straight line relationship between the dependent variable and one or more independent variable. Nonlinear regression finds a relationship between the dependent variable and independent variable using a curve or more complex shape. Okay, so getting back to linear regression, it is, so technically if somebody asks you what is linear regression, in machine learning, you will say it's a supervised learning algorithm which is used to, please try to understand each and every term, is used to predict a continuous target variable. Please be clear. It's not continuous data, as you all were saying. That's a wrong statement. It helps us to predict continuous output variable by modeling its relationship with one or more independent variables through a linear regression. It predicts a continuous dependent variable based on one or more independent variables. So it predicts the continuous dependent variable. Here it says target, output, dependent, completely anything you can say. It uses the least square criteria to estimate the coefficients of the regression equation. What do we mean by the least square criteria? That the value between the actual and the predicted value, the square of the error of this error, that is RSS, should be minimum. That is the residual sum of squares. Getting my point? And it can be applied if there is linear relationship between the variables. So in case the dependent variable is continuous and independent variables can be continuous or discrete. We are not bothered about our input variables. So for predicting the output, we are always considered about the output. So the relationship between a dependent variable y and one more independent variable x is established using a best fit straight line, which is also known as the regression line. And there are two types of linear regression. One is known as the simple linear regression. Other one is known as the multiple linear regression. All right. So simple linear regression is clear to everybody. We have one independent variable and one dependent variable. Do we understand now the terms beta naught and beta 1? This is the intercept and the slope. Yes, everybody is understanding now what is simple linear regression. And as I told you, a simple linear relationship is given by one of the input, that is TV expenses over here as my input. And in the output, we have that sales. That means in this particular data set, we are trying to establish the relationship that if what is going to be the budget of TV and how it is affecting my sales. So what do you conclude? Do you see the red points? These are the predicted values, and the blue points are nothing but my actual data points, and I'm going to calculate. It automatically does the calculation of the error if once I apply the algorithm. Clear? So do you see a kind of positive linear relationship? Can I conclude that this shows a little positive linear relationship? That is, the value of TV expenses increase, the sales is also increasing. It shows a positive relationship between them. Getting my point? And practically, if you look at the real world problems, they will not be simple linear regression problem. They will going to be, multiple linear regression problem. There will be more than one input. From how we know positive and negative? See, positive and negative, Basant, that's shows it very clearly from the graph. If the graph is showing this thing, that as my x is increasing, y is also increasing, it shows a positive relationship. See over here. And if x is decreasing, y is also decreasing. But if my graph is like this, what does it show? That x increases, y decreases. And if x decreases, y increases. Getting my point? So this is a negative relationship. Inverse relationship between input and output shows negative relationship. And direct relationship between input and output shows positive relationship. So as I was telling you, practically, if I talk about, real-time data, we have more than one inputs and output. So multiple linear regression models the relationship between the two and more independent variables, predictors, features, and the dependent variable as a straight line. The equation for multiple linear regression is y is equal to beta naught plus beta 1 x1, beta 2 x2, and beta n xn. That x1, x2, xn are the predictor variables, and beta 1, beta 2, beta n are the coefficients of each predictor. So let's start practically working on this data set. That this becomes now, if I want to try to find out the relationship between TV expenses, radio expenses, and sales. So now my straight line turns into this hyperplane. Do you see the difference? How the straight line has got converted into hyperplane? And of course, there is one constraint that we cannot view more than 2D or 3D graphs, right? We cannot view more than 2D or 3D graphs, right? That correlation covariance is same as, regression, but in regression, it's a linear relationship, but the positive and negative relationship is the concept same as correlation and covariance. That correlation and covariance is founded by Pearson's, coefficient of correlation. But here we are talking in terms of linear equation. But if I talk about one input, x1 and y, how x1 is related to y, then that is r. That is this +1 -1. That exactly is the same concept. The concept is not very different. Linear regression is using that particular concept. All right. So now let's start practically working on the data set. So what I want everybody to do is on your, go from data set folder, open your Jupyter notebooks and keep the TV marketing.csv data in the same folder where you have kept this 3.2. Yes, learners, wherever you have kept this 3.2, keep the TV marketing.csv, copy it from the dataset folder and start uploading this data. Clear? And then run this thing. So basically, this data set consists of 3 input variables. This is my x1, x2, x3, and this is my output. All right. So once I have done my head, what does the head command do? What does the head command do, learners? What does it? It prints the top 5 rows by default, and these are my inputs, right? And what does the info function do? Good, Rishi. Good, Anush. What does the info do? It tells me there are no null values in this data set. And of course, unnamed is not required over here. And all other, my inputs are also in numerical value. And what is my output? My output is sales, and that's a numerical value. And that is why regression will be used. Clear? And that is why regression will be used. Getting my point? Okay. So what is the first thing that we are going to do? Since this data does not require pre-processing, it's a clean data, so nothing required to clean or check on the null values, etc. Right? So we are considering the data to be clean. So now when I want to fit any model, what is the first step that I will do? I will try to separate the input to the with the output columns. Agreed? The first step is to extract the features of the data set and output. What is this ILOC in Python code? Index-based filtering. So if I see very closely that 1, 2, 3 are my input index, this is of actually no relevance. This is of no relevance. These are my input values. And this is my output value. Clear? So in this case, ILOC, the first colon represents, it talks about all the rows, but only the columns which are there, it says 1 and 2. So how many inputs are we talking about? Only the first one. Only the first one is TV. And what is the output? Only the sales. This point is getting clear. What are we taking over here? We are talking about TV and sales. So we are trying to implement linear regression, right? We are trying to do simple linear regression. This X and Y is clear. I've only taken a part of it. First, I've taken one input and then I'll take all the 3 inputs. This point is clear, right? And then we have the from Scikit-learn model selection import train underscores test underscore split. And now I am taking my input, that is only the TV input. Y is my sales. Test size, 30% of the data is used for testing, and random underscore state is taken to be 42. 42 is generally considered from a fiction that it's considered to be a a good number for the whole universe. Clear? Okay, so now what are the different steps to now fit the model? Not much of coding. That's why Python is a preferred language, beautiful language. That is from sklearn.linear model import linear regression. That is, first we will import the library. That is, sklearn is the main library, and we are importing linear regression from there. So when I imply linear regression, it is lin underscore reg, and this is fitting. That is the training input and output training data. Getting my point? Fit function is used to fit the data or train the data. What do we mean by train the data? Finding the parameters over here, that is beta naught, beta 1, beta 2, beta 3, etc. Clear? Are you all there with me till this code? Anybody who's still facing any difficulty, who's not been able to run this part of the code? Till here, are we good to go? First step is to import the library which contains the linear regression model. And then I will create an instance of this linear regression function, right? That is lin underscore reg. It is a instance. What do you understand by instance? Object of this particular function, and then fit the training input and output data. It is divided by using this train underscore test underscore split. And we get these four outputs. Input training and testing, output training and testing. I explained you train underscore test split, where we get the four outputs. Now let's try to find out the linear relationship between the sales and the TV. So TV and sales. So we want it to be an input. So if you visualize the linear regression model, X label, we don't want it to be, I think so that's a little opposite of it over here. This is TV change, make changes in the code, and output is sales. How do we delineate contributing and constraining factors in model? What do we mean by that? Huyan, delineate, what do we mean by that? Okay. So what does this graph represent? What does this graph represent? This plot shows a positive linear relationship between sales and TV, and where the blue regression line indicates the model's prediction. The green data points are generally close to the line, suggesting the model fits the data reasonably well, though some variability exists. Right? So does it show a positive relationship, Basant? Right? Do we see that there is a positive relationship between TV and sales? No, it's not the trained data. It is the test data. Why test data? Because I'm plotting input as training and predicting the output. The x-axis is the input. The x is input, right? And the output is prediction of the training, right? So we are trying to plot over here. Plot over here is the straight line, right? But why am I saying the test data? Because actual data points are my input and output test data. Now clear? We are trying to do a scatter plot over here. Scatter plot is between input and output test data. The actual data points are my testing data points. Okay. And the plot, the straight line is input training and predicting the output. That is why it says the linear regression model for test data set. Now clear? So what do we conclude from this graph? We can conclude that the plot shows a positive linear relationship between sales and TV, where the blue regression line indicates the model's predictions. The green data points are generally close to the line, suggesting the model fits the data reasonably well, though some variability exists. Okay, so this shows a positive relationship. Now, the important point is, how do I understand? Is this model underfitting or overfitting? So, when we are developing machine model, what is the most important point, important concept that needs to be taken into account? The concept of overfitting and underfitting. So when developing machine learning models, achieving the right balance between the complexity and simplicity is crucial. What are the points of overfitting? Let's quickly go through that. Overfitting occurs when the model learns the noise and details in the training data too well, to the extent that it is negatively impacts the performance on unseen data, right? That means when the variance is high, high accuracy on the training data, but poor accuracy on the test data. So how do I know that my model has overfitted? That I get a good score for training data, but a bad score for testing data. And why is it? What is the reason? Because the model is too complex. It has got too many parameters. Underfitting happens when the model is too simple to capture the underlying pattern. Poor accuracy on both training and testing data. Underfitting is more easily to detect, but overfitting is a constraining problem. So what are we looking? How do we solve this problem? We want a bias and variance trade-off. Bias error due to overly simplistic assumptions in the learning algorithm, and high bias always causes underfitting. Variance is error due to excessive complexity in the learning algorithm. High variance causes overfitting. Clear? So low bias, high variance, again, it is failing to be a good fit. This refers to overfitting. High bias, low variance, it leads to underfitting. And optimal trade-off, finding a balance between the model performance on both training and test data. So this is what we are actually trying to achieve in the output, right? So just to understand things, you have to understand the machine learning model from the mathematical intuitive behind it. If it is possible to understand it graphically, well and good, because in higher complexity, higher dimensional plane, it becomes difficult to access, to understand it visually. But mathematical intuition, the concept, and how do I interpret the results? Are you understanding? And of course, how we are implementing those functions in Python. That is where, your concentration should be. Mathematical concept, or what is the concept of that particular algorithm? How are we implementing in Python? And how am I interpreting the results? That should be the option. Clear? Is this point getting clear to everybody? And how do I check the error? The checking of the error is going to be through the training and testing error. So if you just look at this, I'll tell you what these errors are. So if you just look at the training, error is more than the testing error. So is it underfitting or overfitting? Definitely underfitting. Consider increasing model complexity. That means linear regression or a straight line fit is not a good fit on this particular data set. Agreed? So now getting back to the concepts of errors, how do I evaluate my regression model? Okay. Till here, are we clear? Okay. So one of the simplest error is known as the mean square error. This is nothing but your RSS, the residual sum of square error. Please try to understand. This is nothing. So errors, do you think one error is easy to define linear regression? No, right? There would be several errors. So now let's try to understand different errors available in the linear regression model. Yeah. So if I talk about the mean square error, this is nothing but my RSS, or the residual actual minus predicted value, the whole square. So error, square of the error, and if I take the average of it, it becomes mean square error. Agreed? Are you understanding this error? And when I talk about root mean square error, that is when I take the under root, square root of this particular MSC. But what is the need of taking the root mean? Can anybody tell me? What is the need of taking the root of this mean square error? Anybody who can explain? This is exactly the same, question which relates to standard deviation and variance. Anybody who understands the relationship between standard deviation and variance? Anybody who understands the relationship? After square error will increase, so square root will get proper value. No, Nanda, that's wrong answer. Yes, ma'am, rooting variance is standard deviation. Like, but why do we take that under root? That's the question. Why do we take this under root of variance? What is why? What is the significance? No, it doesn't mean that squaring will get a proper value. No, no, square root will. Yeah, because ultimately we have to compare with other values such as average. So average is a simple value. Simple values are cannot be compared with a squared value. Mean square value cannot be used for comparison with other values. So to make it at, it's something like, can I compare a centimeter square, the unit of area that is equal to centimeter square, with centimeter? Can I compare a centimeter square or a meter square, a unit of area, with normal meter? No, that goes mathematically wrong. So just by taking the square root of MSC, now it becomes at the same level, and then the comparison can be done. Yes, and if we talk about mean absolute error, that is actual minus the predicted value, and this is I divided by n, I get the mean absolute error. Clear? Now, these are all, we can say absolute terms of error. And if I want to do comparison between different models, now what difference does it make if I'm saying actual minus the predicted, the whole square, and then I say predicted minus actual, the whole square? Is there any difference between that? Is there any difference? No. So mathematically, whatever way they write, the answer will be same. Yeah. Clear now? Now let's understand another factor of comparison, that is R square. Please try to understand R square. Okay. Okay. Now to understand R square, it is a relationship between SSTO. What is this? Total sum of square. These are my actual points. And total sum of square is the difference or the total variation between the actual points and the average. Generally, we want to always find out how far my points are from the average, right? How my points are far from the average, right? So SSTO is getting clear to everybody. So over here, this is my actual data point, and here I'm doing my comparison. Is the total sum of square clear to everybody? What is SSC? Is SSC same as the RSS? Yes. Here we are trying to find out the difference between actual value and its difference with the average. Yi minus y cap b square. Again y square, because I don't want no positive and negative values cancelling each other. Clear? And if I talk about SSC, or the error sum of square, this is like RSS, actual minus the predicted value. This is my actual, this is the predicted value. Do you see this? So the uncertainty of the data around Y observations lie around the regression line. If SSC, all observations fall on regression line, larger the SSC, the greater is variation of the Y observation around the regression line. Then we have regression sum of the squares, right? This is actual, the average predicted value with the difference with the average. So the difference between the predicted or the fitted value on the regression line and the mean of the fitted value, that is equal to SSR, the measure of variability of Y's associated with the regression line. Larger the SSR in the relation to SSTO, greater the effect, right? So if we look at now the whole picture, that my total sum of the square is equal to SSC plus SSR. That is the difference, the sum of square values with the actual value minus the average, the whole square, is equal to actual minus the predicted, the whole square, and predicted minus the average. Agreed, learners? But what is the use of all these? So now there is this another factor, another unit which helps in comparison of value, that is R square. That is known as coefficient of determination. That is known as coefficient of determination, which is also known as the R square statistics, proportion of variance explained. The value varies between 0 and 1 and independent of the scale y, right? So R square is equal to SSTO minus SSE upon SSTO, SSR upon SSTO. So what is the advantage in short? Let's not get into the mathematics. That the R square value will always lie between 0 to 1. So the values which are more close to 1 are better fit as compared to 0. Yeah, mean square error and RMSE relationship is clear, but they are not relative errors. I cannot do comparison between the different models, that this model is better than the other. They are good to tell the errors are less or more comparison between training, but R square is a relative error. Even absolute error is not a relative error. What do I mean by that? What do I mean by that? Let me explain you with an example. For example, you scored 70 marks and I have scored 30 marks. Who scored better? You would say 70 marks, ma'am. You scored better than me. But I scored 30 out of 30. You scored 70 out of 200. Getting my point? So there, how will I find the relative? If I start taking percentage of this, that 30 out of 30 is 100% and 70 out of 200 is somewhere around 40-50%. Then I can do comparisons. Got my point? That is why we are now heading towards ratio between the SSTO, the total sum of squares, with RSS and SSR, taking into all account all the variability of the data points, and that's why I now reach on this R square term. Now better? Is it better? Sum of square error ranges between 0 to 1, which measures the amount of variability that is left unexplained after performing the regression. And SSTO minus SSE measures the amount of variability that is explained or removed after performing the regression. R square and the proportion of variability in Y can be explained using X. So R square is trying to take into account all the errors and variability of the data point. So when R square is equal to 1, SSE is 0, that means it's a perfect fit. It's an ideal situation. Will it ever happen? Hardly. I don't think so. It's going to be, but something which is close to 1.99 is a good. And when I get this horizontal line that you all were getting, that means R square is equal to 0. Error is equal to total. That means there is no linear relationship between X and Y. Now clear? Right? But R square suffers from one limitation, right? Since R square is also known as if it is greater than 1, it can never be greater than 1. That's Simon, that's not possible mathematics. Percentage ever come beyond 100%? The formula is such, now because we're taking a ratio out of 100, right, Simon? So mathematically, it can never be true. Got it? Okay. So R square, also known as the coefficient of determination, measures the proportion of the variation in your dependent variable X and explained by your independent variable X for the linear regression model. But the problem that R square also suffers is that it will always remain or increase as we are adding more number of independent variables. So this problem is solved by adjusted R square. What is adjusted R square? That it measures the proportion of the variation, explain only those independent variables that really help. So what do? We divide the error by degree of freedom. Do you understand the term degree of freedom, learners? Might be thinking so many concepts. Degree of freedom is the number of independent variables, right? Suppose if they are 10, if they are 10 input features, then the degree of freedom is n minus 1, that is 9. Clear? How many input features are we depending on, Abhinetri? That is referring to my degree of freedom. It's something like, now let's understand it over here. Now, if I want to predict the price of the car, what are the factors that are determining the price of the car? Safety is a very, very important factor. How many airbags does it have? Does it have a parking sensor or not? The branding. What is the most important factor? The mile, the fuelage consumption, the fuel type in today's world, assistant, infotainment system. Is it a luxury car or not? The color, the kind of, the design, the seats, the wheel, the alloy. There could be several factors. Agreed, learners? But do you think the kind of wheels or the wheel alloys are as important as the engine of the car or the model of the car to determine the price? No, right? So that is what is taken care by adjusted R square, and when we divide it by the number of degree of freedom. Getting my point? See, normally what will happen is if I keep on adding the factors in R square, that I've added the number of alloys, the number of, the seat covers, the color of the car, the R square will keep on improving. It will give me an illusion, oh, my model is giving so much well answers, but that's not true. Maybe, adding the kind of wheel alloy is not that concrete factor to determine the price of the car. See, these numbers of degree of freedom, as I told you, this is some example that they are taken. Degree of freedom depends on the number of input features. So that is why adjusted R square is a better way of determining the results. So if I get back to the file over here, and now look at how I calculate the results. So what am I trying to do? From Scikit-learn metrics, import mean square error, R square error, and then I do the prediction. Prediction is done by the predict function for the training output as well as for the testing output. And then the different metrics can be simply calculated in Python by using the mean square error for training data, for testing data, and R square. And then I can do the comparisons. So if do you see the training error is 0.573 and testing error is more than that, that's more closer. So they all refer that the model is underfitting. Now clear? How are we trying to fit the model? How are we trying to fit it, then predict the output, and then calculate the error? So if we talk about linear regression, let's look at it again. That this is my actual output, right? And if I talk about a single variable as my input, and there are two coefficients, beta naught and beta 1, this is the epsilon error. Is this first equation getting clear to everybody? Simple linear regression, single variable is getting clear to everybody. Then we have linear regression, multiple variables, right? We have x1, x2, x3, right? Epsilon over here refers to the random error. And if we talk about a model evaluation, are we clear with these metrics now? The mean absolute error, the mean square error, and the root mean square error, right? So comparisons between the different models is not possible. Therefore, we have R square error, which talks about the ratio, And even better than R square is adjusted R square because it is not affected by the number of inputs in the data. Clear? So basically, we divided by degree of freedom mean model. Clear? And we have also understood different scikit-learn objects. Please try to understand fit function. Fit function helps us to train the input parameters or train the parameters for the data. Transform is transforming the input to output. Fit underscore transform is mixing the function of fit as well as transform. And it is the predict function which is used to predict the output of the training data or of the testing data. To understand it better, types of sklearn objects are based on transformers. Transformers are nothing which transform the data set. Have you learned feature engineering, learners? Do you understand feature engineering? Where we do feature scaling, standardization and normalization, encoding of the data, that we need to transform the data before we actually fit into the model. Let me try explaining you over here. So before the data is actually fed into the model, it needs to be transformed. Why it needs to be transformed? Because if they are missing values that will not fit into the model, if they are categorical features, then we have to involve encoding. Feature scaling is a feature which brings the data into one particular range, and outlier detection. That is why data science is important, because these concepts are covered in detail. How do you deal with data? How do you handle missing values? How do you deal with categorical data? Scaling of the data is all part of the feature engineering process. So in feature engineering, we are not just building models, but we are playing matchmakers for data as well as algorithms. Getting my point, everybody? Okay. So getting back for transforming the data set, right? So fit learns. What does a fit function do? It is an estimator. Please try to understand. Fit is an estimator which estimates the model parameter based on the training data and hyperparameters. And finally, we have the predictors. That is, it predicts the data, makes the data set as input and does the prediction. Score method to measure the quality of the predictions. Getting my point? So here we have the data pre-processing, training, and inference model. Clear? And then we have fit and fit underscore transform, right? What do we do that? When we are trying to train the data, what I'm trying to explain, let me explain it with a slide. That, again, please try to understand. Let me rewind things. In supervised learning, we have label data. First of all, what is label data? That we have the input as well as the output. Now, in the story, have you understood two types of output in supervised learning? That we will have the actual output of the label data, and one we will predict the data using the X test. This point is getting clear? What this point, which I'm trying to explain regarding the output, is getting clear, right? So this is output actual as well as predicted. Now we also understand that we divide the training and the testing data, right? So ultimately we are trying to, when we are doing training, it is all on the training data by the fit parameter. So the model, all the training will be done using the fit function in simple terms, right? And the testing and output will be on the predicted. But if I want to transform the data, so I will fit it and then transform it. And can I do the function of fit and transform together? Yes, by using fit underscore transform function. Getting my point? Can I do the function together? Yes, for only training data, I can use fit underscore transform, and for testing data, I will only use the transform function. Now clear? Okay. Okay, so now let's, once we have understood, now let's get back to the code. So now, are we able to also understand how when the model is underfitting and overfitting, that point is also clear? Yes. And if we talk about non-linear regression, polynomial regression is a subset of linear regression that includes polynomial terms. The relationship between the independent variable x and dependent variable y is modeled as an nth degree. So here we are not trying to do it as a straight line, but polynomial regression, which is a subset of linear regression, which includes polynomial terms. The relationship between an independent variable x and dependent variable y is modeled as nth degree polynomial. Right? So why polynomial regression is called a special case of multiple linear regression? Some polynomial terms are added to multiple linear regression equation to convert it into polynomial regression. So it is a linear model with some modifications made to increase its accuracy. The data set used in polynomial regression for training is non-linear. So what do we observe? That in this particular graph, this is a straight line, linear regression. And if I change it to a curve, it becomes polynomial linear equation. Do we see that exponential curve over here? Okay. So I have this, simple data, right? In this simple data, this is the project statement, okay? Wait, live. Okay. Yeah, so a certain spare part manufactured company once a month in lots which vary in sizes. Data on lot and size numbers and man hours. That means the input is the lot size of the people and how many man hours are required, right? It's numerical, right? So if I start analyzing the data, actually, it's done through an Excel. It's simple that I do x minus x bar, y minus y bar, and I calculate this. What is this known as? RSS, residual sum of square, actual minus the output the whole square, xi minus xi the whole square. Do you see this? And why am I taking the square value? Because I simply take the difference between y minus y cap. The error is 0, which is actually not. Therefore, we take the square values and I get the answer as 13,660. Okay. So the sample size, the number of rows in this data set is 10. Degree of freedom over here is 9. Mean is equal to x bar sigma xi upon n 50. Variance over here is this much. Standard deviation is in this much. So this is where statistics is coming into picture. We have calculated the value. Similarly, we can calculate it for the man hours yi. Okay. And if I try to see the relationship, it's coming out to be straight line, right? Now coming on to the concept of how do we calculate the best fit line, right? So this is the least square concept where we are trying to find out the RSS. So over here, what am I trying to do? Again, yi minus the y cap the whole square, not this one. Okay. Here it is doing hit and trial method, but ultimately the least square estimators can be found out by trial and error method, but that is not the case. We try to calculate it by the normal equation. This is the equation for calculating of beta naught and beta 1. So these are already predefined formulas which run at the back end when I run the linear regression function. So this example shows that whatever values you are getting by solving mathematically or through linear regression model, I get the same values. Okay. So what does polynomial regression on dataset work? Again, we are using the tvmarketing.csv features. From the sklearn pre-processing, we are including the polynomial features. Again, first we are splitting the data. So now I am creating an object of polynomial features, right, with degree equal to 2. And now I am using the fit underscore transform function, not the fit function itself, but the transform function, because I'm transforming the input values as well as fitting, but I'm only and only transforming the output. Do I want to train the testing data? No. Why don't I want to train the testing data? Because, so if I give you what is going to be, if in your test, if I tell you the questions, is it actually a test? No, that calls for paper leakage. If I tell you what questions are going to come for an exam, that is known as paper leakage. And the same concept is known as data leakage over here. Getting my point, learners? So are you understanding the difference between fit, transform, and transform? The fit underscore transform will only and only work for training data. Transformation will happen for input as well as output. Will happen for training as well as testing. But fit will only happen for training data. When I create an object of linear regression, I get this output. So basically, the polynomial features transformer is configured to generate polynomial features up to 4th degree. Then we are only transforming the input to generate a new feature set that includes polynomial features and interaction. Then we transform the test data, corrected from fit underscore transform. It is used on x underscore test to apply the same transformation, and then train the model. The linear regression model is trained using the transform training data. Clear? And finally, we are going to predict the output and then create a graph, right? Do you see the scatter plot is testing data and plot is X range polynomial predict the output. Now clear? You are getting all the code, how the graph is getting created. So what is the observation? And this is exactly, why Jupyter notebooks are hit in the market, because we are able to see the graphs over here directly, which VS Code lacks, right? We can see the code as well as I can write my observations also. So as you can see, the regression line is able to fit majority of the data points. You can infer from the above implementation that nonlinear inputs require nonlinear model such as polynomial model. Clear? So, I mean, linear regression also has capability of dealing with nonlinear data up to degree 4, but not very high nonlinear data, right? Then we have different variations of the algorithm. And if we talk about performance metrics for analysis, why different metrics? Because it calculates the average of the squares of error, which is differences between the actual and the predicted. Then we have the root mean square error. Oh, I hope you all are clear. Mean absolute error, R square error. Zero value indicates model explains none of the variance in the dependent variable. The independent variables have no exploratory power for the changes in Y, and 1 represents a perfect fit. The model explains all of the variance in the dependent variable. The change in Y are perfectly captured by the changes in the X. Clear? So now we have to start understanding another technique, important technique. Okay. So now let's understand what is cross-validation. And before we understand cross-validation, we need to understand few more concepts. Now in machine learning, there are two terms that you need to understand. One is parameters and other one are hyperparameters. Okay. So now what is the difference between parameter? A lot of learners get confused because they both think they are the same thing. No. Again, I'm telling you, I try to give you exactly, the crisp concepts, differences between them. So when I talk about parameters, they are values learned by the model during the training. So during the training, what the model learns is referred to as parameters, and hyperparameters are defined by the user to control the learning process. Purpose over here is it directly impacts the model predictions. So model automatically learns the parameters, and that is directly impacted in the output. Whereas hyperparameters are controlled by us. For example, how much is going to be the training data and the test data is a hyperparameter, test underscore size of train underscore split, right? The factors or parameters which are controlled by us during the training process or model fitting process, that are known as hyperparameters. Whereas when the model learns the parameters on its own using the fit function are parameters. Clear? They are estimated during model training. They are generally estimated before the training begins. Learn from the data using optimization, whereas the hyperparameters are set. They are usually set or tuned using the methods like grid search, random search, or Bayesian optimization. Influence on the model affects the output directly, affects the speed and the quality of the learning. And this is dependent on the data set. These are independent of the data set. So the model parameters are nothing but your coefficients, beta naught, beta 1, beta 2, or they can also be represented by weights in general. So generally coefficients become weights. That's the general term used in deep learning. Whereas the test underscore size, the number of iterations, and there are several other factors that will be controlled by us. Even random underscore state are all hyperparameters. Is the difference getting clear? Right? So now, what is the need of cross-validation? Do we cross-validate results? Do we like to cross-validate views, reviews of doctors, lawyers? What does that mean, Abhinetri? And why do we want to do that? What does it mean and why do we want to do that? So that we are more sure of the answer, right? If one of the doctors is saying that you need to be maybe your disease has this and maybe you need to get operated, and even the other doctor says, that means you're more correct that yes. Or if the other doctor says no, doesn't need to get operated, you can cure it through these medicines, right? So cross-validation, or also known as rotation estimation or out-of-sample testing, refers to the process of rotating or splitting the data into different subsets. So it helps in the process of rotating, splitting the data into different subsets. Okay. So one part we are very, very clear that when we take the data set, we divide it into training and test. And definitely we don't want to mix any of their training and testing data sets to avoid any kind of data leakage. That point is also clear, that we want to avoid any kind of data leakage. That point also makes it clear. Now, to make our results better, more confident, more accurate, rather than using only one part of the set, if I use only one part or one sample of the set, if I use multiple samples, I can get better results, right? So this is my mini training data set. So it's always the training data set which gets divided into further training and validation split, right? So what is the idea? That we initially the data is getting split into training set and test set. Train and tune your models using cross-validation. So we will try to find out, okay, we want to make certain changes. This is better, not better, only through the training set. The test set is not involved. Test set will, we do not touch this until the very end because ultimately that is going to give us whether the model is robust or not. Is this point clear now? So how do we go about cross-validation? So model evaluation is this when we fit the model and then we predict the test set. That point is clear that we have one data set that is divided into training and test set, right? This point, this is normally that we do. We fit it and then we predict the output and do the comparison. But if I want to do model selection between different comparisons, what I will do now, the training data set is going to get divided into train as well as validation data set. What is the use of this model selection? It helps us to explore the hyperparameters grid. Now they are different hyperparameters. How do I know that this is the best hyperparameter for me? I will try to do it through the validation set. Fit on the train, evaluate on the validation, pick the best hyperparameter. Clear? Why are we doing this? Because we want to validate our training and results better. It helps us in finding out the different hyperparameters, right? So as we move along, more algorithms, you will understand it more. It's not part of regression, but part of supervised learning also. So cross-validation, when data set is too small for apply hold out strategy, then cross-validation can be used for evaluation and model selection. So what do we do? Suppose this is my 100 rows in data set, okay? And now I divided into 20 groups. So I have 5 groups, 1, 2, 3, 4, 5. So one of the part is going to be used for validation, other is going to be used for training. Then the next group is going to be used for validation next. So I will iterate it for 5 iteration. Got it? Of course, it is increasing the complexity, but it is giving me a much more validated result. Agreed? So one of the techniques or variants of k-fold is leave. This is known as leave one out cross validation, right? So we have 1, 2, 3 and n over here, right? So if we take one part of the sample and the rest n are taken for training, then the next row is taken, the rest for training. So how many times the loop will be executed? N times. Is it a good idea? No. Taking each sample for for validation and others for training is not a good idea because it will increase the number of computation. But if I have k-fold, that is, I divided into number of groups, my number of iterations decrease and I get better results. So how do we go about the performance and the output metrics, right? So what will happen? So the cross validation will automatically create an array. In the first iteration, I will get the first metric. When it takes the second k-fold, I get the second performance metric. When I take the third iteration, I get the third performance metrics. The fourth one, and last one, I get the fifth performance metrics. Clear? So to answer that point, everybody please understand the test data is not touched. It is the training data and the different folds which I use, and final evaluation is done on the test data, whether I am getting the correct output. So the concept is same. We are doing comparison between training and testing, and that will give me the results, whether it's overfitting, underfitting, etc. Clear? Yeah. But when we talk about categorical data, what does categorical data means? That the data is in category in terms of males and female. So the fold we have, which have been cross-validated, will be taken up for final testing. Final testing will be on the test data only. Once the parameters have been found out, okay, the number of folds, okay, the number of, uh, K value for this thing is this. So now we will test on this value. Are we getting the minimum results or not? It will help us to calculate the different hyperparameters. Got it? Okay, so when we talk about categorical data, dividing it into male and female. So this is my round one. So stratified k-fold is being used for categorical class, which helps us to keep the ratio of the different categories same. Okay, this we will do it when we do classification. Okay. So what is the difference between k-fold and stratified k-fold? K-fold is random. Stratified k-fold helps us to maintain proportions, may vary across folds, maintains class distribution across folds, imbalanced data set, not ideal, preferred use cases, balance and imbalance. And how do I check the metric that my cross validation is good or wrong? First, my parameters for cross validations are the estimators, input, output, scoring, and CV equal to 5. Estimator is equal to the model object. X is an array of the feature values. Y is an array of the target value. CV, the number of folds. Scoring, the metric, and it returns score, an array of scores at each split. So, the beauty of this particular function is that it returns at, score of each iteration. So, you are able to see which one is better, but generally we take the average of that. Clear? So now let's get back to the file and do it practically. So this file is quite long. We will be using this file in the next session. Of course, we will not be able to complete all the concepts today. So we are on cross validation. After cross validation, then we have regularization. After regularization, then we have hyperparameter tuning, that is model optimization, and then the pipeline. So it's a long journey that definitely we are going to continue. Okay. In this way. Yeah. So cross validation technique. Everybody is there with me? 3.7.2. So what have you understood? What is cross validation technique? Tell me, learners. So cross validation is a machine learning technique that evaluates the model performance on unseen data by dividing the data into multiple folds. In each iteration, one fold is used as a validation set and the remaining as training. That point is clear? Then the process is repeated. So we have to give the number of iterations also. Yes, is repeated so that each fold serves as a validation set once, and the results from all iterations are averaged to provide a robust estimate of the model performance. Some of the common cross-validation techniques is K-fold cross-validation. K refers to the number of equally sized folds. That if it is unequal, it will make it equal by adding randomly some of the, randomly the data set only for the last one, right? And there is no harm also in doing it. Will not affect it much. So the model is trained on K minus 1 folds and tested on the remaining fold. That point is clear? So if I have 5 folds, then one of the fold will become the valid for validation test and 4 will be tested. This process is repeated k times. So is this k also a hyperparameter? Yes. We decide they are going to be 5-fold, 6-fold, 7-fold, 8 folds, not the system. They are not parameters to the algorithm. It is decided by us, so it's a hyperparameter. And with each fold exactly once as the test data set. The results are averaged to produce a single performance estimate. We generally average them. What is the advantage of K-fold cross-validation? It provides more accurate estimate of the model performance. Yes, that this is the answer. K is the number of folds. Yes, Ajay. And cons, computationally intensive for large data set. Yes, you have to reiterate the training process, but it gives definitely better results. Clear? Then we have stratified K-fold. Similar to K-fold, but ensures that each fold has the same proportion of different classes as the original data set. This is especially useful for imbalanced data set. More reliable performance estimates for imbalanced data set, and still computationally expensive. Third is the holdout method, simple and fast. One, we divide the data into training and test, and the training data is further divided into training and validation data set. So the model is trained on training set and evaluated on the test set. It is simple and fast. The evaluation may be noisy and variability in the training. So the normal one that we do, we divide it into training and test, is known as the holdout method. And leave one out cross validation is again a special kind of cross validation technique used in K-fold. A special case of K-fold cross validation where K is equal number to the number of data points in the data set. Each observation is used once as a test set. The model is trained on remaining data points. Clear? So this maximizes the amount of training data used. Cons, extremely computationally expensive, especially for the large data set. Clear? 4 variants of cross-validation techniques. K-fold, stratified, hold out, and leave one out cross-validation. Okay. Now can we begin with the code? So I hope everybody is familiar with the Pandas and the Matplotlib library. We are also familiar with the Scikit-learn model selection. These are the different techniques and metrics. Linear regression over here, and this metrics to compare mean square error, absolute, R-square, etc. Clear? So here we are talking about housing.csv. So, yeah, take it as housing. So what are the pre-processing steps? What are the steps involved in EDA? Tell me. How do you perform EDA? You'll do head, tail to view the data, check null values, do info, right? So let's look at info. So if you look at info, it has around 20,640 rows and 8 columns. Do you see this? All are integer values. Do you see this? Yeah. Now the question is, can you tell me what is the output over here? Why it is a regression problem? What are we trying to do in this data set? Can you analyze it through the number of columns? Based on the latitude, longitude, housing, age, total rooms, bedrooms, they all are inputs. I am trying to predict the house value. What will be the value or the price of the house? House price prediction. Now clear? All these are my inputs and one output. House values are numerical continuous value. Therefore, this is known as regression. Clear? Okay, now let's see the observation that price lies between 1.1 million to 2.6 million. Houses are generally 18 to 37 years old. Housing data. Let's check the null values. Yeah, now let's check the null values. So total number of bedrooms, we have 207 values. How do we deal with null values? Either we will replace it by mean, median, or zero. Since null values make up only 1% of the total data, rows and column features with missing values will be removed. So what are we trying to do? We are going to drop now because 207 is hardly 1% of 20,000 rows. So we can drop those data and now my data set is clean, right? And this is the categorical data which we are not using. We don't have that. And now can you tell me what does this mean, X and Y? Now I have dropped the median house value, axis 1, because that's my output. And now this becomes my output. This becomes my input, right? So if I say print X and then print Y, do you see? Yeah. So now do you see this? So X basically has longitude, latitude, house, median, total bedrooms, etc. And Y is only that. So let's remove Y. Clear? So I keep making changes in the code. Are you understanding? So these are my now the input. And my output is median house value. And then I use the train test underscore split. Clear? Okay. Now let's perform k-fold cross-validation. It implements k-fold, number of splits is 10, divides the data set into 10 folds automatically, random underscore state is 42, shuffle is also equal to. So I have created an object of this k-fold. Now I initialize the model. There with me? And then I evaluate the cross-validation score based on the model. Model was linear regression, training data, and the target variable. Scoring, I'm using negative mean absolute error as the performance metric. So this is where the absolute error comes into the picture. CV cross-validation is KF. Number of jobs is equal to -1. What does this mean? It utilizes all the available processors for parallel computation. Do we understand the concept of threading or the number of core processors, learners? So this parameter takes care of that. Okay. This parameter takes care of that particular one. Clear? So from statistics, import mean. I'll take the mean of the k-fold cross-validation. K-fold scores are not defined. So let me run this. Let me, show you that since the number of folds is 10, so the output of k-fold crow is an array object. See, do you see? They all are mean negative absolute errors. Negative does not mean that the error is less. It's just the sign. Okay. So we will try to take the average of these, right? There will be 10 outputs since we have given 10 folds. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Clear? It's an array. And then I will try to take the absolute average of this. Clear? So we have trained the model and evaluate on the test set. So are we now understanding how are we going about cross-validation score, learners? And now finally, after cross-validation, now we can use the test data. So this is how I have fitted the data, predicted it through the test, and my MSE, test MSE is here. Similarly, my R square is here, right? So my test MSE and R square scores are here, right? Look at the error, it's so huge, indicating that on average, the squared prediction errors are large. This can be interpreted in context of units of dependent variable, which are likely in order. Since the numbers are very high, that is why the errors is coming out to be large. This can be mitigated by scaling the features. Feature scaling is critical in machine learning to ensure that all features contribute equally. So this is how, and then we demonstrate leave one out also. LOCCV scores, and we get the absolute mean score. Clear? So the mean absolute error is high. To improve the model, more complex model can be considered, which will be discussed in further lessons. So the concept of cross-validation is clear. Let's do a quick knowledge check on that. Okay, a quick knowledge check. First question. Which of the following cross-validation versions may not be suitable for very large data set with hundreds of samples? We just now studied that. I think so we've all seen it practically. Practical has a major impact. We all have just now seen the impact, and it is leave one out cross-validation. Great. Which of the following is a disadvantage of k-fold cross-validation method? Training algorithm has to return from scratch. Do we understand this? Every time it has to restart and do it again. Next question. Suppose you have picked the parameter for model using 10-fold cross-validation. Which of the following is the best way to pick a final model to use and estimate its error? Train a new model on the full data set. Using the parameter you found, use the average cross-validation error as its error estimate. So you can use average cross-validation error as its error. Everybody got this? Why C is not correct? Because we will train the model on the full data set. Okay? So what is the idea? The best way to pick, why is the answer B correct? The best way to pick a final model is to train a new machine learning model on the full data set using the parameter learned to use the average cross-validation error as its error estimate. So please be clear with this particular point. That is why I have added this MCQ. We can compare different models using cross-validation. Cross-validation is mainly used for comparison of different models. For each model, you may get average generalization error on the k-validation sets. Then you will be able to choose the model with the lowest average. Clear? And cross-validation is also used for model checking, not model building, because it allows to repeatedly train and test on a single set of data set. Let us suppose we have a linear regression model and a neural network. To select the best one among these, we can use k-fold cross-validation. So to compare between the models also, we can use cross-validation to select a better performing model. Clear? So when we are now looking at the regression outputs, right, or the regression analysis, some of the outputs are like this. So the output over here that we receive is in these terms of coefficients, that this is my beta naught, this is my beta 1, beta 2, and this is my beta 3. So this is my north, south, east, and constant term. And these are the values, right? So what is it showing? This is the constant value positive. East has positive relationship, but south has more positive relationship with the heat flux. Heat flux is the output, and north has a negative relationship with the output. Are you now understanding it better? How do we get the output and how are we relating it with the the equation of linear regression? So this is nothing but like beta naught plus beta 1 x1, the value of east, plus beta 2 x2 minus. So a lot of you had questioned that how do we understand negative? It will automatically get this. So this is multiple linear regression. Yes, learners. This is multiple linear regression. And there was a lot of confusion regarding, ma'am, what does multi-collinearity mean? Multi means referring to multiple independent variables, multiple inputs with multiple regression. Call means joint or together, referencing to the linear movement or correlation. As I told you, it tries to find out correlation in terms of -1, +1 occurring within the linear equation. And suffix means the idea. So if we look at over here, from statistics, we understand that p-value is a very, very important term, right? That if I have the value lesser than 0.5, then this is accepted. This is accepted. This has a strong evidence, statistically significant. But if this is not lesser than 0.05, that means east is 2.12 is not very statistically proven or confident that the value is this. Clear? And when I talk about VIF, how do I calculate multi-collinearity? It is the variance inflation factor, which is coming out to be 1.21. What does that mean? This is the correlation map, a heat map that you understand. So multicollinearity is the phenomenon of high correlation between the predictor variables can create instability and bias in regression model. To identify and address multicollinearity, we use the variance inflation factor. So the VIF is equal to 1 minus 1 upon R square. And if the value is equal to 1, that means all the input values are independent. And if it lies between 1 to 5, it suggests moderate correlation. So over here, we are getting the value between 1 to 5. So there is moderate correlation, or we can say independent also. And if it is greater than 5, then it indicates high correlation. That means then linear regression cannot be can be fitted on that input values. So where VIF should not be used, polynomial equation, dummy variable, or a normal variable. And multicollinearity reduces the statistical significance of the independent variables. VIF is used to detect these variables. A large variance inflation factor on an independent variable indicates a highly collinear linear relationship to other variables that should be considered or adjusted for structure. Because multicollinearity is one of the assumptions that we assume when we are trying to build the linear regression model. So that means if the VIF value is greater than 5, then linear regression should not be used. Clear? I hope these points are clear now. First concept that we will learn, data leakage in machine learning. So now we will understand the concepts of pipeline today. Pipeline is a technique for automating different processes. What is the different processes that we do? Whenever the data is loaded, we want to do transformations such as encoding, scaling, right? So we'll try creating a pipeline. And what is our main aim? That we want to avoid data leakage, of course. Why? Because if there is data leakage, the data gets lost. A lot of information is also getting lost. So now if we look at the data from the supervised learning perspective, it is divided into two parts. One is known as the training data and the other one is known as the test data. Agreed? Okay. So a scenario when the ML model already has information of a test data in the training data. Do you think that test data should be present in the training data? If I tell you, okay, in your exam, these questions are going to come, that's going to be very beneficial for you for scoring marks. But do you actually learn out of it? No, that's not a good way of learning, right? That, it can give you good results, but you're not going to be a robust model. That means if any other question is asked from that particular topic, you will absolutely fail, right? But this information would be available at the time of prediction called data leakage. So what is the disadvantage and how can we avoid it? That it causes high performance while training set, but performs poorly in the deployment or the production. Okay. So when there is an, or if I say when there is an overlap of training and test data, then it causes data leakage, right? And basically, data leakage happens due to two reasons. First, we understand train and test contamination or the target leakage. What do we mean by that? Target leakage occurs when the model is trained on the training data that contains target or the feature information. So we don't want that. And that should not be available at the time of prediction. So we have to be very, very careful when we are doing this. The other one is the train test contamination is an event where the test data leaks into the training data and the data pre-processing steps for transformation, for example, scaling, encoding, are applied before the splitting the data set. So contamination is when the test data leaks into training that and the pre-processing steps. So that the scaling, encoding should not be applied before the splitting of the data set to avoid data leakage. Got it? Basically, if there is mixing of training data in the test data set, or rather test data in the training data set, then this causes data leakage and we have to avoid it in every case. That is, we should not apply any transformation, that is scaling or encoding, before the splitting of the data set. Now clear? Now, another very important concept of regularization. There are two types of regularization available under regression, that is Ridge and Lasso. Preventing overlearning, yes. Normalizing the data, yes, we can say that. So regularizing thing in a normal way, right? We want to prevent it from overfitting, overlearning, right? So regularization is a technique in machine learning which prevents overfitting of the model. And how do I know that the model has overfitted? How do I know that the model has overfitted? Test error much higher than the training. The training error, and why is it that model is trained so complex than requires high variance? It covers every possible train outcome, making it complex. Yeah, so the complexity of the model increase. It tries to train on each and every data point and fails on the final test data due to noise, due to learning of noise in the training data. So to avoid it, so as I've been telling you, that in machine learning, do we suffer more from underfitting or overfitting? Overfitting, right? So we need methods so that our model does not overfit, and we need certain control parameters to achieve that. So there are two, algorithms under this, that is Ridge and Lasso. So Lasso is known as L1 regularization technique. Can anybody tell me what does this term mean? Anybody? It is summation of the actual value or the true output minus the predicted output, the whole square. What is this term known as? It's an error. I want the typical name of this error. It is the residual sum of square error. But rather than only taking this error, actual minus the predicted value, the whole square, I take into account the another hyperparameter lambda, which I will use to control or regulate the training process. So do we have a regulator? Do we have a regulator to control the speed of the fan? Similarly, lambda, we will use the regulator. And similarly, summation of beta. Can anybody tell me what is this beta over here? What does the term beta mean? It is the coefficients. It could be a single, it could be many multiple variables. So this is known as the regression coefficients, right? Not the intercept or slope. That is only in two-dimensional case, like beta naught plus beta 1 x1. I agree. Both of you are correct on those perspective. But in general, betas are known as regression coefficients or the weights parameter. So what is the advantage that we are getting through this L1 regularization? That in the error term, in the RSS term, now we have added the penalty lambda, which is controlled by us and which controls the value of these regression coefficients. Getting my point? And in regression, that is known as L2 regularization. So this is now also, known as my error, or it is also known as the cost function. Try to understand in deep learning, the error with which we are calculating becomes my cost function. In this case, it is represented as L over here. It represents it as my loss function. There is slight difference, but actually in machine learning, they all mean the same thing. Okay? So here we have the RSS W. Now what is this W over here? Is it the same as beta? Is it the same as beta? Yes. It's the regression coefficient. Is the lambda same? Yes. The lambda in Python is known as alpha. And then we have sum of the square of the weights. And what is this? Actual value, predicted value. Now are you understanding whether it's W or beta? They mean the same. And this is the lambda parameter with the square of the coefficients. Okay. So what are the advantages and disadvantages? And now then we will practically jump onto the file and start learning from there. So L1 regularization performs feature selection. What do we mean by features? Independent variables or the inputs? Yes, the inputs. So now we are trying to control. So now what is the use of overfitting? We understand that overfitting generally leads to high variance, agreed learners, and complex models. Agreed? Do we understand this concept, everybody? So to reduce the complexity, now I will try to control my coefficients, regression coefficients, beta naught, B1, and beta n, or in general, I can also call them as weights. Now getting my point. Do not get confused with the terminologies. Somewhere it would be written as weight, somewhere as beta, somewhere as independent variable, somewhere as features. So you should be able to understand the concept of it. Clear? So the beauty of L1 regularization is that it performs feature selection by shrinking the less important features weights to 0. So if I have a multivariable data set from beta 1 to beta naught to beta 7, it will shrink few of the features. That means some of the features or the weights will become 0. That means they have no significance relationship with the output. For example, if we want to, just try to listen and absorb as much as you can. That suppose, we want to predict the price of the car. Okay. So there are several factors from fuel to design to color of the car to the alloy of the wheels to the security systems to the infotainment system to the sunroof. There can be several features, but maybe the alloy of the car or the wheel of the car might not be important, so it can be reduced to 0. That will help us to reduce the complexity, and that will try to reduce the overfitting of the model. So very, very important concept. L1 is used to reduce or shrink the less important features weights to 0. So it helps us in feature selection, right? And it can also be used for high dimensional data set with many number of columns such as 20, 30, 50, 100 with many irrelevant features. And the disadvantage is it is not effective for data set with many important features. Now you might say, ma'am, how can we remove a feature? My every feature is important for the output. Then we use L2 regularization, okay? Where the value of the coefficients of the weights will not become 0. It provides a smooth solution and improves the generalization performance of the model. So, ma'am, Ridge is going to doing the opposite. Instead of 0, it is reducing the weight. Ridge is trying, or it is trying to see, the first one is making it 0, and the L2 will try to reduce the value. L1 is Lasso, and the ridge one is making the value of the coefficient small, not huge or big, but small. So therefore, the biggest advantage is that it can handle data sets with many important features. Okay, so now moving ahead to great Abhinedra. Now let's get back to the file. Everybody has the file. Everybody is ready in the Jupyter notebooks. Okay. So regularization in regression. In linear regression, regularization encompasses a set of techniques employed to address the issue of overfitting. So what is regularization? Regularization is the method, techniques to achieve the objective by introducing a penalty term. Please try to understand. Again, it's a very, very important question from the point of interview. Introducing penalty term lambda to model's objective function to prevent it from overfitting. This objective function, typically measured by mean square error, is minimized during the training process. So generally, the error of the mean square error, or the RSS to be precise, is minimized during the training process. What is the advantage of that penalty term or the lambda? The penalty term discourages the model from attaining excessive complexity by penalizing the size of the model coefficients. So, model coefficients, regression coefficients, beta naught, beta 1, beta 2, or the W1, W2, Wn, thereby mitigating the overfitting process. Got it, learners? All right. So now if we talk about the regularization term, alpha, it can be known as alpha as well as lambda. Okay. They all mean the same thing. It's written as lambda or sometimes as alpha. So do not get confused. Okay. So there is a little terminology mishap happening. So everyone uses their own technique, but try to grasp the concept. Okay. So alpha is the hyperparameter that scales the penalty term. It controls the strength of regularization. Higher the alpha, it imposes stronger penalty on the coefficients. That means they tend to become 0, leading to greater regularization. This tends to produce a simpler model that may underfit the training data, but often generalizes better to unseen data. If we talk about lower alpha, it imposes a weaker penalty, leading to a model that is less restricted by regularization and more complex, potentially capturing more details in the data, but at the risk of overfitting. So what are we looking at? We are definitely looking at a value which is not very high and very low. So again, minimum mid value to find out. Got it? How do we find it? What are the best methods? That we will understand today. That is known as hyperparameter tuning. That's part of this today's session also. Okay. Now, what are the benefits of regularization? It enhances the generalizability of the model. By mitigating the overfitting factor, regularization fosters model that can perform well on unseen data, reduce model complexity, it promotes interpretability, and potentially reduces computational cost associated with training complex models. And the two common regularization techniques are L1 and L2. L1 is Lasso. Lasso is the full form of least absolute shrinkage and selection operator, right? So absolute term is there as the penalty. So Simon, is there any standard to label it as high, alpha or low? Yeah, we'll understand. Of course, low is my zero values or negative values, and high values are in thousands and lakhs. Let's do it practically to understand that point better. Okay. So is the full form of Lasso clear to everybody? So which is the penalty term? Of course, it is the alpha or the the lambda. But what are we trying to add? The absolute value of the regression coefficient. So the least absolute shrinkage and selection operator regression relies upon the linear regression model, but additionally performs a so-called L1 regularization, which is a process of introducing additional information in order to prevent overfitting. As a consequence, we can fit a model containing all possible predictors. What are predictors? I'm purposely reading. You might feel ma'am just reads the data, but I'm purposely reading it to make you understand line by line. So what is containing all possible predictors? Predicted value is an output, predictors are input. So we can fit a model containing all possible predictors and use Lasso to perform a variable selection by using a technique that regularizes the coefficient. So what is that lambda parameter doing? It is having control on the value of the lambda or the alpha has where it's controlling or regulating the values of the coefficients. The regression coefficients. That's up to you how you want to represent it as betas or weights, right? So it performs variable selection or feature selection. It forces some of the coefficient estimates to be exactly equal to 0 with the help of large tuning parameter. So more the value of the lambda, some of the features coefficient value will turn out to be 0. And that is why this is a technique which is also used in dimensionality reduction. What is dimensionality reduction? Reducing the number of features in the data set so that it reduces the complexity. So L1 again plays a major role in that. It helps to reduce learning of more complex data and overfitting. It decreases the variance of the model without increase in the bias. All right. So in minimization, objective does not include RSS like the OLS regression, but also the absolute value term. So this RSS now is clear. This is the residual sum of square. And this is how we can expand it and write it. This point is also clear. What is yi? This is the actual output. And what is this output? This is the predicted output. Are you all understanding it mathematically, conceptually? But in Lasso, where does the difference come? The RSS is the same, but we have added the penalty term alpha or lambda along with the absolute value of the summation of the coefficients. Now clear? If the alpha is equal to 0, then there is no regularization that will happen because the error term will be same as the RSS. If it is equal to infinity, all the coefficients will become 0. And if the alpha is greater than 0, lesser than infinity, coefficients are between 0, that of least square linear regression. Got it? Is the theory part clear? Now let's move on to the practical part. Start with a new data set. So let me share it with you, hitters.csv. Okay, here we go. Please download this data set and be ready. I hope different libraries are also clear. The NumPy Pandas, then linear model Lasso, the metrics mean square error, R square. All these are there. Okay. So basically now let's understand the description of the data set. So I have provided a link over here. So this is for like we have like now IPL matches. So here we are trying to predict the salary of the player based on at bat, number of times he batted in 1986, hits, the number of hits, the number of home runs, the number of runs batted,
walks, number of times a bat during his career. So lots and lots of parameters to decide the salary of the player. That is 1987 annual salary on opening day in thousands of dollars. Got it? And then we have another important column, that is new league, a factor with A and N indicating the players' league at the beginning of 1997. So what is the first step? We've loaded the libraries, we load the data set and the view of the data set with df.head. Okay, what are the other functions that we would perform? Info. So this data set is quite huge in the sense that it has the number of rows are only 322, but the number of columns are many. So this is an object data type. At bat, everything is integer, but we have league, division as categorical data, and then we have salary over here as the output and new league. So what are the different steps that need to be performed? Can we directly apply the model onto this data set? So these are my columns. So I have used df.drop unnamed equal to 0. Encoding, if any. Do you think encoding is required? Encoding is definitely required for league division for all the columns which are of object data type. Please remember this point, learners. Encoding is definitely required for object data type. Without that, you will not load it into the model. Duplicate values, if they are, then we need to check that. Okay. We are removing unnamed column because that is not required. We are specifying the access. What does in place equal to true mean? Permanent removal of that column from the data set. So now if I see my first column gets removed, so the first processing that I have done. Now let me check the null value. Are there any null values over here? Only the null value is in the output, in the salary field, right? Which is my output field. Agreed, learners? Do I need to separate my X and Y also? Yes. So the number of missing value in salary is 59. So 59 out of 322 observation with null values correspond to columns salary. Since we will use the Lasso algorithm from the Scikit, we need to encode our categorical also. Okay. Now, how do we deal with categorical data? What is the use of value underscore counts function? It gives the category along with the frequency, along with the count, right? That's incomplete. It gives the category along with the count. So in league, there is A and N with these categories. In division, there is W and E, Western and Eastern. And again in new league, we have A and N, the American League or the National League. So if I separate this into a data frame, do you see this data frame rather? This code is getting clear to everybody. Are we here? Till here? Okay. So what are the different ways of encoding data? One is one-hot encoding, other one label encoding. What is the difference between the two? One-hot encoding adds column and then gives the binary output. If that column value is there, then it has 1, else all values are 0. Yes. And label and assign integers to each of the category. Yes. And label encoding is used when we have a ordinal data. One-hot encoding is used when we have nominal data. That means there is no order. So over here, we are using which function, learners? Yes, it is now one-hot encoding that now it will have, instead of 3, 6 columns with 0 and 1 value. Right? So do you see this? League A, League N, Division E. Do you see now? So wherever we have value of league, Get underscore dummies is one hot encoding and label encoder, that is the function. So is the output of dummies dot head is also clear? That now if these are the 6, the 3 categorical value can get converted into 6, and wherever the value was there, this is 1 or this is 0, and this is 1. Clear? Okay, so what are we doing? We have separated the output. X numerical value, we are dropping the output, the league, the division, and the new league because they all are categorical data, and everything gets converted into float type. So the numerical columns are now clear. The input X numerical and the output Y salary. Good, Chakrapani. Good. Now, do we need to concatenate these columns with the original data? So we'll just take one of them. Since it has binary category, please try to understand. Since all of them have binary category, therefore it can be used for league underscore N, division underscore W, and new league underscore N. Getting my point? So now you see all my inputs have become integer values, numerical values, and that is what is required before you feed any data into the model. Now, once my data is ready, now we go in for testing and splitting of my input and output. Test size is 25%, rest is training, and I get my 4 outputs, right? So Lasso, performs best when all the numerical features are centered around 0 and have variance in the same order. Homoscedasticity needs to be maintained. And if a feature has a variance that is orders of magnitude larger than others, it might dominate the objective function and make the estimator unable to learn from others. So it should not be that, one of the columns have very high values and the other one low. This means it is important to standardize our features. We do this by subtracting the mean from our observations and then dividing by standardization. What is this concept known as? Of feature engineering. Okay, I've given you one hint. This is the concept involved in feature scaling, and this refers to standardization, that is scaling the factors with mean equal to 0 and standard deviation equal to 1. Clear? To avoid data leakage, standardization of numerical features should always be performed after data splitting only for the training data. Please try to understand. To avoid data leakage, we will only and only use it after the splitting of the data. We saw that. So what is data leakage? We understood what is data leakage? That it occurs when the information from the outside, the training data set, is used to create the model. This can happen if the data would not be available at the time of prediction, is included in the training process. So data leakage can lead to optimistic performance estimates and models that fail to generalize well to new as well as unseen data. Clear? So, which is the Python function? Which is the Python function to perform standardization, standard scaler, which creates an instance of the object fit. Fit trains the X-train numerical data, that is training means, to find out the parameter to compute the mean and the standard deviation for each feature in X-train list underscore numerical. X underscore train is your for each data set, and the list numerical is the list of column names corresponding to the numerical features. Got it? What is the use of transform? It applies to the standardization of the training data, which transforms each feature in the training data set to have mean 0 and standard deviation 1, right? And then we only use the transform function on the test data. Now clear? Okay. Standard scalar is clear. It's the function to perform standardization. Standardization is one of the feature scaling technique where we take mean equal to 0 and standard deviation equal to 1, Anush. That point is getting clear. Fit is always performed on the training data, that is numerical data. Till here also this point is getting clear. That this refers to the list of numerical data. And transform, we are doing it on the trained data. That is how we are going to avoid data leakage. Now clear? Got it? But when we talk about, testing data, are we going to apply fit function on it? No. We are only going to transform it. So it applies the same standardization parameters, mean and standard deviation computed from the training data to test data. And this ensures that the test data is scaled in the same data as training. Now clear? Okay, right? So practically, how do we go about it? So we have imported the standard scalar from the Scikit-learn library, and then we perform this function. So the explanation is given above. Right? So what are we trying to do? We are fitting the standard scalar to numerical features so that there is no biasness in the data set. Now, you'll see positive, negative value because the sum of all these values should be 0. The mean of all them should be 0. Clear to everybody? So the training data has 241 rows and 19 columns. Clear? Similarly, test 1 will only have 81 rows because of the 25% data and 19 columns. Clear? Now they were missing values in the output data. How do we go about it? How do we go about it? Let's see. Yeah. So what are we doing over here? Yes. What are we doing? We are taking the training model as well, training data as well as the testing data and filling it with the median value. Wherever there is null value, it will fill it up with median. Not mode over here. Dr. Henry, we see it practically that it's getting filled with median. What is the difference between mean and median? Besides that, which one is affected by the outliers? Where do we use median? When we do not want to get affected by the outliers. So now let's move ahead and understand the Lasso model. So whenever we have to create, how do we begin with the hyperparameters? If I want to start any of the models, how do we begin with hyperparameters? We will randomly assign any value and then start training on it. And to find out the actual value, we do hyperparameter tuning. So we apply Lasso regression on the training set with regularization parameter that is alpha equal to 1. So we begin with a very simple value alpha equal to 1. This value is commonly used as default and provides a good balance between maintaining model complexity and reducing overfitting. Okay. So by default, whenever we have to do things, you can randomly assign any value to the hyperparameter. Alpha is equal to 1, maximum iteration is equal to 10,000. And now we are fitting the training data. And this is now my new intercept coefficients, the regression coefficients, beta naught, and the other coefficients. Because since they are how many parameters? Can you tell me how many parameters are there in this particular question? How many are there? 19, all the numerical values, right? So we would have 19 coefficients. And do you see after applying Lasso, some of them have become 0? This one, this one, this one, and this one. Getting my point? So if I see the output, these are my coefficients and some of my coefficients have become 0. Do you see? Then you might say, ma'am, what is -0? It just puts the sign. There is nothing, no term in mathematics as -0. Clear? So what do we conclude? This is the intercept term of your Lasso regression model. It represents the expected mean value of the independent variable when all the independent variables are set to 0. In practical terms, it is the baseline prediction when no other information from the variables is provided. So the Lasso coefficients represent the relationship between the variable. Positive coefficients. Now, what do we interpret out of it? Let's see that. A positive coefficient indicates that as independent variable increases, the dependent variable also increases. That's the positive relationship. A negative coefficient indicates that an independent variable increases, the dependent variable decreases. The magnitude of the coefficient shows the strength of the impact. Now clear? So the magnitude of the coefficient shows the strength of the impact. A larger absolute value indicates a stronger defect. Lasso regression is known for its ability to perform feature selection. So ultimately, the values have become 0. So now my 19 features have reduced to, so I have reduced these two. Then I have also reduced 2 above and 1 in the last. So 3 features get reduced. So 19 gets reduced to 16, right? When we have taken lambda equal to 1. All right? Right? But in this model, however, it seems that none of the coefficients are exactly 0, suggesting that all included variables have some impact on the models though some impacts are very, very small. So basically 4 features. Yeah, okay, 4 features. So now how do I evaluate it? I'll calculate my mean square error for the training data and then for the testing data. This code is also getting clear. That helps me to decide whether it's overfitting or underfitting. So now you tell me, is it an overfitting model or an underfitting model? Testing error is more than the training. So is it underfitting, overfitting? It's overfitting. And if I do the R square over here, so the value is very, very less. So to better understand the role of alpha, the regularization parameter. So what is alpha known as? The regularization parameter. Plot the Lasso coefficients as a function of alpha. Maximum iterate are the maximum number of iterations. So here we have np.linspace function. What does the np numpy linspace function do? That now the values of alpha will range between 1 to 5 and with 10 equidistance value. So now what are we trying to create? Linspace function, do we understand of NumPy? So now if I say now I will start understanding the range of the values from 0.01, right, to 500 and the value is still 100, right? So over here, these are the values or the array created of alpha. The maximum iterations are 10,000. And now I will try to run or fit on each of these alphas. And then look at this beautiful graph. Simon, specially for you. So the value of the alpha goes from 0.01 to 100 and 1000. And we see as the value of the alpha is increasing, some of the coefficients actually become 0. Do you see this? So that is why L1 regularization is also known as feature selection. Agreed? Okay. So have you understood this graph now? So we create now the best value of alpha. How do we find out the value of alpha? That now we will use cross validation to find out the best value for alpha. Lasso regression comes with built-in cross validation. So beauty of Lasso is that you can combine Lasso with cross validation. Alpha again ranges between 0 to 1000, CV is equal to 10, maximum iteration 10,000, and n underscore jobs is equal to -1. Can you, anybody tell me what is the use of this parameter? Okay, I need to repeat that. Okay, Simon, I'll do that. In the meanwhile, tell me what is the use of n underscore jobs, learners? See, once we have checked on the training and the testing process, and we found out that it is an overfitting model, the test error was too high than the others. So now we have to find out the, the best value of alpha. Okay. Right, so use the maximum course, and which is the, best alpha value which has come out. Over here, 6 comes out to be the best uh, regularization. So get the best alpha regularization strength selected by the cross validation. Clear? So it was not, the value of alpha was not 1, but it will come out to be 6. And now I will create and fit the Lasso model, taking this value. Now I will fit it and now check on my training and testing errors. So have they improved? Well, the test error is still higher than the training, right? But it shows a better performance on the tuned parameters. So zero coefficients such as runs, RBI, CAT, and all these new leagues have several coefficients shrunk to 0. This indicates the Lasso has deemed these features less important, irrelevant for the data set, and the non-zero coefficients give us the detailed relationship. Clear? Moving on to ridge regression. Ridge regression is another technique for handling overfitting of the data. That's known as L2 regularization. Here, none of the features will become 0. Rather, values will become less, right? So, where it is used, when to use that and when to use the other one. Get the best alpha selection validation. Now, what is this? Added below library. Okay, so when is ridge to be used? It is useful for handling multi-collinear data where two predictors, independent variables, are highly correlated to each other. Right? And the second important reason, Ajay, you are absolutely correct. Ajay Kana, you are absolutely correct. But the second reason where we use ridge regression is that it is useful for handling multi-collinear data where two predictors, independent variables, are highly correlated to each other. Now getting my point? Collinearity refers to a situation where two or more predictor variables in multiple regression model are highly correlated, meaning they have a linear relationship, and this makes it difficult to determine the individual effect of each predictor on the target variable. Right? So that's why the penalty term is added, the regularization terms are added. Getting my point? So now let's see ridge. Again, we have a ridge CV function which can do. So on the same data, we will first apply the alpha fit function and get the intercept value. Yes, ridge needed to use if we want to keep all the important features. So I have not been running the code, so I will get error. So sorry for that. I'm not running the whole code, going back and running it. So now let's move and then evaluate the model. Again, testing error is more than the training. So overfitting is there. And do we see the coefficients now? None of them become 0. Now we can use cross validation again to find out the best value. These are the values. I have used rich cross validation, and in this case, the value comes out to be 204. Right? Then we train on it, and these are my new coefficients. These are my new coefficients, right? All values have reduced. If you compare with the original, all values have reduced now. So the negative error relationship is with errors, division W, they show the negative relationship. So the coefficients with highest value suggest cumulative career statistics, total runs, the total hits are most important and showing a positive relationship with salary. Division underscore W, the only feature which is notably high negative coefficient, which indicates that being in Western division is associated with negative effect on the target variable. So do not be in the Western division. Years assist and new league and these features are smaller. So are you understanding? This is how you're practically supposed to run the code and write down the observations over here. And if we see it graphically, that in this case, the values will not become 0, but near to 0. Clear? So have you understood the concept of regularization? How it helps in preventing overfitting, whereas L1 helps in feature selection and Ridge helps in reducing the values if all are important. And of course, this analysis helps in understanding the relative importance and influence of different aspects of a baseball player statistics on the predicted target. Clear? Now moving on to the next concepts, that is optimization, right? Model optimization. Now, what does the term optimization mean? What is the meaning of model optimization? Optimizing resources. We want minimum number of code, less number of time to giving the best. Yes, how the model performs efficiently. Absolutely. So if we talk about the journey of data science or analysis, see everything if we are doing a normal Excel, maximum, minimum, drawing graph, that's also analysis. And even when we are doing machine learning, that's also analysis. But where is the difference? Are you able to get this graph that I'm showing? Where is the difference? Can you tell me? If we already have a data set, so this is the site for that. We are going to describe, about the historical data that we have. That is simple finding out insight in the data. When we try to find out why that happened, that becomes diagnostic analysis, that is insight. And if we move further, what is going to be predicted? Sorry. Or what will be the output that becomes predictive analytics. And similarly, why that, we are predicting that output, whether that is going to be good or bad, that is known as prescriptive analytics. So this is where we start from insight, and now we want to move to the foresight. How does it happen? When we start optimization of the model. Are you understanding this point? Very, very important graph. From one analysis to another. To explain you in more layman language, suppose you have cold and cough, right? And you go to the doctor. Doctor sees, okay, your nose is running, you have cold and cough. He says, you take this normal medicine and do a lot of steaming and take this medicine, you'll be fine. But that was his analysis which he done to just by seeing you. So then you come back, you are not fine, then you go back after a week to him, you say, no, I have fever also, I have other thing. Then he thinks that the fever he is not getting well, so maybe he has some kind of an infection. Then he prescribes you certain blood tests. So based on the blood test, he would give you certain medicine. But you are still not fine. Your further analysis is needed. Maybe you have a chest infection now, or something, and maybe you want to go in for an MRI. So that's how the level of analysis increases. All right. So basically, what do we want to do and what do we want to optimize in this whole machine learning process? That if we have this input data, that is the training data, including the target output. Of course, if it is supervised learning, we would also have the target output. This is my model, right? And output prediction calculated by model. So when we try to compare the predicted output with the actual output, therefore we are able to calculate the error and the loss function. Are you all there with me? Then we are able to calculate the error and the loss function. And using this error and or loss function, we can use optimization method to further reduce the values. How we can further reduce its value. Getting my point? Right? So that's how we are trying to improve on the error part of it. And then another way to optimize the model is through hyperparameter tuning versus model training. What is hyperparameter tuning? That to find the best hyperparameters which give us the most efficient results. And this is a very, very important slide because it gives the whole crux of the data, of all the points that we have studied till now. Please look here. This is my data set. Feature engineering is performed before. What are the different aspects of feature engineering? And why is feature engineering required? Tell me. What are the different aspects of feature engineering and why is it required? To prepare the data to feed into the model, not tune, we will say to prepare the data, pre-process the data to feed into the model. And what are the different types of feature engineering? So what are the different processes? Encoding, scaling, transformations, right? Dealing with the outliers, they all come under feature engineering. First point, first step is clear. Then what is happening in this particular step? Can anybody tell me what is this step known as? Splitting, but what are we splitting and why are we splitting? It is splitting of the data set. Why are we splitting it into three parts? Normally it is training and testing. This step is known as cross-validation, that it divides the training data into training and validation and a separate test data. Second step is splitting of the data, yes, but we generally keep using it for cross-validation by taking multiple samples. Got it? By taking multiple samples. Now, this is an iterative process. This keeps on getting repeated. So the training data, we build models, train the results, right? And finally, once the training is done, then on the validation thing, we do the training results, do hyperparameter tuning, and keep on repeating this iterative process. Finally, the best model which is selected is then used for testing the output and compare the results. Do not get confused. See, every concept that we study has its own role and concept, right? So where will the regularization fit over here? If I compare the result, my testing result is much higher than the training result, then it is an overfitting model, right? We always start with the basic mega. Then we will use the model over here as Ridge or Lasso and then do the comparison. Now getting my point, everybody? All right. And the two types of hypertuning methods are grid search and random search. Grid search is the one in which we It's an exhaustive research technique where we have different hyperparameters, one such as A, B, and C. It's not necessary that, we have understood that regularization has one hyperparameter. We have other models like decision tree, which have many hyperparameters. Hyperparameter to XYZ value, and then we try to take all the combinations and then see which one works best for a model. Disadvantage of this method is it's an exhaustive method. Computationally and time-wise, it is expensive. Clear? And random search, that randomly we will select any hyperparameters and do training on it. Clear now? And we have seen, so cross-validation is a very, very important technique. Why? Because it helps to split the data into training, validation, and test set. Please make this point clear. Cross-validation technique will almost be used in supervised learning because it will divide the data set into three parts. That is training, validation, and testing set. Useful if you want to have a metric on how well your model is performing. Clear? So once the grid CV search returns with tune parameters, build the model using this set with the tune parameters and test the new model with the test set. Clear? And this is another, slide which I always show it to my learners even in my feature engineering class. Now, are you able to interpret this particular slide, everybody? Yes. Right, so we again have a data set, retrieve the data set, perform pre-processing, wrangling, feature extraction, feature engineering, train the model, then model evaluation, hyperparameter tuning, and reiterate the process. But this slide gives a much better picture of each step. Got it, learners? So getting back to the file. So this file is pretty long. Last week also we have done, and I think so this session also we would be using. So model optimization means hyperparameter tuning is the process of finding the best settings for the parameters in the machine learning model. Hyperparameters are settings that are not learned during the training, but are set before the training process begins. Hyperparameter tuning involves trying different combinations of the hyperparameters and evaluating the model's performance using validation techniques. So the two techniques that we can use is grid search. So how does it work? How do we do the grid search? It systematically works through the multiple combinations of hyperparameters. It performs an exhaustive search on a specified parameter grid. So how do we go about it? Please try to understand the different steps. The first step is we define a parameter grid that is defined with the help of dictionaries because there can be more than one hyperparameters in the model. Combination evaluation. The algorithm evaluates all possible combinations of these hyperparameters. Model training. For each combination, the model is trained, evaluated using cross-validation. And then we have the optimal parameters combining yielding the best performance. Highest accuracy is chosen as the optimal set. All right. And how does the random search work? It defines the parameter distribution, specify the distributions and ranges of the hyperparameter. Random sampling, random sample combinations of hyperparameters from these distributions. Model training for each sample combination and optimal parameters. All right, so now on the same hitters.cv, we are running the code. I might get a lot of error. It will. Let me run the x_train. Okay, so this is the grid search cross-validation. Here we are creating a cross-validation object with repeated k-fold function. Number of splits is equal to 10. Number of repeats is 3. Random state is equal to 1. Are you now there with me? Everybody, other code, else code is running. Then we create a grid or a dictionary and then try to find out the values. So still it's giving error. Is it running for everybody else? Oh, well, I've tried to do a shortcut, but shortcuts never work in life. Value y input consists of nan. Okay. Yeah, are you getting it? I'm not running the code. So this point is clear. So the best parameter grid of alpha, now it's coming out to be 0.9. Is it the same with everybody? So then we create and fit the ridge regression model to avoid training data with the optimal alpha. So here we have the ridge function results into best parameters alpha, fit them through the training input as well as output and find the mean square value that comes out to be 341. And R square comes out to be 0.38, which suggests a moderate fit. The model captures some of the variability in the data, but not a large portion. And now if I see the coefficient, this is how the coefficient values are. Now let's move on to the next concept, last concept by creating pipelines. So Scikit-learn pipelines are nothing but an automation of the model fitting and data transformation steps for training and data set. So what are we doing at the moment? When we upload the data, we separately use fit and transform, do encoding, do scalar standardization. Now we will try to implement it with the help of a single pipeline. So what do? If we have test data, test labels, we would perform feature scaling, standard scalar initially. Then if feature selection or extraction, dimensionality reduction is required, that can also be done. And then the model data can be fed to the different models. So how do we go about it? We are very clear in supervised learning. We have a training set and a test set with class label, right? So in the first step, we will try to fit the training data that is missing in the test set because we do want to avoid data leakage, right? The fit function will never ever work for the test data, right? And therefore, we have the fit transform function over here. This is the pipeline, right? So over here, we do the transformation such as for scaling, dimensionality reduction, and then do the predictive model. And over here, it is fit and transform for the training data, but for the test data, it is only the transform function. Clear? And the predict will only be for the test data. Now let's see how do we practically implement it. So why Scikit-learn pipelines? Pipelines provide an organized approach to managing your data, pre-processing, modeling the code. They combine the pre-processing and the modeling steps into a single streamlined process. Cleaner code pipelines eliminate the need to manually manage training and validation data at each pre-processing step, reducing the clutter and the complexity. Fewer bugs by bundling steps together. So bugs are few. It gives a much more cleaner code and easier to productionize. That is, they simplify the transition from a prototype to a model to a scalable, deployable solution. Clear? So we have Scikit-learn is a beautiful library. We just need to, create a class or we do import the pipeline function and we will create an object of pipeline class, whatever steps that we want to perform. Do we want to use any kind of memory or verbose? Clear? So a pipeline is a sequence of data transformers that can include a final predictor also, final output also. It lets you apply pre-processing steps to your data in order and optionally end with a predictor for modeling. Each intermediate step in the pipeline must have fit and transform methods, while final step only needs the fit function. Memory stands that you can use cache memory for these transformations to make the processing fast using the memory argument. The pipeline main goal is to combine multiple steps that can be cross-validated together and have their parameters adjusted. You can set parameters for any step by using it name followed by a underscore. So you can set any of the parameters by default followed by a underscore name and the parameter name. And you can replace any steps estimator with another estimator or remove transformer by setting it or pass through or none. So now over here, they are using a different data set. That is the one with ocean proximity, that is housing one. I think so I gave you for testing also. So it is little different from original because one of the parameter is categorical ocean underscore object. So how do I check that? What are the different categories of this particular function? How do I check that? So we have this categorical data. So what are the different encoding techniques? Either we use one hot encoding. That is better because there is no order in this. So we'll not use label encoding. We'll use get underscore dummies function to perform it. Value underscore counts function is a function in Python which gives the categories along with their frequency count. Very, very important function. What is happening in this particular code of line number 46? Come on, learners. Y is getting the output value and then we are separating the X. Yes, we are defining input and out. What is happening in the next step? Line number 48, what is happening in the next step? Splitting of the data, very, very important. And then we see the info and sum over here, right? So where are the null values? Where are the null values? Total bedrooms has 162 null values. Data is huge, 14,448, right? So definitely cleaning is required. Removing of the null values, encoding is required, right? So rather than now performing each of these steps separately, can I use the concept of sklearn pipelines? First, I will feed in for training data, perform feature scaling, feature extraction, and ML algorithms, and then work on the test data. Getting my point, learners? Okay. So what are the steps that we want to perform before building the model? Feature engineering steps. So feature engineering part is used as sklearn. Even the other parts can be combined as pipeline. First, missing value treatment, imputation. 162 missing values in the total bedrooms, numeric data column. Then we have the dummy variable creation for categorical data. And finally, standardization of the numerical value. So how do we go about it? These are my different libraries that I will import, and most importantly is the pipeline library. Getting my point? A very important concept in sklearn is the column transformer. That importing column transformer class to apply different pre-processing steps to different subsets of the feature. So column transformer has the capability that encoding is applied only on categorical data, not on numerical data. Getting my point? So it will only be applied on categorical. So let me explain this. Okay, so this is how the fit transformation happens. But if these are my features, which is a combination, obviously, of numerical, categorical, and others. So column transformer has the beauty that for numerical columns, only scaling will happen. For categorical, one hot encoding, and maybe others can simply pass through. It's not necessary that some operation needs to be performed on it. And finally, we can get a transform data in very one go, and it can be combined together. Got it? Column transformer concept is clear to everybody? So here we go about implementing it. So now when you read about column transformer, you will understand that it allows you to apply different pre-processing steps to different subsets of the features in your data set. This is particularly useful when you have a mix of numerical and categorical data that require different types of pre-processing. Column transformer ensures that each column or group of columns gets appropriate transformation before combining the results for further processing or modeling. Okay, so now step 1. Let's store the names of the numeric and object type variables differently. So how are we going to do? And now we have splitted the training and the testing data, and we are exclusively selecting the data types, include object, exclude object, and result. Are you understanding this code, learners? So housing underscore cat will only have one, since this data set has only one categorical data, that is ocean underscore proximity, and the rest are all numerical in nature. Clear? Now, the next step says to set up Scikit-learn pipelines for numeric variables, we need to perform missing value imputation and then standardization. So how do we go about it? Now we will create a pipeline object using this pipeline function, num underscore pipeline. So for numerical data, we will import, do the missing value imputation and standard scaling. Is this point getting clear? Simon, are you there? Are you understanding this code now of creating pipelines? Yes, learners. What is imputation and what are we trying to achieve over here? Imputation is the concept of missing value, and here we are filling the missing value with the median value. Good, good, Megha. Very clearly it says that, right? And standardization is that we are trying to create the mean of the data 0 and standard deviation equal to 1. Then unified data processing with pipelines and column transformer. Now, we need to create another pipeline. No. So we've created a numeric pipeline. Now we create a column transformer, the numeric pipeline, and the other one categorical. For categorical data, we only need to perform only and only one function that is known as the one hot encoder function. Clear? So this ensures both numerical and categorical data are pre-processed approximately within single unified work. Now got it? The beauty of column transformer that we have combined the numerical as well as categorical values. Okay, then we do pre-processing fit underscore transform x underscore train. We're going to fit and transform and now check the data set for training. Clear? Now do you see? It has already done this. So right, so now we fit and transform and now check the training data. This is my training data. And now if I check the scaling has already happened, negative values are there, as well as the null values have been removed. Got it? Pipelines, are you understanding? So what is our observation? Good to see all missing values are treated, numeric values are standardized, ocean proximity is converted. Now, the other way of creating model is again, you can create a final pipeline for pre-processing and model reg. Over here, we are creating reg regression model straight away and then moving ahead. So have you printed that also, the final pipeline also? Yeah, so final pipeline gives you this, that after applying the basic thing, we are applying the ridge model, right? And then we define the grid of hyperparameters to search. You can set parameters for any step. So over here, this is my ridge alpha, the hyperparameter, which will range from 0.1 to 2.1. And then I use my grid search CV along with cross validation. Estimator is my final pipeline. These are my grids that I have passed onto it. Scoring, I'm using negative mean absolute error. Number of jobs is equal to -1, and we fit and get the output. Clear? So the mean absolute error is 49,000 and the alpha value is coming out to be 0.1. Then I check my test result. The test result is slightly higher, so it's almost a good fit of the value. Now clear? How, and even in classification model, we would be using a lot of pipelines to get the result. Getting my point? So finally, today, after Scikit-learn, we come to the end of regression analysis, which is, part of supervised learning, predicting numerical value. Regression analysis is an essential method for estimating, examining, and predicting variable relationships. In this lesson, we type, as we had discussed initially, types of regression, then the different error matrices, this cross-validation technique, the regularization technique, hyperparameter tuning, and then finally the pipelines. Are we all now clear with this particular file 3.2? Finally, we are ending with regression today. First question, what is the primary goal of regularization in machine learning model? Why do we want to do regularization? Yes, if we want to prevent overfitting. Which of the following is a characteristic of L2 regularization? Squaring of the value. Which answer is correct? A, B, C, D. Quick learners. It is both B and C because it adds the squared magnitude. It's rich of coefficient and it reduces overfitting by reducing the model complexity. Next question. What effect does increasing the alpha parameter in Lasso regression have on the model? Lasso, do we want to increase model complexity or decrease? Obviously, when alpha increases, the model complexity. What is the primary difference between L1 and L2 regularization in terms of the effect on the model coefficients? Remember, L2 means squaring of the value, L1 is absolute. So it's simple. L1 encourages sparsity. What is sparsity? Having value 0. So it makes most of the features equal to 0. Well, while L2 regularization does not encourages sparsity. Now clear? How does regularization help in improving the generalization ability of a machine learning model? We want to reduce the variance or the bias? Overfitting. Overfitting gets reduced by variance. What is the risk with tuning hyperparameters using test dataset? What will happen if we tune hyperparameters? What is the risk with tuning hyperparameters using test dataset? The model will overfit the test set and data leakage can happen. Which of the following is not the purpose of optimizers? They try to avoid overfitting because that's the work of regularization. If searching among large number of hyperparameter, you should try values in a grid rather than random value so that you can carry out the search more systematically and not rely on chance. True or false? We should carry out more systematic searches or random searches when searching a large number of hyperparameters. right? False. You should try values in a grid rather than random values. Why? Because then it would become an exhaustive search, right? We should always try random values. I hope this knowledge check was helpful for everybody.
Start with another part of supervised learning, that is classification. Now tell me, how will you define classification? It says supervised learning used when the output is categorical, right? Yeah. So this is supervised learning technique when the output is categorical. So these are the independent input variable and the model classifies them as animals and fruits. So are you aware about different classification techniques, learners? Do you understand different classification techniques? Do we understand the concept of binary classification? What can you interpret from this particular diagram? That the the model will classify the input, or not input, sorry, the outputs into two categories. For example, if a mail is there, it will either put it into the spam folder or the inbox. So when there are two categories as output, that is known as binary classification. Getting my point, learners? Can we have more than two classes as output? Can we have more than two classes as output? Yes, we can have, when we want to label different vegetables such as capsicum, carrots, tomato, radish, turnip, it could be endless number of classes, and that is known as multi-class classification. Are you all getting this point, learners? That is known as multi-class classification, learners. What is this? Suppose I have an image and in the image there can be multiple labels. This image consists of a truck, boat, dog, as well as a plane. So if we have more than one, it's not multi-class, but a same, uh, you know, image or a same input. For example, a movie can be romantic, thriller, horror also, right? Or comedy, thriller, horror. So the same item can have multiple labels. That is known as multi-label classification. What do you observe over here? If the classes are not balanced, right? The images of trucks are around 60% plain, only 25% boats, 15. Then there is a different techniques to deal with imbalanced class data set. All right, so this basic concept of different classes is clear. Now let's straight away dive into how we will analyze the classification output, right? Or what are the different metrics to analyze the classification output? So what do you think? How will I check whether my model is classifying the mails and the spam mails correctly? The metrics which is used, or the major role that is being played, is done by the confusion matrix. Please try to understand. For example, I'm taking a very simple example. There is a bag of balls of red and green balls. Now, if I tell you to classify them, it is good that in the red ball bag you put all the red balls, and in the green ball bag you put all the green balls, right? So that is true positive and true negative. So the green balls which belong to the green bag are in the green bag, and the red balls which belong to the red bag are in the red bag. But is there a possibility that a red ball can be in a green bag, or a green ball can be in a red bag? Is that possibility? Yes, machine can create those errors. And that kind of errors are known as false negative and false positive, right? When the machine does not predict the correct output. So what is our aim as a model? We always want to increase the true negative and true positive to create the best results, right? And we always want to decrease the errors, that is the false negative as well as the false positive. Getting my point? Right? So a confusion matrix, please remember again, it is very, very important point when we always talk about classification, that a confusion matrix is a n by n matrix used for evaluating the performance. And that is why statistics is said to be the strong foundation for machine learning concepts. Bang on, Mega. Appreciate this. Yeah. So confusion matrix is an n by n matrix used for evaluating the performance of a classification model where n is the number of target classes. So it will always be a square matrix. A good model, as we have understood, will have high true positive and true negative rates, and whereas a low or a bad model will have, high, low true positive and true negative rates. So what do we do when we have imbalanced data set? That means the ratio of the classes is not same or equal. It's always better to use confusion matrix as your evaluation criteria for your machine learning model. So this is how, you will get the output in terms of your Python code. It will create this kind of a matrix and display for you. And I hope the terms true positive and true negative, false negative are clear. True positive is predicted positive, which are actually positive. False positive, predicted positive, but are actually negative. Getting my point? And this is the exactly the same example I always use in my hypothesis testing class also. I use the same example. All right. So this is a very, very interesting example. We have the images of cat and dog, right? So we have about 20 images of cat and dog, right? So for cat, they were only 7 images, and dog, they are around 13 images, right? So I, ran this particular images on the model. So 6 images, which were actually cat, were predicted positive by the model. So that becomes my true positive. 11 images which were not cat were actually predicted that they are not cat. They come under the true negative category. So very good. But the errors were that the image was of the cat, but it says that you are a dog. So one error over here of false negative. And similarly, the image was of the dog, but it says that you are a cat. So this is false positive. So the false negative errors are known as type 2 errors also, and the false positive are known as type 1 error, or also known as alpha and beta. If you remember from hypothesis testing, same concepts, absolutely same concepts are being used. Are you understanding this? So they are different metrics that can be evaluated from this confusion matrix: accuracy, precision, recall, F1 score, FPR, and FNR all can be calculated. So if I talk about accuracy, accuracy simply measures how often the classifier makes the correct prediction. It's the ratio between the number of correct predictions and the total number of predictions. So what does accuracy mean? I'll take my true positive, true negative divided by the total number of output. That gives me accuracy. But what is the illusion over here? The illusion over here is that it is not valid for imbalanced data set. Anu says, why type 1 and type 2? Why type 1 and type 2? Is there a possibility that the classes might not be classified correctly? So type 2 and type 1 actually arise because I am considering one of the statement as positive. Positive means that the image is of the cat, and negative statement means that you are not a cat, right? So false positive error means that actually it is not a image of a cat, but still says you are a cat. That is why false positive, that it is not a cat. and false negative because it is not a dog. The same game we play between null, but we'll be, resolving it into different metrics. So one of them is accuracy, the other one is precision. So the precision is defined as the ratio of the total number of correctly classified positive classes divided by the total number of one predicted. So precision is useful when, please try to understand, precision is a useful metric in cases where the false positive is a higher concern than false negative. What do we mean by that? That false positive is a higher concern in precision. So what is more deterring, whether the mail is not a spam but the model predicted as spam? Is that more important than a mail which was spam and model predicted as not spam? Getting my point? So if our important mail is considered as spam, then that is a serious issue. Therefore, the precision needs to be high. So what is precision? It is true positive upon the true positive plus false positive. Getting my point? All right. So the other metric that we can use is recall. Recall is classified as the ratio of the total number of correctly classified positive classes divided by the total number of positive classes. Or out of all the positive classes, how much we predicted correctly. So recall should be high and ideally 1. And again, where is the recall function mostly used? It is useful metric in cases where false negative trumps false positive. Getting my point? So what would be the case where false negative is important than false positive? For example, medical cases where it does not matter if we raise a false alarm, but actual positive cases should not go undetected. Got my point? So this is the formula for recall, the true positive divided by the true positive plus false negative. Clear? Ma'am, do we need to calculate all these formulas? No, you just need to understand the mathematical intuition. The Python programming will do it all for you, right? So some might say, ma'am, sometimes, the false negative error as well as the false positive error, both are important, right? Then how do we go about? Then the metric which is used to balance it out is known as the F1 score. So the F1 score is a number between 0 and 1, and it is the harmonic mean of precision and recall. So the definition already has the formula. Okay, harmonic mean. We use harmonic mean because it is not sensitive to the extreme values. So F1 score is valid when we have imbalanced data set because it maintains a balance between the precision and recall for your classifier. If your precision is low, the F1 is low and the recall is low again, and F1 score is low. So what do I mean by that? This is the harmonic mean and this is the formula. So F1 score is the harmonic mean and it should be ideally equal to 1. So there will be cases where there is no clear distinction whether to use precision or recall, then we can use the F1 score. Got it? So again, a quick recap. Accuracy is used when true positive and true negatives are more important. Accuracy is better metric for balanced data. False positive is much more important. Use precision. Whenever false negative is much more important, then use recall. F1 score is used when the false negative and false positives are important. Now clear? This gives you more clarity when to use what and where. And how do we create this confusion matrix in Python? By simply importing sklearn matrix, import confusion matrix, and running the confusion underscore matrix function. So this is my y test, y predicted, and this is how I get the output in form of two-dimensional array, right? But the best part about it, that simply by using Scikit-learn metrics import classification report, we can get the all the metrics in one particular output. This is what we actually use. Is it good 85% accuracy? See, if you're not, see, Simon, it's a very, very relative question, right, Simon? Obviously, 100% is perfect. But depending on the model, the kind of problem that you are facing, if you're not getting accuracy more than that, then this is the best. But if you can get accuracy up to 92, 95, or 97%, then of course, 85% is not acceptable. You are the one who's going to decide whether to accept or to reject the project. Or you want to make further improvements or optimizations onto it. All right. So this is a very, very beautiful, code that, for classification, that we will have this classification report in which we get all the output precision recall F1 score in one tabular form. All right. And this is what we are going to actually use for, comparing the results. Getting my point? So again, a quick recap: accuracy, precision, recall, F1 score, specificity, and different metrics can be calculated. But as I told you, we do not use different metrics. We will straight away import classification underscore report and get the output. Now, another very, very important factor, how graphically we can judge the output. So in classification problem, we have AUC and ROC curve. What does AUC stand for? AUC stands for area under the curve and ROC stands for receiver operating characteristics. This material is not there in the Simplilearn file. This is my material. I'll be sharing it. Even the regression material, classification material, right? So another very important factor to understand classification is the graph AUC and ROC curve. AUC stands for area under the curve and ROC stands for receiver operating characteristics. So AUC ROC curve is a performance measurement for the classification problems at various threshold settings. Now, what do we mean by various threshold settings? That we will try to change the, that whether the classes have been classified correctly. The threshold value always ranges between 0 to 1. So it's like a meter rating. Okay. Now, this is a point or this is the boundary. Yes, these two classes have been classified correctly, or the other two, right? ROC is the probability curve. Please try to understand. ROC is nothing but a probability curve, and AUC represents the degree or the measure of separability between the classes. So here we are trying to measure how well the two classes have been classified correctly based on the threshold value. It tells how much the model is capable of distinguishing between the classes. Higher the area under the curve, the better the model is at predicting 0 classes as 0 and 1 classes as 1. Now getting my point? What do we mean by AUC? It represents the degree or the measure of separability. The higher the area under the curve, the better the model is at distinguishing between patients with diseases or no diseases. So how does it work basically? So this graph is drawn between the false positive rate on the x-axis and true positive rate on the right hand axis, right? And the this graph is, and this is area under the curve, and this is the ROC, the receiving operative, sorry. So this is receiver operating characteristics, and these are the different formulas that we have just now seen. So sensitivity and specificity are inversely proportional to each other, whereas TPR and FPR are proportional. Okay. So sensitivity and specificity. Okay. Recall the name. Recall. Have we understood recall? Recall is nothing but the ratio between true positive and the true positive and false negative. Okay. The recall is also known as the true positive rate, and the other name is sensitivity. Now clear? Specificity is opposite of this. This is true negativity uh, divided by true negative plus false positive. So ROC curve is the plot between the true positive rate and the false positive rate. That point is clear. Across the all possible thresholds. So what is this threshold? The threshold value is always between 0 to 1. And in between, it tells how well the two classes have been classified, right? And AOC is very clear that it is the area under the curve. So the more the area under the curve, which is equal to 1, the better is the classification. Now clear, Anush? So ROC AOC curve is the area under the curve. It sums up how well a model can produce a relative scores to discriminate between the positive and the negative instances across all classification threshold. And the values will always lie between 0 to 1. So AUC is desirable for the following, that why do we want to understand the area? Why do we want to use this area under the curve? Let me go through it, and still you have errors. I'll explain them. First, let's get the crux of it. I understand a lot of points are there. First, let's get the crux of it. Area under the curve is scale invariant. It measures how well predictions are ranked rather than the absolute value, right? So it's scale invariant. It tells how well the predictions were ranked. It's not absolute value. It helps in comparison. Secondly, it is classification threshold invariant and measures the quality of the model's predictions, irrespective of what classification threshold is chosen. So this is what I mean by my threshold. Generally, it should be like 50-50%. Generally, 50-50%. That my true negatives have been classified as true negative. Green balls in green bag, red balls in red bag. And the total area under the curve is 1. So this is one of the ideal situations. This is one of the ideal situation that there is no overlap. Area under the curve is 1 and the model has ideal measure of separability. Now moving on to the next point. If we see it practically, even if my threshold is 0.5, there would be some, errors that, the red ball going into the green bag and the green ball going into the red bag. But these should be less. And if my area under the curve is close to 1, around 0.9, 0.8 or 0.7, then also it is said to be a good classification problem. So AUC 0.7 means that there are 70% chances that the model will be able to discriminate between negative and positive classes. Now getting my point, everybody? Now are you understanding the meaning of threshold? Now if I decrease the threshold, suppose if I make it to 0.2, what will happen? My false negative error will become less, but my false positive error will become more. So the threshold, we have to try to always create a balance to get the minimum errors. Okay. Now look at over here. This is the case where the model was not able to Differentiate between negative and positive classes. One of the worst cases, that area under the curve is 0.5. So we don't want the area under the curve to be equal to 0.5. So this is a worst situation where area under the curve is approximately 0.5. The model has no discrimination capacity to distinguish between the positive classes and the negative class. Now better? And what could be the even worse situation? That the true negatives have been classified as true positive and true negatives, positives as negative, and the area under the curve is 0. So when AUC is approximately equal to 0, the model is actually reciprocating the classes. It means the model is predicting a negative class as positive class. And do we want this situation? Never. We don't want this situation. Area under the curve to be 0, area under the curve to be close to 0.5, but close to 1 is a good option. That means the classes are able to distinguish each other clearly. What is the role of threshold? Classification threshold in machine learning is a boundary. At what boundary, as I told you, we will cut the two classes or cutoff point used to assign a specific predicted class for each object. Any machine learning algorithm for classification gives output in probability format. That point is also clear. So in the morning also I was teaching the LLM. So LLM chat GPT is, predicts the next word. They all come under the category of classification problems and they all give the output in terms of probability. Okay, so a little bit of Gen AI and LLM models. So LLM chat GPT, your Copilot, all the different models, they are all come under the category of classification problem and generate the word based on probability. Okay, so that's the tip of the day today. So in order to assign a class to an instance for binary classification, we compare the probability value to the threshold, and if the value is greater than that, then the probability it belongs to class 1. If it is less than that, it belongs to 0. So the story of threshold is like this, that what is the cutoff point that we can achieve to get the best distinguished classes? That if you increase the threshold, you move left on the curve, and if you decrease, you move right to the curve. Okay. Let's get back to the file. So now we are on lesson number 4. You can go ahead with 4.1. So there are a lot of algorithms that we would be covering in this classification: logistic regression, naive-Bayes classifier, KNN, decision tree, support vector machines. So today we will be touching on to the classification algorithms. Let's see how many are we able to do. Let's logistic, naive Bayes and KNN. Definitely we are doing 3. Let's see if we are able to begin with decision tree also. Let's see. So now if I ask what is the definition of classification, how will you define it? Tell me, what is the definition of classification? Yes, learners. I am purposely asking you these questions so that you have the, clarity of the concepts, and then you are also well prepared for the interviews. Supervised machine learning algorithm using categorical data. Always say it is part of which learning technique, and where the model is trained to predict the class label. The output is important. When I say label the output of the given input data, so it is important that the output is categorical. Getting my point? Please try to cover all the points in the definition. If you're going to just put 3-4 words, it will never give you a complete answer. Getting my point? Okay. So classification is a supervised machine learning technique used to predict the category of class of n observations based on the training data. So I think so this definition is quite correct. So classification algorithms categorize data into different categories. So do you think that in classification there is a role of this, straight line or linear regression? Do you think that can we use a straight line to separate two classes? Let's see. Since linear regression is a simple function, let's see, can it be used? But before that, classification, examples of classification in healthcare, whether you are diabetic or not, or your medical condition is there, all come under the healthcare category. Finance, banks, financial institutions are classification algorithm, whether you are eligible for loan or not. Marketing, classification aids in customer segmentation and target marketing. It helps business identify potential customers and tailor marketing strategies by categorizing customers based on their behavior. Retail, in retail, classification algorithms are crucial for managing inventory, forecasting demand, and manufacturing. Classification is essential for quality control, fault detection. So there is no domain where classification problems cannot be used. I hope you all are getting this point. In retail, marketing, manufacturing, HR, everywhere. Right, learners? Now, what are the different types of classification that we have understood? Can you tell me? This is what you are going to try to solve, Roshan. Can we use regression in classification problem? This is just, we are just about to solve it. We're just about to solve it. Just be patient. Okay? Okay. So what are the different types of classification? What is binary classification? So when the model is able to classify only two classes, for example, whether the mail is fraud or not fraud, or spam or not spam, comes under binary classification. Already predefined, yeah, to classify into predefined multiple classes, whether it is a tomato or whether it is a vegetable, it is a fruit, or it is an animal, or is it a domestic animal or pet. So many classes can be used. One to many? No, Chakrapani, that's not the correct way to answer. The model is capable of predicting more than one classes of the input. That's the way to answer it. Multi-label, multi-label classification. Be careful while answering this, that each data point can be assigned multiple labels simultaneously rather than just one. Yes, simultaneously, like in an image, it can have an image of a dog, cat, rat, a chair, etc. Okay. And the last part is imbalance classification. What is imbalance classification? When the classes are there, they can be two classes or more than two classes, but they are not equally balanced, right? One class, like 70% of males are there and 30% of females. When the classes are do not have the same frequency count, or we can say when one class has higher significantly more than other observations, right? When one becomes a majority class, other one becomes a minority class. Okay. So binary classification, under binary classification, some popular algorithms are used. So please try to understand. Binary classification can be achieved by logistic regression, naive Bayes, KNN, decision trees, and support vector machine. We are supposed to, do all of these. So while these methods excel in binary, capable of handling multi-class. So, except logistic regression or other are capable of handling multi-classification task also. This versatility allows them to be used in wider range of applications such as recognizing multiple categories of objects in images or predicting several types of behavior. So now we'll start with logistic regression. Before that, let me also let's do a recap. Now, what are the different metrics involved in classification? How do I judge that my classification problem is correct or not correct. Confusion matrix. Yes. So what are the different components of a confusion matrix? Accuracy, precision, recall. These are the different metrics, but components of confusion matrix are, I said components. True positive, true negative, false positive, false negative. Absolutely correct. And based on these components, we calculate different metrics which can be used to analyze the classification model. So if this is my data and I divide the data, because classification also comes under supervised learning technique. So if this is my data and I divide it into training and test set, and the training set over here, we have, right, from the training, we develop the model. Test set is used for model evaluation. And we understand for classification problem, the different metrics used are accuracy, precision, and recall, right? So it's a quick revision again. So this is my end-to-end matrix. If I have two classes, what are true positive and true negative? So when the output is also true, the predicted value is also true. When the output is false, when the predicted value is also false. But what are the two types of errors? What are the two types of error that we analyze in confusion matrix? Type 1 error is also known as alpha, or the false positive error, right? The type 1 is also known as the false positive or the alpha error. And type 2 error is also known as the beta errors. Clear? Then which metric is to be used when? We have accuracy. When out of the prediction model has been made, what the percentage is. If it is an imbalanced class, is accuracy a good metric to be used? Right? If we have more of positives, right, true positive, right, out of all the yes, how many them were correct, then we use the precision. Recall and sensitivity are the same. When we want to answer the question how good the model was predicting at real yes events. Recall and specificity. So there is this always this confusion about recall. So recall is associated with specificity also and sensitivity also. The question can accuracy. So F1 score. So F1 score is a more matured score which can be used, which is not biased towards the precision or recall. And it is used when dealing with imbalanced data set, meaning that they are more of one class label than they are of the other. It corresponds to the harmonic mean of precision and recall, right? And what is the graph that we understood, which helps us to identify whether the two classes have been classified correctly or not? If you remember that graph, learners, the AUC, it's AUC and ROC curve. ROC stands for receiver operating characteristics. AUC stands for area under the curve, right? So what was that graph telling me? This graph generates probability value instead of binary 0 and 1. It should be used when your data is set roughly balanced. The ROC is imbalanced data set leads to incorrect interpretation. So ROC curves provide good overview of trade-off between the true positive and the false positive rate for binary classifier using different probability threshold. So the value, if the value is below 0.5, it's a poor classifier. 0.5 random classifier. But if it is 0.7 or greater than 1, we can set that it is a good classifier. Now clear? So this is how we understand the ROC and the AOC curve is between the false positive rate and the true positive rate, right? And if we look at the more closer look at the AUC and the ROC curve, this is my X, this is my Y axis. This is my optimal threshold. Practically, we are going to draw this graph also and the selected threshold. The ROC curves gives a quick visual understanding of the classifier's accuracy. The closer to the right angle curve, the more accurate the model is. So more closer it is to the right. Classification threshold that turns the upper left corner of the curve, minimizing the difference between the true positive rate, false positive rate is the optimal threshold. Clear? Okay, so now let's go ahead and understand the first algorithm for classification, logistic regression, that is transform linear regression, which gives output between 0 and 1. So there was this query of you all, can straight line be used for classification problem, right? That was the query. So when I say, binary classification, how do you think that binary classification would appear? Yeah. So I'm asking you, how do you think that binary classification points would actually look in the graph? Tell me. Yeah. Maybe not a straight line always. Absolutely correct. Right? There can be on the either side of the straight line, right? So if I say it's a typical good binary classification data, it's a typical binary classification data that either the output will be 0 or the output, this is an ideal situation. Agreed? Either the y will be 0 or the y will be 1. Do you all agree? So now tell me, is a straight line a good fit on these data points? Or is it covering, is it consistent, or is it underfitting? No, this is not a good fit. And moreover, the values are also getting lesser than 0, some of the values, and some of the values are greater than 1 that we don't want. Because in binary classification, the output will either be 0 or be 1 in ideal case. Agreed? So now I need to modify this straight line into a sigmoidal curve or an S-shaped curve. Is it helpful for me? First of all, the values will always be within the range between 0 to 1. Is this point getting clear to everybody? And suppose if I want to find out that my threshold value over here is 0.5. So if my value is zero point 0.2, it is very clear that it belongs to this class. And if the value is zero point 0.7, it belongs to this class. Only the confusion would arise at 0.5. So it is up to me. The 0.5, I want to keep it on this class or that class. Clear? Yes, linear regression, that question that regression are incapable of solving binary classification problem. Why? Because the straight line gives underfit to all data points. The values can exceed greater than 1 or 0, right? So are all these points getting clear to everybody? Right? So how do we go about mathematically? So we understand this sigmoidal function equation is written like this, right? P is the probability 1 upon 1 plus e to the power minus y, where y is nothing but the, y can you tell me? It's like the linear polynomial, not even polynomial, multiple linear regression equation. Agreed, learners? So this is your linear regression. This is your sigmoidal function. So now if I start taking log on both the sides, so now on the left hand side, this is the equation that log to the power p. P is nothing but the probability. We want the answer in terms of probability that the values will lie between 0 to 1, that is p upon 1 minus p, beta naught, beta 1 x1, beta 2 x2. So again, ma'am, are we need to solving the coefficients over here? Yes. Logistic regression is a modification of linear regression, but here also we are trying to find out these regression coefficients. Got my point? Is this point getting clear to everybody? So taking this point further, log px upon minus px is known as the log it function. Now getting my point? Where does the term logistic term comes from? Because of this equation, and simple px1 minus px is known as odds of p. That's the technical term. So now you are clear that the straight line or linear regression is not capable of solving the logistic regression problem. So the straight line gets converted into the sigmoidal S curve because the predicted y lies within the range 0 and 1. I hope this is clear to everybody. So, ma'am, in probability, P is the success, 1 minus P is the failure of the probability, right? Same we are using. Absolutely, the concept remains the same. Yes. Okay. So, if I say what is supervised learning, sorry, what is logistic regression, please try to understand and try to answer all the points. This is what the interviewer will catch. How many concepts you have grasped. Okay. So logistic regression is a supervised machine learning technique primarily used for binary classification. In this method, we apply the sigmoidal function to the linear combination of independent variables and predictors. Now clear? Always say that it is a part of supervised learning classification problem used for binary classification. And here we are applying the sigmoidal function to predict using the linear combination of independent variables, predictors of features. What does this mean? What does that mean? Independent variable predictors or features. This refers to the input part of it, right? Absolutely correct. Great. So this produces probability value between 0 and 1, and this probability represents the likelihood of a data point belonging to a specific class, positive or negative outcome. Clear? Now, the mathematical concept of logistic regression, it uses the sigmoidal function. The core is the sigmoidal function, sigma ZS. So over here, logistic regression is also known as sigmoidal function. This is how it will always range between 0 to 1, 1 plus e to the power minus z, where z is nothing but the linear combination of input. Multiple variable linear regression, and the output is in terms of probability ranging between 0 to 1. Are these points 1, 2, 3 getting clear to everybody? So now you're getting the crux of machine learning. You have to first understand the mathematical intuition of that algorithm or model. Then how do we implement it in Python? Understand it from three perspectives. As I always tell in my data science class also, first try to understand the concept, the mathematical intuition behind it. Second, how do we implement it in Python? And third, how are we going to interpret the output? All these things need to be taken into account. Got it? What is the cost function? What is cost function? The error function. How are we calculating the error function in logistic regression? That is calculated with the help of binary cross entropy. Please try to understand. The cost function used in logistic regression is binary cross entropy, which measures the differences between the predicted probability and the actual class label, where M is the number of the training samples, Y is the true label, Y cap is the predicted probability. Clear? What does the term optimization now mean, learners? Do we need to optimize our models also? See the concept, same concepts will be applied. So what is optimization? Why do we need to optimize the model? Tell me. Nobody understands why do we need to optimize? What is optimization? Extracting the best, right? Getting the best. So the goal is to find weights W and bias B that minimize the cost function. That is, this is typically done using gradient descent. So we'll try doing the gradient descent algorithm as we move ahead with further algorithm. Mostly in ensemble learning I've covered. Yeah, so basically we want the best output from the model. So now we are going to use the breast cancer data set. Do I need to share this with you all? Okay. Please download this and be ready. So this breast cancer Wisconsin diagnostic data set is widely used data set in the field of machine learning, particularly in classification problems related to medical diagnosis. This data sets consist of breast cancer cases derived from a group of patients who underwent surgery and had their breast mass tissue sampled, whether they are cancerous or not. And basically, there are two types of cancer. One is malignant and the other one is benign. Malignant, malignant, I don't know how I really pronounce it correct or not. And the other one is benign, right? And this data set contains 569 instances, each representing an individual sample of the breast tissue. Number of attributes, they are 30 numeric attributes computed from the digitized images of the tissue sample. These measurements of the cell nuclei present in the images. So based on that, we are there. So what are the different attributes or inputs in this data set? Radius, mean of the distance from the center to point. So it's not an image, just they have taken different parameters, which will help us to decide whether it's cancerous or not. Textured standard deviation of the grayscale, perimeter, area, smoothness, compactness, concavity, concave point, symmetry, fractal dimension. The target variable diagnosis indicates the cancer type, which can be malignant or benign. So, what is the output? Diagnosis. And what are the two outputs of the diagnosis? Whether the cancer is malignant or benign. Now clear? Is the objective, please always try to give time on the data set. Without that, you will not be able to understand the analysis, what you're trying to do, and what you are trying to achieve. So we will use this data set to explore and compare various binary classification algorithm, examining how their performance varies depending on the type, implementation of each algorithm, accompanied by the mathematical explanations. Yes, learners, are we good to go? Why do we do regularization? First, let's understand that. If regularization is required, then only we will do, Anush. Why do we do regularization? Tell me. Yes, if observed overfitting, if the model will overfit, then we will. Okay, Anush? Yes. Now clear? So now let's start implementing. So what are the steps in Python? Come on, tell me quickly, learners. What are the steps in Python that we need to perform? Tell me quickly. Importing of the libraries. I hope the basic libraries are clear to everybody. Then these are for the pre-processing model scaler. Pipelines. Have we understood the concept of pipelines? Can we implement it in classification? Yes. What is the concept of pipelines? EDA? What does EDA mean over here? No. We don't, yeah, we start with EDA, but first is import of libraries. I'm starting from very basic, Simon. So what is the use of pipelines? Tell me, learners. Yesterday we did sklearn pipelines. Deployment after package, what do you mean by that? Organized workflow. Yeah, it's an automating workflow for building ML models. Good, Ajay. That's a better way. It's automating because we would do all the pre-processing in one workflow. That's the correct way of answering it. Okay. An sklearn linear model, logistic regression, and accuracy. My sklearn version is 1.5.1. What about you, learners? Have you been able to load the breast cancer data set, everybody? With ID, diagnosis, radius mean, texture mean. Oh, so Subra, yours is higher than mine, right? So what do we observe in the info of this data set? Tell me. What do we observe in the info of this data set? Tell me. Where is my output? This is my output. And of course, it has to be categorical as malignant or benign. And all others are numerical values. You see, all others are numerical value. So do we need to convert the output categorical value into numerical? Do we need to encode the output? No. Ajay, we don't need to encode the output. Is encoding required? Yes, we definitely need to, because computer will not understand benign or malignant. All the categorical value need to get converted into numerical value. Okay. So df dot describe. Okay. So this is the ID. This is the radius mean, texture mean, the perimeter mean. Do you see this? The count, the average value, standard deviation, minimum and maximum. So you have to, observe whether the values are lying within the range or are they too deviated, right? Right. So this is if I do df dot describe dot t, then I get the values for all other parameters. So unnamed, do we see there are, complete null values? So can we drop off this column? So df dot drop nr, right? Access equal to 1, it is for the column. In place equal to true, we understand that means it will make the changes original in the data set. So now we will remove this column because it is of no relevance. Got it? Uh, So now my data set is ready or not? So when I do a df dot shape, it has got this particular data set has got 569 rows and 32 columns. Agreed? So this particular data set has 569 rows and 32 columns. And what is the best way to check categorical data? By using unique function, which gives me the different categories. N unique gives me the number of categories, but I always prefer value underscore counts function. That means it gives me the frequency along with the category. So they are 357 benign cancerous patients and malignant 212 malignant patients. Got it, learners? And if I draw a bar graph or count plot of it, I get this type. Everybody is getting this point, learners? Are you all there with me, learners? Even in your project or in real world, always try to create graphs, write down the observation what the graph is doing, right? Then again, which id has been dropped, which column has been dropped, the id column has been dropped, and this is my original data frame. Got it now? Trying to plot a correlation heat map to understand the relationship between the features. The heat map visualizes the correlation between differences in the data set. So what does the heat map do, or what is correlation? Yesterday, we discussed about this. We've discussed this point. What are the values of correlation? What does the correlation do? What is the range of values of correlation? Tell me what is correlation, Pearson's relationship, which will always range between -1 to +1. Did I share that with you or not? So what are the values of correlation? -1 to +1. Positive correlation, yes. Negative correlation and no correlation. Yes, good, good. So you all remember, other learners? Great. So heat map is the map which gives me relationship between the various dimensions. So what do we observe? That there is high correlation value between radius mean, perimeter mean, and area mean. Whereas when we talk about other observations, feature groups, features related to worst, largest value of these features for being each image, mean and error, standard error calculations are grouped over here. Now tell me what is happening in the next stage. What is happening over here? That from Scikit-learn pre-processing import label encoder. Right. Label encoder is one type categorical encoding. Please try to understand the correct word. This is categorically encoding, and we are using label encoder, right? And only one column is categorical, that is diagnosis. And here I am trying to fit and transform only the diagnosis column. So now my benign and malignant values change into 0 and 1. Clear? Is this point getting clear? So now when I see my df dotted, I see now no M and B. Earlier, please look at the output, the column of diagnosis. It is in terms of M and B. Now I can see it in terms of 0. Can we define what is 1 and what is 0? How else? Yeah. So when 1 is malignant and 0 is benign. Yes, we can. Now what is happening over here? Yeah, so basically we are trying to separate the input and output and then split the training and the testing data, right? And after the splitting only, then we move to sklearn pipeline, dot pipeline to streamline the pre-processing and the training process. Why do we do this? Why do we do this after splitting the training and the testing data? That the features in the training and the test sets are standardized to have a mean of 0 and standard deviation of 1. A logistic regression model is trained using standardized training data to avoid data leakage. We don't want our testing data to be part of the training data, otherwise they would no point be of the prediction. Got it? Right? So do we understand this pipeline function? What are the two things that we are doing in this pipeline function, learners? We are creating a pipeline. First step we are doing. What does standard underscore scalar do? Come on, learners. Tell me, it's not that difficult. We've all done. the EDA part of it. What does standard scaler do? Feature scaling, yes, standardization. And then we are applying model selection, logistic regression, which will be iterated 10,000 times and randomly the data 42 is getting selected. So till here, are we clear? We have splitted the data, right, into training and testing. Now, after training and testing split, and even the categorical encoding has been done, I am doing standard scalar function. What is standard scalar function? That all my data points will be standardized with mean equal to standard deviation equal to 1, right? They will all be having that value, mean equal to 0 and standard deviation equal to 1. And next step, we will apply logistic regression on the data. Now better, Simon? Now clear? And finally, we go in for the pipeline dot fit. What does pipeline dot fit do? It will try to find out the parameters or the training data happens on input as well as output training data. Till here, so now when I do fit, it will automatically first do standardization of all the input points and then fit the model. And then we will predict the output using training and testing data. Clear? But since it is a binary classification problem, we will do not use simple predict function. We use predict underscore probability A. What does that mean? Probable outputs are needed that will range between 0 to 1. So this is my output, obtain the predicted output after training the model. Got it, learners? So now, how do I actually test? This is my actual label. This is my predicted label, and this is the probability associated with it. Are you understanding the three aspects of it? So when I do the probable A, it gives me the values in binary. Yeah, the values will be 0 and 1. The values will be 0 and 1. But will it be 0 or 1 will depend on the probability value. Got it, Ajay? This is what I was saying when I say about the LLM models, right? The probability decides what is going to be the output. And then we can calculate the accuracy score and the training score. So in this case, both of them are coming out to be quite same. So we can say it's overall coming out to be a good fit. But which are the metrics which are actually used for classification problem? Which are the metrics which are actually used for classification problem? The confusion matrix. Because it's a little imbalanced, not highly imbalanced, because if two classes were absolutely equal, then it would have been balanced data, 50-50. But it is somewhere around 60-40, I would say. Okay, Puneet? Value underscore counts on this graph is telling me it's imbalanced. Right? So the training and the testing accuracy is there. But ultimately, who is the judge? The confusion matrix. The components of confusion matrix are true positive, true negative, false positive, false negative. I hope these points are very much clear to you. So the provided confusion matrix provides a summary of the effectiveness of COVID-19 tests that identify individuals with the virus and those without it. So we have understood this concepts that the case correctly classified as positive and predicted also as positive. These terms are very clear. We've discussed it in detail yesterday and I had done a recap. So now significance of confusion matrix is in terms of these metrics such as accuracy, precision, recall, which is sensitivity, true positive rate, specificity, and the F1 score. Right, learners? And do we understand the formula? That's also we've gone in detail. So lots and lots of revision for you. Then we also understand the ROC curve or the AUC curve, which is used as a graphical representation of a classification model's performance across different classification thresholds. It plots the true positive rate against the false positive rate at various threshold settings. So true positive rate or recall at these settings. Clear? So what is our main aim in, plotting the AUC or the ROC curve? That the default threshold for many classification algorithm is zero point 0.5, meaning that if the predicted probability is greater than zero point 0.5, the instance is classified as positive. However, this threshold might not always be optimal, especially in the cases of skewed classes. Do we understand the term skewed? What do we mean by skewed class distribution, learners? If the data is not normally balanced, it is known to be skewed data. Okay. So the methods of finding optimal threshold, there are two ways. One is maximizing your Jordan's J statistics. In this, we will find out the value of J by subtracting the true positive rate with the false positive rate. The optimal threshold is where the statistics is maximized. This method balances the TPR and the FPR, aiming to maximize the true positive while minimizing the false positive. Closest point to 0, 1. Another method is to point on ROC curve that is closest to the top left corner, representing ideal classifier. Clear? An area under the curve also we are clear. Now getting back to the Python code. So again, confusion matrix, classification report, ROC underscore curve, all these are part of which library? They are part of which library, learners? Learn metrics. Be very clear. Sklearn dot metrics. Even the RSS, MSc, they were all under these curves. Clear? So the confusion matrix is created simply by calling the confusion matrix by passing the actual value, predicted value output, and based on that, I get this display. What do I observe? 70 are my true positive, 41 are my true negative. And if I talk about type 1 and type 2 error, it's quite less. So logistic regression has done well. It gives me 2 and 1 errors. Clear? And then the best way to go about is creating a logistic regression report. So over here, the precision is 97, 98 for 0 and 1. Recall, F1 score is 98 and 96. And if I look at the overall accuracy is also coming out to be 97%. So overall, this particular logistic regression has come out to be a good classifier for this particular data set. Clear? So over here, they've given in detail class 0, negative class. Precision is 0.97, 97% of instances predicted as class 0 are actually 0. 99% of actual class 0 instances are correctly predicted as class 0. And here we move ahead. Right? All of the detail is given over here. Okay. And finally, how do I do the judgment that I need to do plotting of the ROC AUC curve, which shows the trade-off between the positive rate and the false positive rate at various threshold settings. The AUC value indicates the model's ability to discriminate between the positive and the negative classes. So parameters used in plotting are these many parameters. That first of all, ROC underscore curve is the function which gives me the different values of FPR, TPR, and threshold, right? And based on that, I'm going to calculate my Jordan's J and find out my optimal threshold value. So what do I observe? That optimal threshold value is coming out to be 0.4848 and ROC or the area under the curve as 1. So is it a good classifier? Area under the curve is nearing, it's almost 1. It is 1, not even almost 1. So it is a very good classifier. Getting my point, learners? So the ROC curve in the image reaches the top left corner, TPR equal to 1, FPR equal to 0, which indicates a perfect classification performance. The model perfectly distinguishes between positive and negative classes at various threshold settings. And the ROC curve for logistic regression model has AUC1. This model has perfect discriminatory power, and AUC of 1 means model correctly classifies all positive and negative instances without error. And the optimal threshold of 0.4867 defines the decision boundary for the classifier. Probabilities above this value indicate stronger belief that an instance belongs to the positive class, whereas the probability below this value indicate stronger belief that it belongs to the negative class. Clear? This practical example has made all the points clear. So over here, are we doing any kind of sigmoidal function, anything? That's already part of the implementation. So again, I'm repeating this point. First, try to understand the mathematical intuition behind the algorithm or the model. Secondly, how we will implement in Python. And thirdly, how do we interpret the results? Is it a good model or not? Clear? Ajay says, ma'am, one doubt. Despite I seen that this model is perfect in matrix itself, what is the main purpose of seeing ROC curve also? See, ROC curve tells me whether the two classes have been classified. Are they well separated from each other or not? That is the idea. Is this more overlapping or not? So just to reconfirm things, it's not by just doing one test. If you are suffering from some problem, the doctor wants to reconfirm from different tests, maybe the blood test, MRI report, and X-rays or other things, something like. So it's something which is more visually appealing, tells us has more impact. Yes, this is a good model. The confusion matrix also tells us, the different classification report also tells us, and AUC ROC curves also tells us. So there shouldn't be any doubt left, when we are doing our analysis. All the analysis should give the same result, right? So now do we understand this graph? Let's see. So now this is also one of the reasons the threshold is used. That if I take it as 0.5, any value coming above it, as I told you, would belong to this class, So distinctly, there is no overlapping. It distinctly classifies all the points, and any value which is lesser than 0.5 belongs to this class, right? So can we go in for a quick knowledge check about logistic regression and classification? So question number 1, which of the following metrics are used to evaluate classification models? Confusion matrix, ROC, and F1 score is calculated using confusion. What is a classifier? So when we talk about classifier, the output has to be categorical. So which one gives the output as category? It's both A and B? No. Output as a single discrete value or output as a single discrete value. So both A and B. Input can be anything, continuous or discrete. Yes, the answer is C. Next, false negative. What does false negative represent? Which option is correct? It's A, predictive negatives that are actually positives. Yes. In binary logistic regression, definitely it is C. The dependent variable consists of categories. Next question. Why is linear regression model output a poor predictor of probability? Why? Because D is the correct answer. It can give, it cannot, the range can be beyond 0 and 1. Next, the output in logistic regression problem is yes, equivalent to 1 or true. What is its possible value? So of course it is B. It would depend on the threshold value. Okay. So now we have naive Bayes classifier. Okay, now moving on to the next algorithm. The next algorithm is completely based on probability. So what is probability, learners? chances of occurring of an event. And what is the formula? Mathematical formula of probability. The number of successful outcomes upon the total number of outcomes, right? What is the probability of getting ahead when I throw a coin? It's 1 upon 2.5. When I throw a coin, what is the probability of getting head? What is the probability of getting 1 when I throw a dice? That is 1 by 6. But there is another concept which is associated, which is known as the conditional probability. Do we understand? What is the probability of event A given probability of event B? Do we understand conditional probability? This particular algorithm is based on that. Bayesian theorem. That's why data science is important. So learners who have done data science should be clear about the Bayesian theorem. Conditional probability or the posterior probability is equal to the likelihood function, that's opposite. What is the probability of event B given A into the prior probability A divided by the marginal probability? Do you remember this point or not? No? Posterior probability is directly proportional to the likelihood function. You understand this or not? Into prior probability. Okay. So the naive-Bayes classifier, this is the formula that if I have these random figures or, shapes, the classifier is capable of classifying them into different shapes or groups, right? And the basic formula lies in that the posterior probability is directly proportional to the likelihood function into the class prior probability divided by the predictor prior probability, right? So how is this, posterior probability actually calculated? It is nothing but the product of the likelihood function. Do you see this? X1, my first input given C, Px2 given C, Pxn given C into the class prior probability. So the products are generally written, the summation, not the summation, but the products are written in terms of pi and summations are written like this. Clear? So how is this particular, algorithm useful? Let's understand it practically with the help of an example. So suppose this is my categorical data where I have my inputs also as categorical: outlook, temperature, humidity, windy. And based on these factors, I will decide whether I will go for play or not. Play over here, again, it's a binary classification problem because I will go to play or otherwise I will no. So the outputs are yes and no. See, what is C over here? That my output probability whether I will go to play or not. Clear? Right? Now, if this is my input, okay, these are my input values: output, temperature, humidity, and wind. This is represented as my X1, X2, X4. Got it, learners? So what could be the values of the outlook? Outlook has three outputs, whether it could be sunny, whether it could be overcast, or it could be rainy. Are you understanding the three categories of outlook column? Then the temperature can be hot, cool, or mild. Again, three. Humidity can be high and normal. I don't think so there is any other category. And windy, again, two, true and false. Clear? So how do we go about calculating whether we will go to play or not? So what is my C1? Yes, I will go to play. Suppose I want to calculate, yes, I will go to play, given the humidity, the outlook, the wind situation, and the other one was temperature, right? So this becomes my formula. And once I separate them, as I told you, they become the individual products of probability. This formula is getting clear to everybody. We just now understood based on Bayesian theorem, mathematics behind this particular theorem. Okay. So how do we go about it? What is the probability of going to play when it is sunny? That is the situation I want to check. Hot, high, and windy. So from here, I can calculate the probabilities of sunny, hot, high, false, and no. Then the other one is sunny, hot, high, true, and no, overcast. So based on the given data, I can calculate the individual probabilities and put into the formula and finally get the output. Now clear, learners? How are we going to predict whether you will go for, and this is the algorithm which is practically used to determine whether the email is a spam or not. Email is a spam or not is used, actually the naive-Bayes classifier is used for that. Getting my point? So the advantages of naive Bayes is simplicity and speed. Naive Bayes is computationally efficient, very good algorithm. This algorithm is simple and also gives good result. So naive Bayes is computationally efficient and straightforward to implement and making it suitable for large data set and real-time applications. And it is also effective with small data, performs well on small data sets when the number of features is high relative to the number of samples. Got it? But every algorithm in machine learning will have its pros and cons also. What do we mean by pros and cons? That then we have to decide, okay, on this data set, this algorithm is giving good result, or this data set with looking at its advantages and disadvantages. So the assumptions of independence assumes that the features are independent given the class label, which is often not the case in the real world data, leading to potential performance issues. What does it, assume? So naive actually means that all the inputs are independent of each other. Poor performance with correlated features can perform poorly if the features are highly correlated, as the independence assumption does not hold good. Getting my point? So the naive-Bayes classifier is clear that why statistics, why probability are heroes in machine learning. Okay. So what is naive Bayes? Naive Bayes, it's not naive, somebody says naive Bayes. So naive Bayes is a probabilistic classifier, completely based on probability. Even the previous one was based on probability, right? And it is based on Bayesian theorem. Naive Bayes is called naive because, why the word naive? Because it assumes that the input variables are independent of each other. This is what it means. And this is a strong assumption and unrealistic for real data. It is particularly suited for large data set, widely used for binary and multi-class classification tasks. It is widely used for text as well as sentimental analysis. Lot of practical use of this. As I told you, even you can check on mail, the spam filtering is based on this particular theorem. So what is the mathematical concept? It's based on Bayesian theorem that the posterior probability is directly proportional to the likelihood function into the prior probability. Clear? The mathematically, with an example, I made the point clear. Let's do it practically. So we are running the same data set, breast cancer data set. So what are we doing over here? Who's going to explain me the code? Line by line. Yes. What is the first step? Come on, let's see. Who is the smart one, attentive one, and quick to answer in the batch? Let's see. What is the first point? What does the first line of code do? Importing library from Scikit-learn. Now we want to create naive Bayes classifier or Gaussian NB. Second, what are we doing in the second step? What are we doing in the second step? Defining pipeline. Very good. And what are we trying to do in this pipeline? Two-step pipeline. What are we trying to do? Feature scaling and not model selection, do model creation. We are trying to build a model, not model selection, but model creation. The last step, this last, what are we trying to do or achieve over here? Training the model, fitting the data, both are correct. Okay. Now tell me what is happening over here. Predicting the Y output, predicting the test output, training as well as the testing output. Agreed? Predicting both the training, input training and testing. Based on that, I'm getting my output training and output testing. Accuracy score, we require output training and predicted, output testing and output predicted, and calculate the training and the testing score and then check the prediction of the probability. So if we compare it with logistic regression, is it better than that or not better than that? Tell me. Compare it with logistic regression, the training and the testing accuracy. It's slightly towards overfitting, right? Slightly. But logistic regression was better, or is this model better? Now, this was better or that? Here, the training was 98 and testing was little less than that. But they were almost equal. But in Bayes, it's 93 and 96. Of course, logistic regression has given better results than naive-based classifier. Now clear, Abhinetri? And that is how judge or test. Okay, now this algorithm is better than that. How is this overfitting? Testing accuracy is better than training. Isn't it? This one. In this case, check this one. When the training error, see, actually the training error is less and the testing error is very high. Or when is overfitting? When the training error is less and the testing error is high. So in that case, that is the situation. Check the naive Bayes result. All right. So the training accuracy is 93.63%. Testing accuracy is this much, are relatively close to each other. This suggests that the model is not overfitting to the training data. Agreed, Puneet. Good. As the performance on the training set is slightly higher and comparable to the training set. Good, Puneet. So you corrected that particular point. Yes, it's not overfitting. Good, Puneet. Right? So this is how we get the predicted probabilities and the actual probabilities, do the comparison. So the naive Bayes classifier computes the probability of the class given the input features by multiplying the individual conditional probabilities of each feature, as I've told you. Internally, many naive Bayes implementation use logarithms to prevent numerical underflow when multiplying many small probabilities. The extreme values observed might be result of the conversion back from log space to probability space. So here internally, a lot of conversions take place. That is why it is e to the power minus 0.9 and plus 9, because a lot of conversions take place from logarithmic space to probability space. Got it? But the ultimate decision maker is the confusion matrix. Right? So here, this is my true positive, true negative, but my error is 3 and 1. Have my, the type 1 and type 2 errors also increased. Type 1 and type 2 errors also increased. Have my type 1 and type 2 errors also increased? Then logistic regression, do the comparison and let me know. And is my overall accuracy F1 score better? Yes, the errors have increased. Has the accuracy decreased? Yes. F1 score only for 0 is 97%, other is 95, 96%. Got it? And if I look at my AUC ROC curve, so this is again 1 and my optimal threshold is 0.0126. Getting my point, learners? Clear? So what do we observe by the ROC AUC curve? The ROC, I'm sure, most of you have still not understood what does it tell. The ROC curve for the naive-based classifier demonstrates outstanding performance with area under the curve of 1.0, indicating perfect classification ability on, like it's perfect. That means there is no overlapping. Whichever data belong to the benign, they fall under benign, they have been predicted as benign, and whichever which fall under malignant cancer, they have been put into malignant database. So this simplifies the model, is highly effective in distinguishing between benign and malignant cases with no errors. Optimal threshold is 0.0126. Some models such as naive Bayes often produce uncalibrated probabilities that tend to be extreme. This result in needing a very low threshold to balance sensitivity, specificity explicitly. Now clear? Is this point getting clear to everybody? Good to go? All right. So KNN. KNN stands for K nearest neighbor, and it is simply based on the concept or logic birds of feather flock together. What does that mean? The data points which are near to you, you are likely to be like them. Agreed, learners? Agreed? And how do I calculate my neighbors? With the help of distance, how close they are to me. How do I check the proximity of the data points? So the data points who are near to me, I'm likely to be like them. So the calculation of distance between the 2 points. So mathematically, what are the different ways to calculate distance between 2 points? Tell me, what are the different ways? Euclidean distance, Manhattan distance. Yes, these are the methods in which we calculate. Now, please look at over here. Now, suppose I see again, machine learning is all about prediction. So there are different ways. Every algorithm is using different way to predict what a particular data point is. Right? So if this is the question mark, we want to predict what this question mark is. How do we go about it? I'll try to analyze the neighbors around it. So suppose if I try to calculate 4 neighbors, how will I predict that what this question point is? Maybe the points which are more near, I will predict that. But if we talk about probability, there are 3 over as stars and 3 as triangles. So we never take the number of neighbors equal to the number of neighbors k equal to even values. Getting my point? We never want to take them as even values. Right? So generally the k is taken as odd, that is taking 3 closest data points, and based on this, there is 1 star and 2 triangle points. So chances are that this question mark is a triangle. Right? Whichever ones are with maximum probability. Simple algorithm. Yeah. So here we are going to predict a data point based on our neighbors. Okay, Abhinetri. So if I take even number of neighbors like 3 stars and 3 odds, right? How will I actually predict this data point? So the probability of number of stars is a 3, and this is also 3. So again, I will not be able to decide correctly what this data point is. So generally, K stands for number of neighbors. We want to keep it as odd value. So now when I predict based on these Based on these three data points, the question mark, so the triangle has more probability than the star. So the question mark we will predict as triangle. Now clear? Simple logic, right? So again, let's put it over here. If I take k is equal to 1, the nearest data point is red. So I can simply say that this particular question mark is red. But if I take k equal to 3, then, since there is one red and two blue values, it becomes blue. And if I take k equal to 4, the number of neighbors as even, then the classification is not properly defined. Now clear? So that is what I want to say, that k is never taken equal to even values. We always want to keep it as odd. Now clear to everyone? And the different types of distant functions. So when we are defining the KNN model itself, how are we defining the KNN model? First, we will import its library, call its function. So whenever we are defining the KNN model, we can define the type of distance we are using to calculate. So whether it is a Euclidean distance, Manhattan distance, or Minkowski distance, that we need to take into account. So different formulas are there mathematically. Clear? So now what are the different steps that are performed in KNN algorithm? The first step is choose the number of k neighbors. How do we choose the number of k neighbors? Randomly. Start with randomly assigning the k numbers, or they can be another technique which we have studied in regression to find out this value of k. Anybody who can tell me? Any other technique that we have studied in regression which can help us? Absolutely correct. Cross validation can again be used to find out this technique. Very good, Ajay. Then we calculate the Euclidean distance of k, the number of neighbors. Get the k nearest neighbors according to the calculated Euclidean distance. Out of these k neighbors, determine the number of data points in every category. 5. Give the new data points to the category that has maximum number of neighbors. And finally, the model is ready. Getting my point, learners? So what is the effect of K? What is the effect of K in KNN algorithm? How do we decide when the model is underfitting or overfitting over here? Right? So it is this K which significantly impacts the model performance by influencing the bias and variance. So whenever the K is small, it will always lead to overfitting. And whenever the number of neighbors K is equal to large, it will lead to underfitting. And as very correctly said by Ajay, finding the optimal K requires balancing these effects, often using the techniques like cross-validation. So this will make your concepts even better because things keep on getting repeated and concepts keep getting more clearer. Got my point, learners? So what happens when the boundary k is equal to 1? Do you see I get a very complicated curve? It is like overfitting, but still they are still misclassification. And if I keep a large value, it's like a straight line, but it's like an underfitting. So how do we go about finding the k? Wherever there would be minimum bias and variance, that particular value of k will be taken. Agreed? Getting my point, learners? So the advantages are simplicity. It is easy to understand and implement. Non-parametric. So this is a non-parametric algorithm. Do we understand this term? Very, very important. Non-parametric algorithm means that it makes no assumptions about the data, making it versatile. If I talk about adaptability. It performs well with noisy data and complex distribution. Disadvantage, I've tried to cover advantages and disadvantages of all the algorithm, that it is computationally expensive. That is, the entire training set must be stored as compared, which can be inefficient. Choice of the K would be challenging because it significantly affects the performance, and sensitivity to irrelevant data, that each feature contributes to the distance, so irrelevant features can distort the results. Getting my point? All right. So can we get back to its practical implementation? Back to the file again. Distance computation should be done for each feature or combination of them. Each feature. Data point, it will automatically calculate for the predicted value and the feature beneath. Each feature. All right. So the KNN algorithm is a popular machine algorithm used for classification, and it relies on the idea that similar data points tend to have similar values or label. During the training phase, the KNN algorithm retains the entire training data set as reference. For predictions, it computes the distance between the input data and all the training examples using a selected distance metric, such as Euclidean distance or any other diagram. Now clear? So the steps are also clear. We will load the data, choose the value randomly, then find the optimal value of K on the specific data set using cross-validation. So for every point in the test data, what does it do? That's the question asked by Puneet Reddy. That it calculates the distance between the test data point and each point in the training data set using distance metric, right? Sort the calculated distance in ascending order. Select the top k closest data points, smallest distances from the sorted list. Assign the most frequent class among these k nearest neighbors to test the data point. Clear? Is this point getting clear to everybody? So what are the first steps that we will be using for implementing on KNN? That what we would do, we would import the libraries KNN, define the pipeline for standardization and model, right? And now where is the difference? Please look here. What are we explicitly defining over here when I'm creating the KNN model? Yes. So when we are creating the model, we have to first initialize the neighbors count. So here we are taking 3 neighbors randomly, then fitting the data and then predicting the value. Clear? Creating any object, and if you want to find anything about it, it's very clear that you can just put a question mark, introspection. By default, the number of neighbors, if you're not specifying, it will take it as 5. And the metric parameters, by default, the distance metric it uses is Minkowski. Clear, learners? Okay, so now if we look at the accuracy, the training accuracy is again, but the testing accuracy should be even higher than the training, right? That is going to be a good model, but it is lesser than that. Agreed? So the error over here of the testing error is more than the training, right? Now I'm saying it correctly. Now is it correct? The testing accuracy should be higher than the training. No, that was a good point, because I was interpreting it in that way. So accuracy. So is it a good model or a bad model? Not very good, because the testing accuracy should definitely be more than the training, right? If it has to be a really good fit. So not a very good fit. Testing accuracy is higher than training. So it's a little overfit. We can say now it's a little overfit. Agreed, learners? So let's see what does the observation have to say. So this is how it's predicting the output. This is my confusion matrix. Oh, so what do we observe? What do we observe? And we are not getting the accuracy also very good because the testing accuracy has reduced. And what do I observe in the confusion matrix? Now you tell me. What do I observe in my confusion matrix? The errors have increased, both type 1 and type 2 error. And it very clearly shows on my classification report that my precision, my recall all have reduced, and overall average has also reduced from 97-98% to 95-94%. Right, learners? And let's look at the ROC AUC curve. And the ROC AUC curve is not giving me full one. It has reduced to 98% with optimal threshold value equal to 0.33. So now you will be able to iterate algorithm and see which algorithm is best. So it's an iterative process. Okay, let me apply this algorithm, that algorithm to finalize it. So the ROC curve has a steep ascent to high true positive with low positive, false positive rate, indicating the classifier is affecting and distinguishing between positive and negative classes. Now, hyperparameter tuning in KNN. So what is the best way to find out the value of K? By using hyperparameter tuning along with cross-validation. So the concepts that we have studied are all applied in supervised learning. Getting my point, learners? Yes or no? So the number of neighbors is a crucial hyperparameter in the KNN algorithm. It specifies how many nearest neighbors this algorithm should consider when making prediction. The selection of K impacts the model's ability to generalize effectively. A smaller K can make model sensitive to noisy data, that is overfitting, and high value of K can cause underfitting. So how are we going to do grid search and cross-validation? So sklearn model selection part has grid search CV function also. Now, how do I define my parameter grid? Did we study this yesterday? So whenever we are doing grid search, we have to define the grid with the help of dictionary. Since there is only one hyperparameter, I will define the KNN ranging between 21. Since my data set is like that, so I can range between 1 to 21. Or if more you want to do, you can range it between 1 to 50, 1 to 100. Not more than that, right? Then I create my pipeline, and now I create a grid search CV object, pass the model pipeline, grid parameter grid, cross validation, the k-fold cross validation value equal to 10. And finally, I'm going to do judgment on the basis of accuracy, fit the data, and finally, this after fitting it, I will get the optimal K. So in grid search, if I use the parameter, best parameters, best score, CV results, I am able to distinguish between them. So the optimal number of neighbors is coming out to be 7, and the best cross-validated accuracy for that is coming out to be 97%. That is why it was not giving good result. Why? Why it was not giving me good result? Because what was the value of K which I had taken? What was the value of K initially? 3. Now clear to everybody? So how is hyperparameter tuning and cross-validation helpful to us? And if I see it graphically also, so wherever is my maximum accuracy, it is somewhere coming out to be over here. It was 7. Let me do the opposite way. So this is my maximum value. This is my around 7. Clear? So now you can again transfer this value to K and then check the accuracy results and score, and you will see definitely better improvements in the results. Here, so there is a lot more to study in decision trees and then support vector machines. So now let's start with decision trees. So lots of concepts that needs to be covered in decision trees. So what are decision trees? Like a tree, as we understand, has root, branches, and leaf. And a decision tree that is in computer science also has a root, branches, and leaves. But what does they technically mean? Anybody who has an idea? What do they technically mean over here? Now, root is always the starting node, right? A decision tree will always start. So a real tree is follows a bottom up approach, but a tree starts from top to bottom approach. So root always starts at the beginning. Then we start splitting the nodes, internal nodes. That is the decision node on which whether, your age is greater than 30, your salary is greater than 30,000. And based on that, we will, have the leaf nodes, whether you are eligible for the loan or not, right? Getting my point? Again, I am repeating, technically a decision tree consists of three main parts. One is a root node, internal node, as well as the leaf node. Root node is always the starting node. Internal nodes are the nodes in between which help to take decision, follow a graph or follow the rules. And then we have the terminal node, also known as the leaf node, which will be my output or the concluding factor. Clear? Is this point getting clear to everybody? So decision trees are a family of non-parametric supervised learning models. I explained to you today what does the term non-parametric mean. Please try to understand. Take help from Google or Companion, do search and tell me what do we mean by non-parametric models. Supervised, we understand that they would be training and testing and splitting. What does the term non-parametric mean? No assumption about the data or function that it is following a linear function or, sigmoidal function. There is no assumption. We start with the root node. There's no mathematical function involved. And which are the algorithms assume a function? Can you name few parametric learning, supervised learning models which assume a function that it is a linear, it is polynomial? Regression is all parametric supervised learning. Even logistic regression where we are assuming the function to be sigmoidal. KNN was parametric or non-parametric? Did we assume any function in KNN? It was non-parametric. There was no assumption about any function. It was all about K. K was the ruler which were deciding the number of neighbors and the output. Getting my point? All right. Another important concept. So there are a lot of concepts in decision tree. That is why, practically it is being asked a lot and a lot to be explored in decision tree. Okay. Then the terms, which are over here, we don't use the concept of confusion matrix to determine the output of classification. Here we talk about purity in classification tree. What do we mean by purity? That if the classes are distinctly classified, like the AOC ROC curve, that means if there is no mixture between the different classes, they are said to be pure nodes or with minimum impurity. So do not get confused like me between accuracy. So are they talking about purity or impurity? Try to just comprehend logically. So we want less impure nodes or highly pure nodes which are able to classify data points in each classes. Getting my point? Is this point getting clear to everybody? The to split at each node is made according to the metric called purity. So when we decide a decision node, how the split is going to happen, that's how a tree will be generated with help of these purity score, right? So when I say it is 100% impure, that is node split evenly 50-50. And if I say 100% pure, when all the data belongs to the single class, so then it becomes a leaf node, right? When it has perfectly defined a class, then it becomes the leaf node. Getting my point? So in order to optimize our model, we need to reach the maximum purity impurity. Are these terms getting clear to everybody, learners? See, it is all about red and green. If the red and green balls are mixed together, then it is said to be an impure class. It is very, very impure. But if I am able to separate the red and green classes or balls easily into two different classes, then they are supposed to be minimum impure classes. Are you understanding the term very impure and minimum impure? Minimum impurity means pure nodes. We are looking at 100% pure nodes, 100% purity in the classes. And there are different metrics available in decision trees to calculate the impurity. The most important impurity measures are entropy. Do we understand the term entropy? The randomness. When we have studied physics, the randomness, the heat part in data entropy, which is again based on probability. As I've told you, probability is a hero in machine learning for all classification problems. So it is minus of P class I total. What kind of probability it is? Conditional probability. So this refers to the conditional probability. Log to the base 2, P class I equal to total. Getting my point, learners? Other way to measure the impurity is the Gini index, which is again 1 minus summation of P class I total square. This is again based on conditional probability, or it could be the misclassification error, right? And it could be based on misclassification error, that is 1 minus max of probability class I given total. Then you would try to understand, ma'am, what is the difference? See, it is very clear that the entropy value will lie between 0 to 1, whereas the value of Gini index and misclassification lies between 0 to 1.5, right? Now, when I say probability, what is the entropy at probability 0 and 1? What is the value of entropy, Gini index, or misclassification error at probability 0 or 1? 0. Why? Because when the probability is 0, are we sure that that event will not happen? Do we have certain certainty in that? There is surety. Similarly, the entropy becomes 0 when we are certain, okay, there is no, red ball or green ball at that particular point. And are we also certain when probability is equal to 1? We are very sure that the event will happen. Yes or no? And we are very sure that the event will happen. Yes. So the entropy curves looks like this. You can use any one of them, but it gives you the same answer. But the maximum entropy or Gini index or misclassification error will be at probability equal to 0.5. So all the three show same behavior. So any of one of the methods or metrics can be used for classification. Okay. Yeah. So basically, what does entropy mean? It is a measure of the randomness in the information being processed. Higher the entropy, the harder it is to draw any conclusions from the information. For example, flipping a coin is an example and action that the probability provides is random. So entropy, we understand this is Hx represents entropy, lies between 0 to 1. It is highest as at zero point 0.5 and lowest as 0 and 1. And that is why we get this inverted U shape. This is the formula to calculate entropy, which is summation of minus pi log to the base 2 pi. So if you want to play golf, like, and now I want to check the probability. What is pi? The probability of an event I of state S or percentage of class I in the node of state S. So how do we go about it? Entropy is 5, comma 9. What is 5, comma 9? What is the probability of getting no? It is 5 upon 14. Agreed, learners? 9 plus 5. And what is the probability of getting yes? 9 upon 14. Agreed? Is this point getting clear to everyone now? And if I substitute this in this formula for yes and no, I get the total entropy for playing golf. What is the present current state? We are trying to find out whether we want to play golf. So there are two, internal states involved in it, yes or no. Mathematically, are you able to understand this concept or not, learners? What is going to be the entropy for multiple attributes? Ultimately, we have to look at the multiple attributes. So when I have to decide, we have to play golf. When the outlook could be sunny, overcast, or rainy. So how do I say what is my entropy for that I'm playing golf, and with the outlook as an input, taking one input at a time. So what is the probability of being sunny? Sunny is 3, comma 2 because of playing golf is yes and no. Probability of overcast is 4 and 0. And probability of rainy entropy is 2, comma 3. So now we understand how to calculate these. Probability of sunny with this, probability of overcast and probability of rainy that we are calculating over here. Clear, learners? So we get this entropy. So if you look at this particular example, right? Entropy before. Can anybody tell me how am I getting 7 and 6? How many data points, circle and plus symbols are there? How many plus and circle, blue circle symbols are there? Total 13. How many are blue circles? Circle is equal to 6. So the circle is 6 and the plus sign is 7 upon 13, right? Ideally, this should be complete. All should be plus sign. Ideally, this should be, all should be circles. But practically, we get this entropy. There are 5 plus signs and 1 circle, 2 plus signs and 5 circles. Now clear? So now this particular slide is also clear. Can you explain this slide? Can you interpret this slide? That what is the, at probability 0, look at the states of the classes. They are so distinctly classified. And the maximum randomness is at probability equal to 0.5. Right? Okay. Yeah. So now we have understood the different ways to calculate the impurity or the purity of a decision tree is Gini index, misclassification errors, and entropy. But it is ultimately the information gain. Please try to understand. Ultimately, it is the information gain or IG, a statistical property that measures how well a given attribute separates the training examples according to their target classification. So now it is the information gain. That means the maximum the information gain, that particular attribute will be chosen for splitting the data set. Clear? Then constructing a decision tree is all about finding an attribute that returns the highest information gain and the smallest entropy. So what are we always interested? We are interested in entropy before. What do we mean by entropy before? This. When the split has not happened, and then we calculate the entropy after the split has happened. Clear? So the information gain Tx is equal to entropy of the T, that is the parent, minus entropy of the Tx. So if I want to check the information gain of the previous example, that is play golf and outlook, it is equal to entropy of play golf minus that. So the information comes out to be 0.247. Getting my point? So do we want low information gain or high information gain? High information. High information gain, more purer nodes or impurer nodes? High information. What is the purity of the nodes in high information gain? More purer nodes. And similarly, Gini index is a cost function used to evaluate the splits in the data set. It is calculated by subtracting the sum of the squared probabilities of each class from 1. It favors larger partitions, easy to implement, whereas information gain favors smaller partitions with distinct values. So how do we create a classification tree? It's quite different from other model. That is why it is favorite questions among the interviewer. Now getting my point? And the recent algorithms are also based on decision trees. Okay? Yes. So classification tree, we calculate the purity of the node. First, how do we calculate the purity of the node? What are the different metrics? Entropy, it could be Gini index, any one of them, or misclassification error, right? Select the candidate for the split, calculate the purity of the data after the split, then calculate after the split also, then repeat for all variables. So we'll keep on repeating for all variables before and after. Choose the variable with greatest increase in purity or information gain. Got it? Again, it's an iterative process that we keep on doing on our input features. And repeat for each split until stop criteria is met. So let me explain it with an example. This is a very famous example in the domain of data science, the Titanic cruise. I don't know whether you've done it before or not, but it talks about the luxury cruise ship driven by demographic features. And here we've just taken a very small example part of it, that 10 people survived and 15 people died, and the total is 25. This point is clear? So what were the criterias of survival in Titanic, if you remember? What were the criterias? Whether you are a male or a female, female and children were saved more. Not named Jack, getting lifeboat. No, the criteria, the boats were given more to the females and kids, less to the males, depending on the class, not much on the age, but the class of the people, like did they belong to the luxury business class or the lower class? Yes or no? If you have sibling or not, all these concepts and criteria were taken into account, right? So if we look at the survival probability, it is 10 upon 25. Died is 15 upon 25. That's the criteria. So this is the Gini index for this. This is the entropy and this is the misclassification error. So I'm trying to give you comparison of all the three. So now when I substitute these values, the Gini index will always lie between less than, 0 to 1, it will lie between 0 to 0 0.5. And if we talk about entropy, it is 0 0.97. Clear? All three metrics are getting clear. So this is before the split. Agreed, learners? The survival and the death. Now let's understand the split based on gender. So the data that was given to us was that male, only 2 survived and died 13. And if we talk about female, I don't know where there's the survival gone. No, survived 8 and died 2. Here it is. Do you see this? Gender was a major criteria in the Titanic ship. Maybe you don't remember the movie clearly. Whatever was shown in the movie, right? So based on gender, now I have to calculate each of the impurity nodes for the male node and the female node. So if I look at the probability over here, that how many survived is 2 by 15. It is 13 by 15 in case of males. And in case of female, it is survived is 8 by 10 and died is 2 by 10. Agreed, learners? Right? So these are my male nodes. These are my female nodes calculation. Got it now? But ultimately, what do we have to calculate? What do we have to calculate? We have to do it for other attributes also. And then now we will calculate. Oh, Gini gender can also be calculated. Then entropy gender can also be calculated. And ultimately, we have to calculate the information gain based on this. So the information gain based on gender comes out to be this much. Then we can calculate the number of siblings on board. And do you belong to the first class, second class, or third class? So this is the table of comparison. We don't create any table. This is just to understand how the decision tree is working at the back end. Clear? With this example, I'm trying to make the point clearer to you. So based on the male and the female, this is how we get the information gain from entropy, information gain for sibling, information gain for 0.6. So which node should be selected? Which node should be selected based on gender, sibling, or class? Tell me. Based on gender. Right. So this is the maximum information gain. Got it? We're always looking at maximum information gain. So first split should occur on the gender, then on the basis of class, and finally on the basis of sibling. Getting my point? So a lot of concepts and decision trees. Agreed? Should I go ahead with more? That what are the different hyperparameters in tree? While creating a tree, we have to keep in mind the depth of the tree. This is said to be level 0, level 1. So that is why depth is equal to 1. This is 0, this is 1, this is 2, this is depth 2, this is 0, this is 1, this is 2, and this is 3, this is depth 3. Got it? So we should have maximum depth or minimum depth? Tell me. How do we decide the depth of the tree? What effect will it have? We should keep it maximum depth. If the depth is 100, we have to traverse 100 levels. Is it a good way, Abhinetri? Not really. No. 100 level will make it very, very complicated system. So hyperparameter means Not very less, not very large. We have to decide where we are getting the good results. So even, it doesn't mean that more depth will give you good answers. More depth will make the system more complicated also. Yeah, we should go up to maximum purity or 100% purity, but there might be cases when we have reached, a lot of levels and still we are not getting that purity. There has to be a criteria of stoppage of the depth of the tree. Okay, especially for complicated algorithms. And decision trees can also be used for regression problems as well as for classification problem. Be clear with that. It is used for both the technique. That is why it is a super hit in the market. The next, criteria is minimum number of samples to split, right? If the samples are less than 11, we will not do the splitting of the node. So one is the depth of the tree is a hyperparameter. What is a hyperparameter? We decide before training the algorithm. Second is minimum to 11, right? And the minimum number of samples to split. Yeah, if it is more than 11, then we will split. Now clear? Two criteria are clear. Third criteria is minimum samples per leaf. We will decide the per leaf criteria. So even if there is one sample per leaf, I am accepting it as a class. Now, getting my point? Is this point getting clear to everyone? Still a lot more concepts to be done and go. But in the meanwhile, let's go back and start working on it practically, and then we will cover it up. So we are on classification 2 PDF. I need to upload that. And what are the best ways to find the hyperparameters, learners? What is the best way to find hyperparameters? How did we find out the K in KNN? Grid search cross-validation. Hyperparameter tuning combined with cross-validation is the best technique to find out hyperparameters. So now let's get back to the code. So today, we are still on 4.1. We'll keep continuing 4.1 till we reach the end of it. Okay, so where is the decision tree? Okay. So what are decision tree? So when we look at the decision tree, it is a non-parametric. Now the term non-parametric is clear. Please try to understand. It is a non-parametric supervised learning algorithm used for classification and regression. And the term which is generally used for decision tree is CART. That is, it is classification and regression trees. So CART stands for classification regression trees. It is a hierarchical tree structure. What are the three components of a decision tree? The root node, the branches, the internal nodes, and the leaf node. What do we mean by root node? We only have one root node, that is the starting node. Then we have the branches, the different internal nodes to take decisions, like we saw in Titanic example, based on gender, based on the number of siblings, based on the class, we are going to take the decision. And what is a leaf node? What is a leaf node, learners? The ending one. Actually, the output or the classes. So decision trees can be used for classification, regression tasks, providing easy to understand. This is clear. The root node part is clear. Decision node, the root node, the leaf node. Now that part is clear. So let's understand it with an example. Suppose if you want to buy a car, if the car of the color is red, then you will check We'll check the model is greater than 2015. If it is yes, then I will buy. Otherwise, I will check the mileage. If it is not, then I will buy. Otherwise, don't buy. So what is this decision tree doing? Is it a classification problem or a regression problem? It's a classification. Which kind of classification? Multi-class binary classification. Binary, because we are taking a decision whether we will buy the car or not buy the car. Exactly. And if the color is white, then we will check if the car is equal to Harrier, then we will buy it, else we will not buy. So how does the decision tree work? Please read this. How does a decision tree work? Creating decision tree involves a series of steps aimed at systematically breaking down the data set. So what are important? First, selecting the best attribute, and that is completely based on information gain. How do we select the root node of the best attribute? With those attributes are selected with maximum information gain. Agreed? Is this point getting clear to everybody? Then splitting the data set. The data set is then divided into subsets based on the value of the selected attribute. And then we repeat the process. The process is repeated recursively for each subset, creating new internal nodes or leaf nodes until a stopping criteria is met, or till the depth is decided and the different hyperparameters are decided. So the metrics which are used for splitting, do we understand what are the metrics used in decision trees? Tell me, learners, what are the different metrics used in decision trees? It is the Gini impurity. It is the measure of impurity or disorder in a set of elements commonly used in decision tree algorithms. This metric measures the likelihood of incorrectly classifying a randomly chosen element if they labeled according to the class distribution. And what is the range of Gini impurity? It will lie between 0 to 0.5. Entropy, it quantifies the amount of uncertainty or impurity in the data set. The values lie between 0 to 1. And information gain is the metric measures that reduction in entropy or Gini impurity after the data set is split on a given attribute. Clear? Is this point getting clear to everyone? All right. Now, what are the advantages and disadvantages of the tree that you have understood? Our trees are good example if they follow non-parameterized approach. That means no assumption about the function. Okay. It's interpretable. Is our trees easily interpretable? I can easily find out why I'm not buying the car or why I want to buy the car. Are they easily interpretable? Yes. So they are simple and interpretable, versatile, because the trees can be used for regression as well as classification problem. No feature scaling is required, right? In decision trees, we do not use standard scalar or normalization method on the data, and it handles non-linear relationships also. So they are capable of capturing and modeling complex non-linear relationship between features and the target variable. Got my point? Moving ahead with disadvantages of decision tree. The biggest disadvantages, yes, that's why looking huge. The biggest disadvantage of decision tree is overfitting. What does overfitting mean in decision trees? That they are able to learn the noisy data also, particularly if they grow very deep with many nodes. Instability, small changes in the training data can result in significant differences in the structure of the tree. Bias towards features with more levels. Attributes with greater number of levels can disproportionately influence the tree structure, potentially leading to biased results. As I tell you, every algorithm will have its advantages and disadvantages. It is completely you as a user who will decide the hyperparameters and the results, whether you will accept the results or reject it. Getting my point? So the errors are even more than the other. That's why decision tree looks huge, right, Ajay? Okay. Still lot more to be done in decision trees. Yes. Huge topic. Yeah. Now let's get back to the next part of it, that is pruning. Yeah, so we are getting huge big trees, and the huge big trees will take are complex, they are difficult to handle. So can we cut off the extra branches? Yes. And cutting off the extra branches in the tree so that it's not so complicated, it's not so huge. That concept is known as tree prune. Getting my point, learners? So are you understanding how the tree is getting bigger and bigger? Yes. So an overfitted tree captures noise and it becomes very, very complex. And a prune tree, that means cutting off the extra branches, cutting off the extra information, is much more simplified and generalized better. Getting my point? This point is getting clear. Do you see the difference? We always start from the root node, and all these points have been pruned or cut off so that we are able to get a more simpler and a better generalized tree. Right? Clear, learners? So there are two types of pruning, pre-pruning and post-pruning. What is pre-pruning? Before we build the whole tree, we will pre-prune it. We have decided the depth, that we will not go beyond the 10th depth or 10th level depth of the tree. Post-pruning is build the whole tree and then cut off the extra branches. Getting my point? Understanding pre and post, let me see. So tree pruning example, this is post pruning. This is an unpruned decision tree that is fully created. But after creating the tree, we cut off this particular branch, and then this becomes my pruned decision tree. Getting my point? Pre-pruning. A pre-pruning tree is a decision to stop growing the tree early. We stop the tree beforehand, and it's not necessary that it should be a fully grown tree. Right, Puneet, Atul, Anush, it answers your query, right? It's not necessary. We will always go till the end of the node and keep on creating more depths or branches. So how do we, okay, post pruning? See, this is pre-pruning. A decision stops growing the tree early. We have decided the criteria to stop it. And post pruning is build the tree and then use your criteria to cut it off. So how do you prune a decision tree? Pre-pruning, of course, which are the parameters which will help us? The hyper parameter will help us in the tree, or the pre-pruning is also known as early stopping of the tree. Which are the different hyperparameters in decision tree? What is going to be my maximum depth, the minimum samples per leaf, the minimum samples per split? All these things will be my hyperparameter. So there's no one parameter, three parameters: maximum depth, how many number of samples per split, and minimum samples per leaf. Got my point? So these are same parameters and can also be used to get a robust model. However, you should be cautious as early stopping can lead to underfitting also. So we again always have to keep in mind that the model should not be underfitted. Also, it should not be overfitted. Agreed, learners? So post-pruning does the opposite of pre-pruning and allows the decision tree model to grow to its full depth. So once the model grows to its full depth, tree branches are removed to prevent the model from overfitting. So if we are pre-pruning, doing early stopping, the model can suffer from underfitting. And in post-pruning, the model can suffer from overfitting, and that is why we prune the. Got it, Dr. Henry, Roshan, Kalpana, Atul, Anush? And the parameter, one more hyperparameter to go. The hyperparameter that can be tuned for post pruning and prevent overfitting is CCP alpha. CCP stands for cost complexity pruning. So we have to always take into account the cost which is going to be there to perform the action. That can be used as another option to control the size of the tree. A higher value of CCP alpha will lead to an increase in the number of nodes pruned. So essentially, pruning recursively finds the node with the weakest link. What do we want to delete? How are we going to start, decide the cutoff criteria? Nobody asked me that. When we are doing post pruning, of course, and that was early stopping, how do we decide the criteria for pruning? We have to calculate the weakest link. That means the node which has least effect on the whole decision tree. The weakest link is by effective alpha, where the nodes with smallest effective alpha are first. So mathematically, the cost complexity measure for the tree is given by R alpha t, that is RT plus alpha into slash t, right? So RT is the total training error of the leaf node. That's how the cost complexity for pruning is calculated, and T is the number of leaf nodes. Now clear? So this is an example I've given you, tried to explain as how regression trees work. So this is an original decision tree, and we are calculating the Guinea, the number of samples and value. So as we move ahead, there is no class as such, but numerical value which are there. And prune decision tree after alpha pruning, that some of the branches of this branch, you see, this branch has been pruned. Got it? Is this point getting clear to everybody? Got it, learners? Have you understood decision tree? You've still not practically implemented. Let's get back to the file. Yeah. Till here, are we clear? What are the advantages and disadvantages of the tree? Yes, learners, are you there with me? So now let's quickly run through the practical part of it. So what is pruning? If I ask you what is pruning, it's like regularization in prevent overfitting, decision trees can be pruned. It's like regularization of linear regression. Over here, we can call it as pruning. Okay? Right, learners? So pruning involves removing parts of the tree that do not provide significant power in classifying instances. This can be done in two main ways. Pre-pruning, that is early stopping, which halts the growth of the tree early based on stopping criteria such as the maximum depth or the minimum number of samples required to a split. And post pruning, now we are clear that the first it grows the full tree and then removes the data that adds little predictive power to reduce complexity and improve generalization. Clear? Are we clear with these points, learners? Okay. So using the same breast cancer detection criteria, first step, we import the Scikit-learn decision tree classifier, and then that scalar actually is not required, but since we are doing it in the pipeline, we do it over here. We fit it and then predict the output and accuracy score. So is the accuracy score good? What do you observe? Training accuracy is perfect. Testing accuracy is less. So is it underfitting or overfitting? Training accuracy equal to 1 definitely means it's overfitting. That how can a model learn perfectly, but it is learning perfectly over here. And when we see the predicted probabilities, we are almost getting the correct answer. So the please try to understand. There's a lot of significance in getting that one. Training accuracy indicates the decision model perfectly classifies the training data. This is a strong indicator of overfitting. Please be clear, Puneet Reddy, on this particular point. Where the model is too complex and it captures in the noise in the training data, resulting in perfect accuracy. Now clear? See, while still high is lower than the training. The testing accuracy is not low, but it is lesser than the training accuracy. And this difference indicates the model does not generalize well to the unseen data. Again, it is reinforcing that the model has overfitted. Clear? So if it is overfitted, does it require regularization? Yes. And how will we perform regularization here? Does it require pruning? Does it require pruning? So when there is a significant difference between training and testing accuracy, as seen in the training data at 1.0 and testing accuracy at 92%, it suggests the model might be overfitting to the training data. Cross-validation helps confirm this by showing how the model performs on different subsets of the data. The primary goal of cross-validation is to assess how well the model generalizes to the independent sets. A model performs well on cross-validated data is more likely to generalize well to new or unseen data. So how do we use the cross-validation? From Scikit-learn model selection cross-validation, I will use the pipeline, the training data and cross-validation equal to 5. And what is the score coming out to be? Why is it required to use cross-validation over here? Because the model was overfitting there, right? I got the training accuracy equal to 1. So what is this cross-validation score suggesting? That this is 91%. Please try to understand this concept, learners. It's very, very important and it will be repeated again. So this cross-validation scores are relatively consistent. That even after splitting or changing the different parts of the data, validating data with accuracies ranging from approximately 91.21% to 94.51%, this consistency indicates that the model is robust, performs well on across different subsets of the data. This confirms that it is not overfitting, that it is robust and it can perform well on the different subsets. Getting my point? The mean cross-validation score of approximately 92.31 suggests that the model generalizes well to the unseen data, providing a reliable measure of performance. And using cross-validation helps to ensure that the performance estimate is not overly optimistic or pessimistic, giving a balanced view of the model's effectiveness. Is confusion matrix also going to be a metric which will help us? Yes. So the errors are more. So decision tree has still not given good results for this particular, algorithm. And if you look at the F1 score, it's reduced further, 94% for 0, 91% for 1. And overall accuracy is also coming out to be 93%. Clear, learners? Are you there with me? Is this point getting clear to everyone? And ma'am, do we need AUC ROC curve? Yes. AUC ROC curve is giving me 93% of areas. In others, we were getting full 1%. So of course, it's not performing well as logistic regression or K-Naves or Nave Bayes algorithm, but it is 93% and the optimal threshold has come out to be 1. Okay. So since this model has been overfitting, can we apply pruning? Let's apply pruning also. Are you there with me, learners? Can we move ahead with the pruning of the decision tree? So by pruning a decision tree, we aim to improve generalization of the model, thereby avoiding overfitting. Let's apply pruning to the decision tree and then evaluate the model's performance. So we have CCP alpha is a parameter when we are creating the decision tree classifier. Accuracy came out to be 92%. Great, Anush. Which 92%? Which one came out to be 92%? This one. The this in classification report. Classification report. It's okay. So the decision tree classifier, we have taken the CCP alpha equal to 0.01 with random state equal to 42. And then we have using the cross validation score also when I have seen the pipeline pruned. Now my pipeline has changed. Why? Because I have set the the cost complexity pruning factor equal to 0.01, giving the training data with CV equal to 5. So now when I check my pruned accuracy, mean CV is 92%, and now the training accuracy is 98%. So definitely overfitting has reduced. Agreed? Now it's not overfitting. Right, learners? Do we see that? Yes, learners. Are we able to observe that this is the prune decision tree is giving better results? And now if I see the confusion matrix, the overall results have also improved. Classification report. Everybody is able to observe this. And now look at my ROC AUC curve. The area from 93% has improved now to 94%. Agreed, learners? So pruning the decision tree has successfully reduced overfitting, and that is what we wanted, as indicated by the reduced training accuracy and improved testing accuracy. The prune model shows more consistent cross-validation performance, indicating better stability and generalization. The overall classification metrics remain high, demonstrating that the prune model maintains strong performance while avoiding the pitfalls of overfitting. And we have also understood the hyperparameters tuning in decision tree. What are the main hyperparameters? And what is the importance of hyperparameters? That they are crucial in improving the performance of the model, right? So maximum depth, what length or depth we want the tree to be. Minimum number of sample splits, second. Minimum sample leaves, and maximum features, the number of features consider when looking for best. CCP alpha for pruning is also a hyperparameter, and the criteria, the function to measure the quality of a split is also a criteria. So 6 hyperparameters to be considered when we are, creating decision trees. Getting my point, learners? Are the 6 parameters clear to everybody? Parameter tuning technique, as we have seen. Grid search is an exhaustive search technique. Well, there are too many parameters over here. Along with cross validation can be used, or a random search over a specified parameter grid. So if we look at the parameter grid, do you understand what is a grid? We always define the grid in terms of dictionary. So this is the maximum depth that I want to keep for my tree, none, 10, 20, 30. The maximum depth of decision tree, if none, the nodes are expanded until all leaves are pure. Full expansion of the tree until all leaves contain minimum split sample. Specific values 10, 20, 30 limit the depth of the tree control to its complexity and preventing overfitting. Minimum sample splits 2, 5, and 10. Again, higher values prevent model from learning overly specific patterns by requiring more samples for a split, and minimum number of leaves, the maximum features, the alpha value. So if we look at over here, now I've imported grid CV cross validation, created a pipeline of it, and now I define my dictionary of different parameters. How much could be my maximum depth, the sample number of splits, the minimum samples per leaf, the maximum features, square root, or log 2. What do we mean by maximum features? The number of features to consider when looking for the best split. Is it consider all features, take the square root of it, or log base 2 of it? Okay. And then we do the grid CV search, fit it, and then find out the best parameters. So the best parameters, alpha comes out to be 0. That means no pruning is required. Maximum depth is none. The maximum features is log 2. Minimum number of leaves is 1. And minimum number of sample split is 2. So the best cross-validation score is 94% and accuracy is 95%. So it is higher, so it is giving you much better results, and there is no overfitting of this decision tree, right? Point getting clear to everybody. So we are not able to do the support vector machine. It again requires a little more thing, but I think so the decision tree, was long explanation. A decision tree consists of a root node, internal nodes, and the leaves and the branches. We always start from the root node, move towards the internal nodes, and then we have the leaves, right? And what is the important metric? We need to calculate the purity of the nodes, how well the classes have been classified, right? The purity. So what are the different ways? What are the calculation metrics used for purity? entropy. It's not entropy, Roshan. It's entropy. So entropy, Gini index are the two. And ultimately based on the information gain. So whichever node has maximum information gain, that metric is used to create the decision tree. How do we avoid overfitting in decision trees?
Yeah, it is tree pruning. The two types of pruning are pre-pruning and post-pruning. That means we cut the tree before the tree is not grown in its full length. It is depending on the depth of the tree, right? And the other one is post-pruning, where we create a complete tree and then try to cut it down. Clear? So what are the different hyperparameters of a tree? I think so we discussed that, but quickly we'll start discussing that. And today we have to do support vector machines and do multi-classification algorithms also. Yeah. Imbalanced classes if possible. Yeah. Yeah. It is the depth of the tree. Then the other one is the number of leaves per split, right? The number of split that we can calculate in per class. So how do we calculate hyperparameters? Hyperparameters are those parameters which are user defined. We define their value. So what is the best way to find the hyperparameters? Hyperparameter tuning. What are the two methods of hyperparameter tuning? Grid search, CV, or the random search. What is the difference between grid search and random search? Grid search performs all the combinations of parameters and randoms rules selects randomly. So grid search is an exhaustive search algorithm, right? So grid search is one of the hyperparameter tuning technique in which different hyperparameters are taken and then we decide which model, which combination of the hyperparameter model gives us the best result. Getting my point? Right? So what does this particular diagram represent? What does it mean? Let the tiny circles represent different hyperparameters and we begin with one value of hyperparameters to train the model. So, right, when we start training, we take one set of hyperparameters and train the model. Then we use different hyperparameters to train the model. We tend to continue the method until we have exhausted the various parameter values. So continuously, whatever permutation combinations can be formed, this is what we always try to do. Got it? Every model produces an error. We pick the hyperparameter that minimizes the error. So that's the whole trick of machine learning, that we will always choose those parameters, hyperparameters that will minimize our error. To pick hyperparameter, we split our data set into three parts. What is this concept known as when we split the data set into three parts? The training, the validation set, and the test set. Cross-validation. So we tend to train the model for the different hyperparameters and we use the error component for each model. We select the hyperparameter that minimizes the error or maximizes the score on the validation set. After that model has been picked or hyperparameter has been finalized, in the end, test our model performance using our test data. Clear? Right? So if we talk about decision trees, this is the parameter, please try to understand in grid search, we always write the parameter in terms of dictionary. Okay. So this is the criteria. This is the range. First is which criteria are we using to finalize the internal node? Are we using the Gini or the entropy method? Maximum depth, we want to range it between 1 to 10 level, right? Or 1 to 9 level. Minimum number of sample split is 1 to 10. And minimum number of sample split is also range from 1 to 5. This point is clear? So the grid search CV over here, grid search cross-validation is always carried out, in which the data set is divided into training, validation, and testing. Training and validation is used to find out the best hyperparameters. Is this point getting clear to everybody? So the colorful balls are representing these hyperparameter. This is the function in which we are doing a grid search on the decision tree. Parametric grid, this is the grid we are passing. Cross validation, we are using 10 times, verbose 1. N underscore jobs equal to -1 helps us to, utilize all the cores which are there in the hardware. And grid.fit trains the data. Clear? So how do I know the best parameters? By using grid.best underscore params underscore. Criteria is grid. Maximum depth is 9. Minimum sample leaf is 3. After doing or running the algorithm, cross-validating it, these are the best result that we get. It is Gini index 9, 3, and minimum sample split is 7. And the best estimator is this, with maximum depth with this much, minimum number of sample leaves this much, minimum sample split 7. So the best score which has come out after applying these hyperparameter is 82.94%. Clear? And what is the effect of hyperparameters? The maximum depth limits the number of levels in the tree, preventing it from becoming overly complex. So this prevents overfitting. Low depth may lead to underfitting, where the model fails to capture the complex pattern. Maximum depth, or I would say large values of depth, high depth can lead to overfitting, where the model learns the training data too well, including noise, and performs poorly on the unseen data. Example, maximum depth is equal to 5. This would restrict the tree to a maximum of 5 levels. Minimum number of samples split specifies the minimum number of data points a node must have before a split is attempted. It impacts the complexity of the tree by preventing splits in nodes with very few samples. All right. And then we have minimum samples per leaf specifies the minimum number of data points a leaf node terminal node must have. Why it is important? Because it helps to prevent the overfitting by ensuring the leaf nodes are not too small based on limited number of samples. Clear? The impact is also there. And then we have the maximum leaf nodes purpose limits the number of leaf nodes in the tree. Similar to the maximum depth, it helps to control the complexity of the model. For example, if maximum leaf node is equal to 10, limits the tree to maximum 10 leaf nodes. Clear? Are the hyperparameters clear? So we are very clear with decision trees now. Okay, now let's quickly do the knowledge check. First question, what is the assumption of naive Bayesian classifier? So a quick revision of different algorithms. First question, what is the assumptions of naive Bayesian classifier? Yes, it is C that all the input attributes are considered independent of each other and the model is considered to be generative. Second question, which one of the following application is not an example of naive Bayesian algorithm? Tell me. Naive Bayesian algorithm is used for classification, not for regression. Yes, it is stock market forecasting. Which of the following statement is false about k nearest neighbor algorithm? Again, the answer is C. Yes, the answer I think is C. It cannot. It can be used for regression. Next, consider the figure if a person A starts driving at 8:30 a.m. and there is no other vehicle on the road. The another person B starts driving at 10 a.m. and there is an accident on the road. What will be the commute time of A and B respectively? Yes, the answer is again C. So all answers are C. What is entropy in context of decision trees? So that answer is A. It measures the disorder or impurity in a node. Absolutely correct. In a decision tree, what is the purpose of the leaf nodes? Yes, it helps us to represent the class label or class value. Next question, which of the following is a disadvantage of using decision trees for classification tasks? It is B, that decision trees are prone to overfitting. If they're computationally expensive, then you have to avoid the depth, right? So B is the better answer, not D. All right. Next question. Given entropy for a split, E split is equal to 0.39 and entropy before the split, E before is equal to 1. What is the information gain for the split? So information gain is equal to before minus after. So 1 minus 0.39 is C. Clear? So here we go in with support vector machine. It is also one of the very, very important algorithm which helps in handling non-linear data, right? So again, it leads to the problem of classification if two classes are really far apart from each other. Example which I generally take is, I don't know how much relevant it is in today's world. The boys' hostel and the girls' hostel in a university are well separated from each other, right? So now the question is, which linear straight line, divides the two classes in a pretty well? Is this the line I should consider? Or this is the line? And it's not about line, it is all about hyperplane. What is the difference between a line and a hyperplane, learners? What is the difference between line and hyperplane? Absolutely correct, Megha. Here we are talking about not one dimension. Hyperplane is in multi-dimension, right? Not always in three. It can be more than three also, Kamal. Okay. So what is the best way to solve? No, not necessary. Plane is in 2D. Hyperplane is in higher dimension, Kalpana. You're wrong. Hyperplane is never in 2D. Planes are in 2D. Line in 1D, plane in 2D. And in higher dimension, it becomes a hyperplane. Okay, please be clear with that concept. So, taking the first two data points of this particular class, which are known as my vectors. Okay. Similarly, I'll take one vector this, one vector this, and try to pass a straight line. So two hyperplanes are being, created. One of them is known as a negative hyperplane, and the other one is known as a positive hyperplane. Are you understanding this equation also? This is nothing again, or this represent your linear regression. Why linear regression? It is your weights W naught X naught plus W1 X1 plus W2 X2. Getting my point? So this is WTX is equal to minus 1. This is the negative side. And the positive side is WTX is equal to 1. Right? And this is known as the center one is known as the decision boundary, which is equal to 0. So any points lying on this side belongs to this class. Any points lying on this side belongs to this class. And the margin is the difference between the positive and the negative, hyperplane. And what is our aim? Our aim to maximize this margin. That means we should be very clear and distinct that this class belongs to the positive hyperplane, and data points lying to this side belongs to the negative hyperplane. Clear? So why it is known as a support vector machine? Because over here we are using this concept of support vectors to draw the margins to deal them in higher dimension plane. Now clear? So again, I'm telling you, in two-dimensional, one-dimensional, a single line is represented with this equation. And when in higher dimension, the equation becomes WT. You would say, ma'am, what is this WT transpose? This is how I write my multiplication, or it is a vector of weights with dot product of these values, x1, x2, x3, xn. Now clear? Both represent the same linear equation. So again, we are clear. Here we want to maximize our margin. This is my decision boundary where it is equal to 0. And then we have the plane on this side. This is known as the negative hyperplane. On this side, this is known as the positive hyperplane. Getting my point? But in the real world scenario, do we have very strict margins that all the data points are going to lie on the on the left side of the negative hyperplane and all the data points are going to lie on the positive side? No. In the real world scenario, there is always mixture of data points. There can be a situation that some data points lie on the other side of the margin also. And on the other class can belong to the other class also, like the red data point. Right, learners? Is that possible? All right. So what is the hyperparameter over here? The hyperparameter over here is what should be the distance or the width of this particular margin. Ultimately, our aim is to maximize it. So the larger value of the C parameter makes this margin slower, or it leads to overfitting of the data, and small value of C gives maximum margin, that means well separated. Clear? What if there is data on the line of the decision boundary? Yes, we are coming. Oh, on this particular point. So it is completely up to us whether we want to put it on this class or this class. That's going to be our logic. That's completely depends on what logic are we going to implement in our algorithm. Okay. Okay. So Megha, I'll repeat. See, ultimately, we want to maximize this particular width, right? So there is this regularization parameter C, which will help. The larger value of C means the margins have reduced, and smaller value of C means the margins have expanded. What I'm trying to say is, how do we go about? So what does C become? C becomes my hyperparameter. Agreed? Which is going to decide the width of this margin. So if the value is lesser, this is maximum width. But is it showing a good margin? No, there is a lot of mixture of data points. Now, when I make C equal to 1, this is better. You know that there are certain misclassification, but it can be handled. When I make C equal to 10, it becomes even more smaller. And C equal to 100, it makes even more smaller margins. So C is known as the regularization parameter of the support vector machine, which manages the width of the margin. Right? But another C seems like lens. Yes, we can say that, we're trying to, adjust the width. But when we try to finalize the width of the margin, we also have to understand the different data points, right? How far are they, far are they from the different, the distance, the margins they are. So this is another hyperparameter of support vector machine, which is known as the slack variable. What is this known? This is known as the slack variable. Yes, C is a hyperparameter as well as this epsilon, also known as the slack variable. Right. So if we look at this, if we look at it, again, what is value of epsilon? If a particular data point belongs to the correct side of the margin, that means the epsilon is considered to be equal to 0. Right? If it is on this side, it is again considered to be 0. If it is on this side, it is considered to be correct. Right? And what is the case? If the epsilon is greater than 1, what does that mean? If it is greater than 1, that means a data point belonging to one class is now shifted to another class. So that means a data point is not classified correctly or is in the other class. Right, learners? And if it lies between 0 to 1, that means it is within the margin. Clear? Let's understand it in a better way. So the slack variable. So please try to understand in support vector machine, there are two hyperparameter. One is known as the epsilon, the slack variable, and the tuning parameter C. Okay. Slack variable epsilon tells us the location of the ith observation relative to the hyperplane and the margin. So what does it tell? The distance, location of the ith observation relative to the hyperplane and the margin. If epsilon I is equal to 0, then the ith observation is at the correct side of the margin. Clear? That means if epsilon is 0, there is nothing to worry. But if it is greater than 0, then the ith observation is on the wrong side of the margin and ith observation has violated the margin. If epsilon is greater than 1, then it is on the wrong side of the hyperplane. Then it is on the wrong side of the hyperplane. Now these three parameters are clear. So the tuning parameter C bounds the sum of the epsilon that can violate the margin as well as the hyperplane. So if C is equal to 0, no violations would be allowed. So tuning parameter C bounds it, the sum of epsilons that can violate the margin and the hyperplane. So if C is equal to 0, no violations are allowed. That means all the epsilons are equal to 0. But if C is greater than 0, no more than C observations can be on the wrong side of the margin. Clear, learners? And the other case is that if we have studied, if in an example is on the wrong side of the hyperplane, then epsilon greater than 1, then the optimization problem requires that epsilon should be lesser than equal to C. So there has to be tuning of the slack variable and the C in such a way that if C is greater than more, obviously C will be having some margin, not more than C observations can be on the wrong side. And if epsilon is greater than 1, then epsilon should be lesser than equal to the regularization parameter. So what does this mean? As we increase the value of C, a greater number of violations of the margins will be allowed and the margin will widen. That's true. As we decrease C, we will allow lesser number of violations to the margin. The margin is narrow. So How do we treat this? We treat C as the tuning parameter, which is chosen as cross-validation. So over here, something like this only. When C is very small, the margins are very, very high. And as the value of C is increasing, the margins gets reduced. But ultimately, it is through cross-validation, we find out the correct value of C based on the value of epsilon. How many wrong, classifications have been there? Is this example making things clear? Right? So there is this one violation happening over here and maybe one over here. That's it. Basically, what we are trying to do is we always want to find out the values of hyperparameter in decision trees, like it was the number of leaves per node and the samples per leaf, the depth, right? Here there are two parameters, C and epsilon. So over here, we want to find out that value of C where the number of misclassifications are less. Clear? So when the C value is less, this is the most widened hyperparameter. Right? So this is of course not a good choice. As the value of C is increasing, the margin is getting lower. And maybe at this particular position, we see it is at best with only two misclassifications in this particular case. Now clear? Now better? Another very, very important feature of support vector machines for which, support vector machines are mostly used, that's for non-linear equation. Now look at over here. This is a non-linear function which separates the two classes, the red balls as well as the blue balls. Is this polynomial function correct? Is it a simple function or a complicated function? Is it a simple function or a complicated function? Are we interested in complicated functions? No. Now, by increasing, and this is in two-dimensional plane. This is a two-dimensional plane. Now, if I increase the dimension, I am converting this two-dimensional data points to three-dimensional data points. But do you see the advantage? This complicated function now gets into a simple hyperplane, and then I am able to separate my red and blue points successfully. But ma'am, why are we increasing the dimension? We are increasing the dimension only in that case, only in one condition, when my function, mathematical function, is becoming simpler. It's not complicated anymore, right? So if these are my data points, right, and we understand this is my nonlinear decision boundary and we will apply the kernel, right? I have now increased it into three-dimensional space by applying some polynomial curve, radial bias curve, and now the beauty is that by using a simple hyperplane, I am able to separate the two data points. Are you liking the beauty of support vector machines? See, every algorithm is different because every data is also different. Every, every algorithm cannot be fitted on the same data. Getting my point? So what are the different types of kernel? So kernel again becomes my hyperparameter. Can I say that? Kernel again becomes my hyperparameter. Clear? So what is the idea? When we have non-linear decision boundaries, the two steps for generating non-linear decision boundaries are transform the original training input data into high dimensional data using nonlinear mapping. Once the data is transformed into new higher dimension, find the linear separating hyperplane in the new space. So if I have two variables, two dimensions, variable x1, x2, then this is the polynomial transformation terms, that is x1, x2, x1 square, x2 square, x1, x2. Clear? Clear to everybody? So now do you see this hyperplane? Yes, learners, do you see the hyperplane equation now? How are we converting it? Because now the x1, x2 have changed into these many variables. So what is the advantage? From this equation, we will get a non-linear decision boundary in the original feature space, and it is used up to second terms. Two features are expanded to 5 of degree term, third degree term, and 3 features are expanded to 9. Okay. So what is the advantage? So we can use the support vector classifier in the expanded space to solve the problems in lower dimension space. So what is the idea? That kernel functions are used to handle the nonlinear transformations of input data into higher dimensional. Yes, the disadvantage is that it may be computationally heavy. Kernel functions were introduced to avoid some of these problems. So therefore, support vector machine is an extension to support vector classifier, which results in transformation of input of data in a specific way using kernels. The main idea behind the support vector machine is to enlarge our input data so that we can accommodate non-linear decision boundary between the classes. So support vector machines are very good algorithm which help in resolving non-linear classification data. And the different types of kernels used are linear kernel, RBF kernel, the radial basis kernel. This is the iris data set, if you remember, right? So this is how it is. And then we have this polynomial kernel and sigmoidal kernel. Getting my point? So now let's quickly get back to the file. I think so. We were on which file in classification? Lesson number 4. First 4.1 only. We are still on 4.1. I think so. We are still on 4.1. Right, learners? Please start loading the data. So this is the breast cancer data set, right? Then we drop this app data and do the df.info. We have to do it till the split thing get does. Then we drop the ID also. This is the heat map. Yeah, then the label encoder. What is the use of label encoding? The output diagnosis, because two types of cancer are there, benign and malignant. And this is the splitting thing. And then we create the pipeline. Pipeline, we will create the support vector. Yes, learners, are you there with me? I have loaded my data set till there. Hopefully it should run. So it is the supervised machine learning algorithm used for both classification and regression challenges. Another beauty of support vector machine is that it can be used for both classification and regression both algorithms. It is mainly used for classification in support vector machine. The required straight line is to fit the data is called a hyperplane. The goal of support vector machine algorithm is to find a hyperplane in an n-dimensional space that distinctly classifies the data points. The closest data points to the hyperplane on the either side are called the support vectors, and the support vectors influence the position, orientation of the hyperplane, aiding in the construction of the support vector machine. So are we clear? There are two types of support vector machines: linear support vector machines and non-linear. Linear separates the data in a linear pipeline, and if the data is separated into using two straight line, it is linearly separable. And when it is non-linear, then we use the kernel function in higher dimensions to make it easily separable. Agreed? So sklearn.svm import svc. From sklearn.pipeline import pipeline, right? So pipeline, what is the use of pipeline, learners? Automating the process. We are trying to use two processes simultaneously, that is standard scalar and the support vector classifier. Training accuracy is 98.90 and testing accuracy is 98.24%. So can you tell me, is it a good fit, underfit, or an overfit? Very good fit, Almost the training accuracy and testing accuracy are coming out to be the same. Good, good. So you all understand this. So this is the predicted output we are getting. So support vector machines also perform well. And if we look at the confusion matrix, one of the errors have reduced to 0, other one is 2. So it will give us good classification report. Do we understand classification report? Yes. Almost all the scores, micro, macro, everything is coming out to be 98%. So support vector classifier or machine has performed very well on this data set. Agreed? And if I talk about the ROC AUC curve over here, it's coming out again to be 1. Right? And if I talk about different hyperparameters in support vector machines, tell me, what are the different hyperparameters in support vector machine? The kernel type, the regularization parameter, and the slack variable, the gamma. So in support vector machines, hyperparameters play a crucial role in determining the model's performance. Here are some key parameters typically adjusted in SVM. Kernel type. The kernel function transforms the input data into higher dimensional space where a hyperplane can be used to separate classes that are not non-linearly separable in original space, right? And the different kernel types are linear, polynomial, RBF, sigmoidal, right? C regularization parameter. Kalpana, are you now clear? The parameter trades off for correct classification of training examples against maximization of the decision's margin. A higher C tries to classify all training examples correctly. That means low bias, high variance. What is low bias and high variance? What is this condition of low bias and high variance known as? While lower C allows more misclassifications but pushes for larger margin, the larger margin leads to high bias, low variance. That means underfitting. Good. Gamma, this hyperparameter is used with certain types of kernels like the RBF, where it defines how far the influence of a single training example reaches. Low value means far, high value means close. The gamma parameter can be crucial in avoiding overfitting or underfitting in the SVM model. Clear? Low bias, low variance, good fit. Yes, Ajay, right. So now clear? We have understood major algorithms of classification. We started with logistic regression, Bayes, KNN, decision trees, support vector machine, and each method was explored through theoretical discussion and practical example. And we have taken one example, that is the breast cancer data set, so that the comparison between all the algorithms can be done. Clear? Yes. So what is multi-class classification? See, nothing over here. We will do the same algorithm, naive Bayes, KNN, decision tree, and random forest for multi-class, but we will be using on different data set. That is online gaming behavior data set, right? So what is multi-class classification? When the target variable has more than two classes, that is known as multi-class classification. So now let's look at this online gaming behavior. So multi-class classification is a type of classification task that involves classifying instances into two or more classes. Unlike binary classification, which deals with two classes, multi-class can handle problem where an instance can belong to multiple categories. Getting my point? Is this point getting clear to everyone? So a tree can be classified as a banyan tree, palm tree, or pine tree. So this is a class of multi-class, of course. So what are the algorithms which come except logistic regression? Logistic regression is the only algorithm which is used for binary classification. All other algorithms can be used for multi-class like naive Bayes, KNN, decision trees, and random forest. Clear? So now let's take this data set example with online gaming behavior. This particular data set on Kaggle is designed to analyze and predict players' behaviors in online gaming. It includes data on various aspects such as player identification, session duration in game, actions and purchases. The data set comprises several features that capture player activities and interaction within the game environment, providing a rich source of information for developing predictive models. So the number of instances is these many. 40,034 rows are there, and it has 13 columns or features. So we have this player ID, age, gender, location, game genre, playtime hours, in-game purchases, game difficulty, sessions per week, average session duration per minute, player level, achievements unlocked. But why is it a multi-class algorithm, or under the category of multi-class classification? Because the output variable or the target variable can be categorized into reflecting the three types of player. That is, if you belong to the medium category, high or low. Getting my point? It's more than two classes. A player can be engaged in three different types of category, that is low, high, and medium. Getting my point? All right. So let's start with its implementation. Yes. So are you getting scared looking at these many libraries? The first four libraries, now you are very familiar. Then ultimately it is Scikit-learn, but with model selection, I'm using train underscore testplate. For pre-processing, I'm using these function, and the naive Bayes, KNN, tree, ensemble. I'm doing all the importing of the files for different algorithm in the very first command only, along with the metrics. Now clear? I hope these many, libraries are not scaring you, or is it? Are these many libraries scaring you? All right. So let's load this data set. Yes, good, Ajay. Have you been able to load the data successfully? Are you there with me with 4.2 learners? Okay. So we have 13 attributes: player ID, age, gender, location, game genre, play time hours, etc. So that point we are very clear. These many rows, 40,034 rows, 13 columns. And if you look at the detail of the column, these are the details. So what are my categorical data? And which is my target variable? Which is my output variable? Of course, it has to be categorical in nature. So the engagement level of the player is divided into 3 categories: low, medium, high. Clear? What are we doing with this particular command? What are we doing with this particular command? Checking the null value. So does this data set has any null values? No. Let's do the describe function. So this is the ID, this is the age, around 30, 31 is the age, average age. Minimum is 15 years, maximum even 50 years old. Play games. Do you all play online games? I mean, just asking. So these are the number of hours which get invested. Some invest 0, and even some even invest 1 full day, around 24 hours a day. Okay. In-game purchases, session, play, etc. So I hope you are now familiar with how to analyze this data set. Everybody understands how to analyze the output of the command, since we have been doing in data science and as well as in machine learning. Now, this is important. This is the different classes along with their frequency, right? So this is the median, high, and the low value. Clear? This is the engagement level, value underscore counts. Getting my point, learners? Okay. Now tell me, what are we trying to do over here? I always ask this question to you. Earlier, defining the X and Y. Only separating the input and the output. Splitting is into training and testing data. So when I do dot gender, it is the males who are playing more than the female. Is it like that? Males play more online games than female according to this data, at least. Location, people from USA play the most, then Europe, then Asia and others. I think so Indians should be the more, no? We Indians play a lot of games, no? So based on this data, it's more of the people in USA. And if I talk about game genre, what kind of games do you like to play more? Then we have the different game genres. The game difficulty level, easy, medium, hard, that needs to be counted. I hope you are appreciating this value underscore counts function. Yes, learners, I hope you are appreciating that. That it is generally used for categorical data where we have different categories along with the frequency count, right? Right. Now, what are we trying to do in this particular code? Now, you tell me. Well, all the comments are there, but what do we understand? This is a categorical columns list I have created, and then I'm using the label encoder. What is the use of label encoder? Converting categorical data to numerical value. So, what is the concept of label encoders? Is it ordered data or nominal data? Ordered, like low we can give least rank and high we can give high rank. So this is how we, get the label encoders. And then what are we trying to do over here? What does x_core do? Good, or, what does x.core function do? Relationship between the features, also multicollinearity, that how strongly they are related. We can say, but multicollinearity is generally calculated with VIF, variance inflation factor, Puneet Reddy. But correlation helps to find out the strength of the relationship. That is what we are trying to say. So now when I do the correlation matrix, how do I interpret? How do I interpret? The darker color means negative relationship, lighter color means strong relationship. So where is the lighter color? Between the game genre. So this is a good score. Game genre, and this is also a good score, right? The game genre is this, and the play time hours is this much. Clear? And now finally, what is happening in this particular code? Here we are splitting the data for training. Now clear? First we were separating all the input and output, and it is the train underscore test underscore split function which is used to split the data. All right. What is that known as? Preparing the data set, or another technical word, pre-processing. Okay, good. Another technical word. Another technical word. Feature engineering. Can we call that feature engineering? Yes, Atul. Good. So preparing the data to be fed into the model. So what are we doing in this last step? Can anybody tell me why did I apply standard scalar after the split? Why did I apply standardization after the split? First of all, what is standardization? Tell me that. No fit for the test data, right? But we are transforming only the test data. But why after the split, Puneet Reddy? Test data we are only transforming. For input, we are doing the fit. Why? To prevent data leakage. And what is standard scalar? What does the standard scalar function do? It standardizes the data, right? Mean equal to 0, deviation equal to 1. Excellent, Puneet. Feature scaling. And why do we do feature scaling? Yes, a large value will not decide or skew the result, so that our model is not biased. Now, what is the first model that we are trying to do? So now our, data is well prepared to be fed into the model. Now it is up to me, I want to use the pipeline or not. So first step for implementing model, importing the library, creating an object of the data and fitting the model. What does the fit function do? What does the fit function do? It trains the input as well as the output data, and then we get the predicted output results. Clear? Is this code and point getting clear to everybody? Then we are trying to find out the class order over here and then check the results output. So what is the class order? Basically high has the high, then we have low and medium. This is the actual label, predicted label, along with the probabilities. Why do you think the medium is the output? Because medium has highest probability in all the cases. Clear? Concept of probability is getting clear. In classification problems, we will always get the output in terms of probability. And as I've told you, in LLM models, V is a classification problem. So therefore, it also gives the output in terms of probability. Right, Ajay? This is what we learned. And now if I look at the naive-Bayes classifier accuracy, what do you conclude from this? I mean, it's not very good, but the training and the testing accuracy again are coming out to be almost the same. Ajay says, ma'am, why logistic regression not in multi-class? We can't extend logistic? No, we cannot, because the sigmoidal function gives only two outputs, that is 0 and 1. That is why it is only valid for two classes, practically. It doesn't give. So either you will get the output as 0 or 1. That's it. So therefore, for multi-class classification, you need 0, 1, and 2, which is not possible in logistic regression. Sigmoidal function does not do that. Now tell me, what is the result of naive-Bayes classifier? What is it a good fit, underfit, overfit? It's again a very good fit. Less accurate, but it's a good fit. Yes. If we look at the confusion matrix, now do you see the confusion matrix? It's a 3 by 3 confusion matrix. Difference you are understanding? Earlier it was only 2 because we were talking about 2 classes, and now class confusion matrix with labels. So high and high, no error, low. So these are the perfect classified classes, and these are the errors associated with each term. Got it, learners? So high, the class is relatively high number of the true positive, that is 3,234, but also considerable amount of false negatives, indicating that some instances misclassified as low and medium. So I think so the best way to do it is check the classification report. Right, so it's quite giving us 85% for high, 78% for low, and medium it is 87%. And this is how I'm getting my accuracy. Clear, learners? So look at the beauty. If there would have been 4 classes, it would have been 4 by 4 matrix, and the classification report would have 4 classes output. Then we have label underscore binarize. It is a function from Scikit-learn that is used to convert class labels into binary format. Right? Here we are using one more function, which is part of the Scikit-learn library, which converts class labels into binary format suitable for certain type of classifiers as well as the evaluation metrics. Particularly, why do we need to convert it into binary format? Because there are 3 classes. Useful when you need to handle multi-class problems with methods that are inherently designed for binary classification, such as ROC and AUC curves. So even the ROC or AUC curves are inherently designed to deal with classification or binary classification problem. So to draw the ROC curve for multi-class setting, this is how we would get my results. That it would check label, binarize. It would check, make the output in terms of binary value 0, 1, y test, classes is equal to nb underscore model dot classes. Getting my point? So n underscore classes is equal to y test binarized is equal to shape 1. And this is my predicted probability. Right? Do we understand predicted probability? Function that is used is predict underscore prob A, not normal predict function that we use in linear regression. And with the help of these binary value, I get my 3 curves, ROC curve of class 0, class 1, and class 2. So they all are almost performing well, around 94, 91, 90%. So what do we see? That class 0 represents high class. The model performs very well in classifying instances of class 0 because the area under the curve is 94, indicates that there is 94% chance that the model will correctly distinguish between the randomly chosen positive instance and randomly chosen negative instance for class 0. Getting my point? What is the significance of diagonal black line? The diagonal line represents random guessing with AUC of 0.5. So always the area under the curve should be more than 0.5. If it is 0.5 or lesser than that, that means it's not a good classification model. So any ROC curve below this line indicates worse than random performance, while curves above this line indicate better than random performance. Now clear? So we can see that naive Bayes performs exceptionally well for all classes as the area under the curve are all in 90s. The model is best at classifying instances of class 0, high class closed by class 1, class 2. Now clear? What is the significance of ROC AUC curve? That the class 0 or the high class game players have been classified very well as compared to class 1 and class 2. Clear? Now moving ahead to k nearest neighbors algorithm. What is the concept of k nearest neighbors algorithm? Tell me. How does the KNN work? The output is based on nearer data points, right? The neighbors of predicting it, right? And generally the number of neighbors are kept even or odd. Yeah, looking at the k closest data point always odd so that, we can conclude, at least one. Even data points can always lead to clashes, right? So from Scikit-learn neighbors, import k neighbors classifier. KNN model is k neighbors classifier with three neighbors, and KNN model dot fit is equal to training. SC, what is this X underscore train SC? What is SC? Scaled X. Yeah, standardized input training data. Yes. Try to understand learners code. Okay. Good. Scaled or standardized X. Right. And that's what then we are going to, fit the model and then predict the output. So we see the medium, high, low values are getting predicted along with the probability values. Then we can get the class order and see the actual and the predicted outputs. Clear? So KNN has not given us good answers. This is wrong. It should be medium. This is also wrong. So KNN has not performed that well as naive Bayes. I don't know. Naive Bayes has, somehow it performs pretty well than other algorithms, right? Getting my point? And then what is the training and testing accuracy? What will you conclude? Is it an underfit or an overfit, Puneet? You're talking about accuracy. I think so. You brought out this point. The testing error is more than the training error, right? Is it underfit? Is it overfit? Yeah, it is overfit. The training error is definitely more than the testing error. Sorry, testing error is much more than the training error, right? So it's overfitting the. Got it, everybody? So now, if I see the classification report, it's not as good as we saw it in the naive Bayes classifier. And if we check the ROC AUC curve, the area, the area under the curve has also reduced from 92, 93% to 89, 83, 79%. Right? So cyan line is class 0 area under the curve. The model performs well in classifying instances of class 0 medium. Area under the curve is 89%. That it has 89% chance that the model will correctly distinguish between the randomly chosen positive instance and randomly chosen negatively instance for class 0. So what are our observations? The KNN classifier performs reasonably well for all classes, but not as good as it was a naive Bayes classifier. With AUC, values ranging from 0.79 to 0.89. If the data set has imbalanced classes, some classes have significantly more instances than others. So this could affect the model's performance. And the ROC curve, it is essential to consider under class distribution when interpreting these results. Right? So the next step that we are going to learn after classification is ensemble learning. That is where we combine the outputs of different algorithms to improve the overall result. That can also be one of the methods. Data is variable, data is uncertain, data is changing constantly. Right? So no one algorithm is fixed, no rule is fixed on data. Okay? So when we talk about real world data, it's constantly changing. All right. So here we are starting the multi-class and the multi-label classification problem. Binary classification, we are clear. Only logistic regression is that algorithm that, helps in binary classification of the things, right? Then we have multi-class classification where, outputs can be more than one, as we are already doing one of the real-time data sets. That's for online gaming data set, which is classifying the players into low, medium, and high level of players, right? And then we have multi-label classification where we have the dog, cat, bird, same image getting done. So multi-class and multi-label classifiers. Multi-class classification can be judged on the basis of one versus rest classifier, one versus one, or multi-label classifiers can be, checked based on multi-output classifier, right? Then we have also understood the label underscore binarized function in Scikit-learn is designed to handle multi-class labels by converting them into binary matrix format using one versus all. What is one versus all or one hot encoding scheme? Why is it important to do label underscore binarize? Right? Then it is able to, do the comparison between the different classes. Getting my point? Right? Format using one versus all or one hot encoding. The function takes original labels and a defined list of all possible classes, then outputs a 2D array where each row represents a sample, each column corresponds to a class. A1 indicates the sample belongs to the class, 0 indicates it does not belong to the class. Getting my point? What is one hot encoding? What is one hot encoding? One hot encoding is when the data is categorical data is not ordinal, it's nominal. This process is effectively one hot encoding for multi-class data. Then we have the class order. The order of the columns in the output matrix y underscore bin matches the order of the classes you provide to the function. Then we have binary versus multi-label. It's important not to confuse this with multi-label classification, where a single sample can belong to multiple classes simultaneously. Multi-label, you are very clear? So for true multi-label problems, you would use the multi-label binarizer class, not the normal label underscore binarizer class. Alternate, the Scikit-learn preprocessing label binarizer class provides the same functionality but with fit underscore transform method for use within the Scikit-learn pipeline. Clear? So this is binary classification and this is multi-class. And what do I mean by binary comparison? Since there are three classes over here, first the red one will be compared with the black one, then the red one with the blue one, and then the black and blue ones are compared. Got it? But the approach which is used, that was it talking about one versus all in binarize, label underscore binarize is that if I want to do the comparison of green with other classes, I will take them as the green and all other belonging to one class. Clear? Then I'll take another class square and all other belonging to one class. Is the approach getting clear? The difference between one versus all and one versus rest with one versus one classifier? Is the difference between the two clear to everybody? And then we have the multi-label classification, multi-output classifier over here, and multi-output regression. Getting my point? So till now we have implemented two algorithms, naive-Bayes classifier and KNN. Naive-Bayes classifier performed better than KNN, but very good point was pointed out that if we could hypertune the parameter, we did not hypertune the K parameter, then the results would have been better. Right? Agreed? Can we move forward again on 4.2 file? Yeah. Now let's apply decision tree classifier again on the same online training data. So what is this code doing? Importing the library. Second is creating the object of the model. Calling the function or creating the object of decision tree classifier. Third step, training the model with input as well as the output training data. Then we are predicting on the testing set. Clear? So now let's check the class order. So it says that x underscore train sc is not defined. So I'm not running the previous code. It is nothing but the standardized input, right? You all remember? So now do you see how well this has performed? This is fine, but this is the wrong conclusion, right? And the probability is coming out to be perfect for median, but here it is high. This one is wrong. Rest everything it is, classifying correctly, right? So what are we observing as the output in decision tree classifier? What output can we observe in the decision tree classifier? The model is overfitting. Why, Atul? Why is it overfitting? So how can we check the overfitting in a decision tree? Right? So how can we, cross-check this training accuracy or improve this overfitting model in decision trees? By doing cross-validation. By doing cross-validation, can we do that? So the training accuracy combined with, so when we have a training accuracy combined with slightly lower testing accuracy, typically points towards the overfitting scenario. That we all are understanding. In practice, this might mean that the decision tree has complex branches that perfectly classifies the training data, but slightly misses when predicting new or unseen data. Adjustments such as pruning the tree, like dealing with hyperparameters, setting a maximum depth, increasing minimum samples required for a node, split might help in reducing overfitting and improving models generalization. So, does cross-validation also help in checking the model just memorizes the training data or if it generalizes well overall unseen data? Is cross-validation also a better way to check? Yes, it is. Please try to understand. Cross-validation is also one of the ways to check. So when I take the mean of cross-validation, it is coming out to be almost same as the accuracy of testing, 82.8%. And this is also coming out to be 82.8. So that means it is not learned the data. The data is like that it has learned it very well during the training. It is not just memorize the training data or if it generalizes well over the unseen data. Clear? So the cross-validation scores vary slightly, but generally remain high with a mean cross-validation score of 0.82%. This indicates good model performance and stability. Getting my point? So if I look at the classification report, it is 80%, 83 to 82%. So the confusion matrix and classification report show that while the model performs well overall, there are some misclassifications. Agreed, learners? Right? So which was one of the best results? Naive Bayes classifier was giving you one of the best results. Agreed? Now we will understand one more important concept of decision trees, that is random forest. What does the term forest mean? It is a group of trees, right? What does that mean? That rather than using a single tree for predicting the output, we will use a group of trees to judge the output. Getting my point? Right? So now with this approach, let me explain you tomorrow's foundation. We would be moving on to ensemble learning method. That is, rather than taking output from 1D, we will combine the output of many trees. And will it, do you think, it's going to overall improve the results? Yes, of course. So how do we go about it? That if this is my data set, I will randomly divide it into different features randomly divided into different samples. The original, let me put it again. The original data set gets divided into different samples, random samples. From the first sample, I create a tree one, check its output. Then from tree two, and from the second sample, I create another tree and I can create n number of trees. And then getting the output of everybody and then take the average or the majority voting to predict the final class. Clear? Are you understanding the concept of random forest now? So to address the limitations observed with the decision tree, we can transition to using a random forest model. Random forest is an ensemble method, right? So there is one more topic in classification that is still left. How do we deal with imbalanced class? We'll just start after we finish this particular file. After finishing that ensemble model, maybe we will not be able to complete it fully, that we will take it up tomorrow also. After that, tomorrow we will take up ensemble learning method. Very, very important. It covers certain concepts of deep learning also. So I request you to be present to follow the class, because tomorrow we would be touching up into calculus, a little higher concepts that will be required in deep learning also. Clear? So we can transition to using random forest model. Random forest is an ensemble method, builds multiple. What is the concept? It builds multiple decision trees and combines their predictions to improve performance and reduce overfitting. So what are the benefits of random forest? It reduces overfitting. Averaging the results of multiple decision trees reduces the risk of overfitting seen with a single decision tree. It improves generalization. The combinations, predictions from the multiple trees enhance the model's ability to generalize to new unseen data. More robust predictions, random forest is more robust to noise variability in the training data. Clear? So how do we go about it? It's not difficult. Simply, we will, like we did the decision tree classifier, we will create the object or the model of random forest classifier, and then fit it, and then predict the output. Great. So my code has run. And now if I see it, again, I get only one wrong answer over here. And now what do you observe? The testing accuracy has improved, but is it overfitting? Again, we can cross check. It's not overfitting. It's due to cross validation. So this is 90%, 91%, overall giving you better accuracy than the decision tree. Agreed? Okay. So the random forest model shows perfect accuracy on both the training as well as testing sets, indicating that it has classified all instances correctly. The confusion matrix for the random forest model shows perfect classification for all classes with less misclassifications. The decision tree had a few misclassifications, particularly one misclassified instance in medium and low. Given the perfect performance of the random forest model on this data set, further hyperparameter tuning might not be necessary. I hope, Ajay, you got the answer. Given a perfect performance on random forest model on the data set, further hyperparameter tuning is not required. However, for more complex data set, hyperparameter tuning could further optimize the model performance. So, if you feel that the data set is more complex, you can, work on the depth, work on the number of splits, then it could even give better results or better performance. Got it, learners? So over here now, multi-class. So what difference did you find out? Was there any difference in the code? Whether we were applying, KNN algorithm on binary or multi-class? No, there was no difference. The same logic, same libraries were imported, same this thing, but classification report and confusion matrix were giving me based on the 3 outputs. If they are 4, then it would give me 4 by 4 confusion matrix. Right? Now let's understand multi-label classification. This particular classification is, comes under the category of deep learning, right? Because it generally talks of images, generally talks of text categorization, movies. So multi-label classification is not covered under machine learning. It's generally covered as part of deep learning. All right, learners. So multi-label classification allows us to classify additional knowledge. What does that mean, Ajay? Deep learning is required, which is a separate course where you cover multi-label classification, not under this course. Okay, Ajay? I'll just make the point more clear. So it allows us to classify data sets with more than one target variable. There are several labels for the output of a given prediction, and making predictions a given input may belong to more than one label. So example is text categorization, new article classification. A new article might belong to multiple categories such as politics, economy, and health. So when I talk about the concept of text categorization, it does not come under the domain of machine learning algorithms, right? It comes under the category of NLP. Getting my point? So NLP is only after deep learning. So multi-label, the classifier can tag each song because text has to be understood. Tagging question answers in QA platform, again, it is based on text, so NLP. So a single question might relate to multiple topics such as Python, data science, machine learning. So a multi-label classifier can automatically assign all relevant tags to each question posted on the platform. Got it? And below, additional resources are there like deep learning for multi-label learning, comprehensive comparative study of multi-label classification methods, and multi-label classification with transformer. So they all come under the category, right? But multi-class classification and binary classification, almost same methods are being used, whether you are using the same algorithm. No difference in the steps. Got it, learners? 4.2 file is clear. So classification techniques are integral to understanding and predicting categorical outcomes based on features, right? In this comprehensive exploration, you have delved deep into the realms of multi-class and multi-label classification, employing data sets such as online gaming behavior, data set to anchor your learning in the real world context. You have become familiar with essential classification algorithms, including naive Bayes, KNN, decision trees, and random forest, observing the applications across different scenarios. So can I do a quick knowledge check with you all? First question, what is the goal of decision tree algorithm during training? Yes, we want to minimize the impurity. C will be the correct answer. Well, all are correct, but I think so more relevant term to trees is impurity. The goal of support vector machine is to find the optimal separating hyperplane which minimizes the margin of the training data. True or false? Minimize or maximize? Of course, we want to maximize the margin. The term kernel in SVM refers to, is it a hyperparameter? Yes, it is, but it is generally known as what? Transformation function. It is a hyperparameter, but kernels are also known as transformation function. Getting my point? Which of the following statement is not true about hyperplane in SVM? That if we select a hyperplane which is close to the data point of one class, then it generalizes. All others are true. A hyperplane is very close to data point, its margin will be small. Okay. If the hyperplane is far, the margin will be large. Optimal hyperplane will be the one with the biggest margin. Got it? In supervised learning, the training data set consists of input as well as output labels. What is the main objective of classification algorithm in supervised learning? It is C, assign input data to the predefined categories or classes. What is logistic regression used for? Due to the sigmoidal curve output. Which classification algorithm assumes independence among features and calculates the probability of a sample belonging to a certain class using Bayes theorem or Bayes theorem? It is B. Which machine learning technique is primarily used for classification tasks and involves dividing the data into distinct categories? So we've done only one of them. So you know already it is decision tree only. Rest, regression is only for numerical data. It cannot be for categorical data, right? KNN classifier assigns the majority class of K nearest data points, right? What is the process of scaling features so that they have mean equal to 0 and standard deviation equal to 1? That's known as standardization. Which supervised learning algorithm uses hyperplanes to separate the classes? Yes, it is SVM. Okay. All right, I think so. That was a quick revision. Okay, now let's start understanding handling of imbalanced data set. What do we mean by imbalanced classes? What do you observe in this particular slide? Yes, learners. Yeah, 1 hour more to go to finally. Let's complete this topic as much as we can. So what do you mean by imbalanced data set or imbalanced data in classification? We see that the orange class is has more of the majority points as compared to the cyan point. So this is known as the major class. Yes, the samples or the classes are of different sizes, not the sample. Sample is the part of the data. Here we will say the classes are of different size. The class with maximum data point is known as a majority class, and a class with minimum number of point is known as a minority class. So again, an imbalanced data set have many more instances of certain classes, not samples, okay, than of others. Getting my point? Right? So now do you see this? So how do you try to make imbalance classes, majority, minority classes the same? How do you go about it? One of the ways either reduce the majority class to minority or convert the minority classes to majority, right? This is one of the ways we can do. Yes, or I add more weightage to this particular class as compared to the majority one. Adding weightage to classes also makes the balance equal. Right. So few terminologies that needs to be understood. So the points which are less in number are known as minority data points. Points which are large in number are majority data points. If the minority data point is present in majority, that becomes the noise sample. Safe edges samples are those which are clearly, belonging to the minority class or the majority class, and safe inner samples which belong to the inner points of the class, and some belong to the borderline sample, right? So why? What is the problem dealing with imbalanced data set? That is the question. What is the problem in dealing with imbalanced data set? Yes, learners. Model will predict an output only by majority, not from the true learning. Yes, it can get biased towards the majority class, right? So it is up to us as a data scientist, machine learning expert to create that balance. The output should not be biased. Okay. So the conventional model evaluation methods do not accurately measure the model performance when faced with imbalanced data set. So which of the metric of confusion matrix should not be used in imbalanced data set? Which of the metric should not be used in imbalanced data set? So the standard classifier algorithms like the decision tree or the logistic regression have a bias towards classes which have more number of instances. They tend to only predict the majority class data. The features of the minority classes are treated as noise and are often ignored. Thus, there is a high probability of misclassification of the minority class as compared to the majority class. Right? So what are there are three challenges, three problems faced when we talk about imbalanced data set. First is the bias models. Machine learning models optimize balance metrics or functions by default. Hence, imbalanced data can lead to biased training models that tend to predict the majority class more accurately while neglecting the minority class. So what is the other issue? This can result in high false negative rate while minority class is misclassified as a majority class. Got it? Second issue is skewed class distribution. Imbalanced data shows a skewed class distribution where the majority class dominates the data set, and this can lead to lack of diversity in the data and make it difficult for model to learn the underlying patterns of the minority class. Getting my point? And the third is the differing cost of misclassification errors. Another challenge with imbalanced data is that misclassification errors can have varying costs depending on the application. For example, a false negative can be life-threatening in medical diagnosis, while false positive may cause inconvenience. Got it, learners? So imbalanced data set is clear. It can be due to oversampling, due to adding more features, use class weights, undersampling are the different methods to deal with imbalanced data set. So an imbalanced data set is a data set where each output class or target class is represented by different number of input samples or data points. Okay. Oversampling is one of the technique to solve it. What is oversampling? Increase the number of samples of the smallest class up to high size of the biggest class. How this can be done? This can be done by generating synthetic samples. SMOT is one of the technique that we will understand. Undersampling is another technique that we would be using. We decrease the number of samples of the biggest class down to the size of the smallest class. Remove some samplers from the biggest class. Other way is class weights, assign weights to each class so that, the weights of the two classes or this thing can be balanced. Then we have the decision threshold. If a predicted value is greater than the threshold, it is set to 1, otherwise it is set to 0. Getting my point? So what is resampling? You can change the data set that you use to build your predictive model to have more balanced data. This change is called sampling your data set when there are two main methods you can use to even up the classes. One is oversampling. Oversampling consists of creating synthetic data for the underrepresented, right? Or formally sampling with replacement. Do you understand? So what does sampling with replacement mean? That suppose there are 10 red balls and green mixed balls. So what do? You take a sample of 3 balls, then you keep it back, then you take another 3 samples of ball, another 3 samples of ball. So whatever sample you are taking, you put it back and then take it out another, right? And what is undersampling? You can delete the instances from overrepresented class called undersampling. Yeah, that's exactly like probability questions you might have done, right? So undersampling, what are the issues with undersampling? Can you tell me? When the majority class is made of the same size as minority, what are the issues with undersampling, learners? Yes, they can be loss of information. What could be the problem? If they can be loss of information in the data. And when I talk about oversampling, what is the issue with oversampling? Noisy data, unnecessary data can also get added in the while we are creating the synthetic data, right? Agreed, learners? Synthetic data will not represent the real world data. We may have bloated information. Could be, yes. But still we use these techniques, right? Because we want to ultimately make the data set balance. So when we are talking about oversampling, we use the SMOT technique, that is synthetic minority oversampling technique, right? So SMOT refers to synthetic minority oversampling technique. SMOT consists of synthesizing elements for the minority class based on those that already exist. It works randomly picking a point from the minority class and computing. So it works a little bit on the concept of k nearest neighbors for this particular point. The synthetic points are added between the chosen point and its neighbors. Clear? So how do we go about it? Suppose these are my two classes and I want to make the classes balance. So now based on the nearest neighbors, I will create the synthetic data points. The green data points are being created. So the algorithm which runs at the back end is that if this is my data, S is the minority class, N is the total number of synthetic samples to be generated. K, how many neighbors to consider? So it is again based on KNN. So synthetic data is synthetic, considered to be null. We will run from 1 to n, randomly select a sample from S, randomly select one of its neighbor, and then put it onto the synthetic data. Now you are understanding why sampling with replacement. So you take the sample, you put it back into the data again, try to take out the another new sample, right? So how do we go about it? Let's see by an example. If 2, 1 is my original sample and the neighbor is 4, 3. So how can I create a new sample or a synthetic data? Maybe in between these two samples. So 2 minus 2, 1 minus 0 0.4 into 2, 1 minus 4, 3. Why are we using this 0.4? S plus U, Z minus S. U is the uniform random value that we choose from 0 to 1. Are you understanding this particular formula? We are using exactly this. This is my original, this is the neighbor. U is a uniform random value chosen between 0 to 1. So over here I have chosen 0.4, 2, 1 minus 4.3. So this is the value I get, and my new sample, synthetic sample value comes out to be this. So it will not be exactly like 2, 2. No, we will generate it randomly, right? Because randomness is one of the very important features of data. Is this point getting clear? Are you understanding the algorithm? How the synthetic data is getting generated? Right? So we are trying to take an example case of k equal to 4. Where generally, we do not take k is equal to 4 because it's an even number. But okay, this is my x1 1 point, x1 2 point, x1 3 point, and x1 4 point. And I'm trying to find out the difference or the radius between this x1. So r1 is equal to x1 plus gap into the difference. Same formula, but done it in the different way. Same formula. Are you understanding how the synthesized data gets generated? So what is the advantage of oversampling? It improves performance, balances the data set. It's not limited to specific machine learning algorithm, easy implementation. But when we talk about disadvantage, it increases computational complexity, not suitable for all data sets, incompatible with regression problem. It can lose the subtitles of the original data also. And if I talk about undersampling, undersampling is randomly removing the imbalanced data set. Okay, so this is my imbalanced data set. Green points represent my majority class. Red triangle represent my minority class. And finally, I get a random undersampler data set. So now let's get back to the code part of it. So the final file, that is 4.3. So handling of the imbalanced data set is crucial because it leads to skewed databases, incorrect results, and can lead to favorite majority classes, leading to poor performance in identifying the minority class. Therefore, we need to deal with imbalanced data set. Now, in real time, in real life problem, do you think imbalanced data set should exist? Try to understand the example given. Imbalanced data set should exist, especially if I'm talking about, the ratio of a country, city with healthy and non-healthy people. Do I want that ratio to be balanced? No, not at all. I want healthy people to be maximum and non-healthy people to be in the minority group. This is what actually we want in the data set or not. People who are smoking to non-smoking. We want non-smokers more than the smoking category of the people. Sometimes we want that imbalanced data set. Getting my point? Healthy versus junk food. We want more people to eat healthy food as compared to junk food. Getting my point? Yes or no? Or do we feel that all data should be absolutely balanced? This is what we were thinking till now. Or every data should be 50-50. Yes or no? Yes, in male-female ratio, yes, it should be 50-50. Neither the male should be more nor the female should be more. But in some cases, we want the distribution to be imbalanced. Right, learners? So what are the applications of handling imbalanced data set? Medical diagnosis system. Of course, we want healthy more than unhealthy. Fraud, less fraud as compared to normal. Spam detection to be much lesser than the original data. Right? Are we understanding these example, learners? Medical diagnosis, fraud detection, spam detection. So before diving techniques into handling imbalanced data, it is important to first understand how to determine if your data is balanced or imbalanced. So which graph will give me balanced and imbalanced data set? Well, this is a pie chart, scatter plot. I think so. Lot more graphs can give you that it is a balanced or an imbalanced data set. Getting my point? All right, so now we are talking about a data set about credit card transaction, right? This data set consists of credit cards by a European company in September 2013. It contains only numerical input variables where each results are of PCA transformation. Unfortunately, due to confidentiality issues, original features and more background information about the data is not available. So features V1, V2, V8 are the principal components obtained with PCA. The only features which have not been transformed with PCA are time and amount. So other data are being hidden due to confidentiality, but time, amount, and class, that is the target variable, is not hidden, right? So what do you think? The fraud transaction should be much lesser than the all non-fraudulent transactions, right? Okay. So first thing that you need to do is please import this, run this particular command, pip installed imb balance learn. This particular library is required to learn for imbalanced data set. So now if we look at this particular data set, it consists of 2000 rows. So it consists of 2000 rows and about quite a lot of columns, 31 columns, where class is my output, amount is again my input, all others are like they have been hidden due to confidentiality. Okay. Simple, data set is simple to understand. And if I look, is it imbalanced? Is it an imbalanced data set? Yes. Non-fraudulent transactions are 1974 and fraudulent transactions are only 26, less than even 1%, around 1% of it. What is 1% of 2000? 1% of 2000 is 200. So it's like even less than that, 0.1%, right? And if I look at through two graphs, one is the count plot or the bar graph. I see a major difference. Two graphs are also getting clear. First, I am using the distribution plot bar graph with different colors. And in the other one, I am using the pie plot. Do you see the imbalance in the data set? What do we observe? So the data set is highly imbalanced with nearly 2000 non-fraudulent transactions, only around 25 fraudulent ones. Significant imbalance needs to be addressed to avoid bias models and ensure fair and accurate predictions. Using this data set for classification has following disadvantage that it can be biased towards non-fraudulent data. and can also give you misleading results. That we are very clear. Now let's understand the techniques to handle imbalanced data set. One is oversampling technique, that we will use the SMOT. Undersampling technique, randomly removing the data. Are we also clear in these two techniques? How are we going to handle imbalanced data set? In my field, we mostly deal with these kinds of data set. And another technique that we will use is ensemble methods for imbalanced data is balanced random forest. Condition for use effective when leveraging an ensemble approach. As I've told you, tomorrow we'll start with ensemble approach to maintain robustness and generalizability while addressing the class imbalance. Clear? For oversampling, the condition for use is ideal when minority classes severely underrepresented, as in this case. Undersampling, useful when data set is large enough, and removing instances won't result in significant loss of information. So that concepts, I think so, we all are very much clear. Oversampling is a technique to balance the class distribution by increasing the number of minority class sample. This can be done by duplicating existing samples or creating synthetic ones. Okay. So now let's understand the SMOT, synthetic minority oversampling technique. More advanced method that generates new synthetic samples from minority class. First, it selects random minority class sample, depending on the random k nearest neighbors. Depending on that, it generates the formula. Advantage of SMOT is that definitely it prevents overfitting of the data. Unlike simple duplication, SMOT generates new sample while helps in creating more generalizable model. Balances the data set by creating new samples. SMOT helps balance the class distribution, improving the model's ability to learn from minority class sample. So here we go with the practical implementation. So which library is new for us? imblearn is a new library in which we are importing the SMOT technique. Otherwise, all others are the same, right? Upload the data set, separate the input and the output features. That's it's done. Then the split can be done and standardization. And now let's first plot the imbalanced data set. So just imagine, the orange, the yellow ones are your fraudial data and purple ones are your non-fraudial data. Agreed, learners? Do you see this? Are you all able to observe this imbalanced data set? We are using the scatter plot now. So the color of each data point indicates the class it belongs to. The color scale on the right shows the gradient from purple to yellow, where each color represents a class label. They are predominantly purple points indicating a majority of data points belong to class 0, yellow points indicating they belong to close to class 1, which are fewer in comparison. So now when I apply the SMOT technique, learners, are you there? Simply you have to call the SMOT function and create a SMOT object, and then ultimately fit resample on the training input and output data to get your more SMOT examples, right? So now do you see we had X trains SMOT. So earlier they were 2000 samples. Now we have 2364 samples and 1200 in the output training data also. Is this point getting clear to everybody? Right? So earlier my class distribution was this much. Now it is 2364 versus 1200. So now if I see the output, do you think it's more balanced? Definitely the yellow points are almost similar to the purple points now. Agreed? So what we can see clearly that the data is more balanced after applying the SMOT technique. Then we train and evaluate and predict on the training data set. So what do you observe? What do you observe on the training and the test accuracy? Almost same. Almost same. Can we say that? It has classified it correctly now? Yeah. Close to, yeah, good fit. It's close to good fit, right? So the decision tree classifier, when trained on smooth, balanced data set, achieved high accuracy on both training, 99.4%, testing 98% sets, indicating strong model performance. However, the slight drop in text accuracy compared to train accuracy suggests some overfitting. The model generalizes well but may still benefit from further tuning or validation techniques. Agreed, learners? And now if I look at the confusion matrix, one of the error is 0, another one is high. One error is high. Right? The methods, methodologies, everything remain the same. What kind of model you are going to apply remains the same. Only that before, applying the data points, you will use the smooth technique so that you balance out the data. Clear? This is where you will do. And what do you observe in the classification report? So it clearly shows that 0 is giving you more higher accuracy and the synthetic data which has been generated is only giving you 57%. Clear distinction is you can see in the F1 score as well as in the overall macro as well as weighted average. And now if I create the ROC AUC curve, let's see how much area. Oh, it's giving me perfect 1. That means the two classes of, even after creating synthetic data, the two classes are being classified very, very correctly as fraudulent and non-fraudulent classes. Right, learners? Can we move on to the undersampling technique, learners? Here, there is no algorithm or any other technique. We will just randomly remove the data from the majority classes. Got it? So undersampling is an opposite of oversampling. It involves reducing the number of samples in majority class to balance the data set. This can be done by randomly removing samples or using more sophisticated techniques. So here we will be using grid. So random undersampling is one of the simplest undersampling techniques. How random undersampling works. First, it identifies the majority and the minority classes. First, identify which class is overrepresented, majority class, which one is underrepresented. Randomly select and remove samples from the majority class until the samples in each class is balanced or same. So if you have 1,000 samples in the majority class, and 100 in minority, you might randomly remove 100 samples from majority class. Resulting data set, the resulting data set will have more balanced distribution of class with a reduced number of samples from the majority class. Got it? So what are the advantages? Simple and easy to implement, reduces training time. Disadvantage, we are also very clear, loss of information or can lead to overfitting. Clear? So now we will use the same data set and train test split for applying these data balancing techniques and fitting the classification model. Then again, let's import the undersampling random undersampler for the imblearn library. Done. I hope everybody's code is running now, especially the imbalanced dataset library. And which is the function that we are using? Random undersampler. What is the use of this random underscore state 42? Yeah, controls the same randomness and splitting. And then I am doing an undersampler.fit resample and passing the scaled data points. And now when I plotted my majority class gets reduced to minority class. Now, do you see the purple points have reduced to yellow points? Right? So we can see the data is more balanced after applying random undersampling, but the data points are less. So now we can again initialize and train the decision tree classifier on the undersampled training data, predict on the training data and the testing set, and calculates its accuracy. So now what do you observe? Good fit, underfit, overfit. So it seems like overfitting, training accuracy equal to 1. So how do we? It seems like, Ajay, we have to cross check it. So the training accuracy of 1 indicates that the model has perfectly learned or memorized the training data set. It can correctly predict the outcome of every sample it was trained on. This could be the sign of overfitting, not always overfitting, but could be sign of overfitting. But how do I check this? Using technique like k-fold cross-validation to assess model performance. Please be clear with this particular point. This can be a question of asked in your interviews that when you get the train accuracy equal to 1, does it actually mean it is overfitting? No, not necessary. It is a sign of overfitting, but it can be cross-checked with the help of cross-validation technique. So this helps to ensure that the model's performance is robust across different subsets. So now, can I also use the IMB pipeline technique? Why IMB pipeline technique? What is the use of pipeline? It is specifically designed to handle imbalanced data set by integrating resampling methods directly into the pipeline. So the imbalance library also has this pipeline function, then model selection. Now, say why are we using stratified k-fold over here? Maybe it looks overfitting only in that particular split. CV and shows. Yes. What is the concept of what is stratified k-fold? Cross-validation technique. Yes, learners. It's used for classification problems. So what does it do? That if I have an imbalanced distribution, it tries to split each group into that same proportion. Yes, we try to split in different, folds the same ratio. We try to keep it the same ratio for males and females. So this is round 1, round 2, round 3. So keeps the distribution of the classes in each fold the same. So now we are using the pipeline method. Pipeline where we want to first do the standardization. Then I want to use a random under sampler. And then finally the decision tree classifier. Okay. And once my pipeline has been created, then I will use the stratified k-fold because it's a classification problem. Number of splits as 5. Shuffle is equal to true. Random state is 42. And now if I check the cross-validation accuracy, it is 87%. So it was here 80. Cross-validation is giving you 87%. And now do you see? Look at the difference in the output. A clear distinction in the F1 score is there. You see that, learners? Because the ratio is very different. Similarly, I'm not even getting this as 50. So what we can conclude? What are the observations? In situations where the data set is highly imbalanced, the ROC curve can give an overly optimistic assessment of the model, since it is still highly imbalanced. This optimism bias arises because the ROC curve false positive rate can become very small when the number of actual negatives is large. As a result, even a larger number of false positive would lead to a small false positive rate. So how do we overcome to this problem? Rather than using ROC AUC curve, can you tell me in ROC AUC curve what is there on the X and Y axis? Can you all tell me in ROC AUC curve, what is there on the X and Y axis? Yeah, true positive rate and the two, it was TPR. But for imbalanced data set, we will try to create an AUC ROP, ROC AUC curve between precision and recall. That is why it is known as AUC PR curve, because it is between precision and recall, which is especially useful when positive classes is rarer and more relevant. Getting my point? Why are we now not using the AUC, the XY true positive rate and the false positive rate? So now from the Scikit-learn metrics, when I import precision and recall curve, average precision score, and now predict the output, and instead of the ROC AUC curve, I will use the precision recall curve to get the value and then see the curve. You see this? So the area under the curve is coming out to be how much? 4.938%. Getting my point? So the curve starts with high precision value of 1 and the recall is near 0. This indicates that a very low threshold setting where the model predicts only the most confidentially positive samples are positive, it does so correctly. As recall increases slightly, the precision drops sharply to a low value close to 0.2 and remains nearly constant across the rest of the recall range. This is a characteristic of a model that after a certain point begins to classify more and more negative sample. So ultimately, this nearly flat and low precision across most of the recall range suggests that the model suggests to discriminate between positive and negative classes effectively as it attempts to increase the recall. Okay. And last but not the least is the the ensemble method, where we try to create a balanced forest data set.
And with that, we have come to the end of this course. If you have any doubts or questions, you can ask them in the comment section below. Our team of experts will reply to you as soon as possible. Thank you and keep learning with Simplilearn.